topology like a dipolar, and such objects constitutes approximately 10% of the OBA star population. And in these stars, one very important consequence of presence of such a large-scale magnetic field is that the wind magnetic field interaction, they have strong stellar wind, such interaction leads to a formation of a co-rotating magnetosphere. And we recently found that at least 32% of these magnetic early type stars can produce auroral radio emission. And we have given this star a special name, which is main sequence radio pulse emitters, or MRP. So the auroral radio emission observed from these objects represents one of the most stable types of auroral radio emission, and the whole credit goes to their highly stable magnetic field. So this is an example of those radio emission observed from a magnetic late B star. So top panel show the right and left circularly polarized pulses. They are observed pulses because they are highly directed emission, and they are seen near these when their line of sight magnetic field is close to zero, because the direction of emission is approximately perpendicular to the dipole axis. And in these types of stars, it is possible to accurately measure the magnetic field, the rotation period, the inclination angle, which is the angle between the rotation axis and the line of sight, and the obliquity, which is the angle between the rotation and the dipole axis. So as a result of that, it's possible to study this phenomena, this auroral radio emission phenomena, to much greater detail in this type of stars than what is possible for cooler objects. So let me show you what we expect in the most ideal case as a signature of this auroral radio emission. So this is a very simple cartoon diagram. Here is the star, this is the dipole axis, and radio emissions are produced near these magnetic polar regions. And here I show you two frequencies. One is a new one, which is at a higher frequency because it is closer to the star, and hence at a region which has a higher magnetic field strength than this region. And they are produced approximately they are directed approximately at right angle to the dipole axis, but because of refraction which happens in this densest part of the stellar magnetosphere, which is called the inner magnetosphere, so here they suffers refraction and they get deviated in this manner. So inner magnetosphere is the part of the magnetosphere where all the magnetic field lines are closed, because the magnetic field energy is higher than the stellar wind kinetic energy. So such a scenario predicts that the light curve should be like this, that there should be two pairs of pulses near the magnetic null phases. These are called the magnetic null phases, and each pair will have one pulse coming from the north and other pulse coming from the south magnetic polar regions, and they can be distinguished from each other because they have opposite circular polarizations. And as a function of frequencies, it is expected that the gap between these two oppositely circularly polarized pulses will reduce as we go to higher frequencies. But the problem was that there has not been observation over wide frequency to check whether this kind of scenario is indeed valid. So we decided to overcome that. So we observed three main sequence radio pulse emitters with the Carl Jasinski very large array using the Savary mode observation, Savary mode Allen S band observation, which gives a continuous frequency range between 1 to 4 gigahertz, and supplemented those observations with lower frequency observation with the upgraded giant meteor radio telescope, which gives us a frequency coverage of zero point 0.4 to zero point 0.8 gigahertz. And we got a lot of surprises. So I'll show you only a couple of examples of those unexpected behavior that we observe because of the time constraint. So first thing that I would like to mention in this talk is the orientation dependence of auroral radio emission properties. So in this slide, I'm showing you the peak flux density spectra for these four ECME pulses. ECME means electron cyclotron measure emission. So what is surprising is that this pulse and this pulse, they are produced at the same magnetic hemisphere but observed at different orientation of the star, which I have shown in this cartoon diagram. So this pulse corresponds to this one, and this pulse corresponds to this one. So you can see they are from the same magnetic hemisphere but seen at different rotational phases, and they, depending on at what phases, what rotational phase we are observing, they have different kind of spectral behavior. We also discovered some very peculiar behavior in terms of the frequency dependence of pulse arrival time. So I would like to remind you that the ideal scenario predicts is that as we go to higher frequencies, the gap between the two pulses coming from opposite magnetic hemisphere should be decreased. Now look at this figure, and I would like to draw your attention to this column only. So as we are going to higher and higher frequencies, the pulses, they are coming closer and closer to each other. But here something weird happened, and here they kind of becomes more separated than this compared to this one. And not only that, you can see that the sequence of arrival of the pulses has reversed. So this kind of an observation cannot be explained by the ideal scenario, and this made us to revisit the ideal scenario. So what we realized is that in this scenario, the role of the inner magnetosphere has been significantly underestimated. So the underlying assumption is that the plasma density gradient inside the inner magnetosphere is not significant enough. But there are already analytical framework that suggests that there could be very strong plasma density gradient, and such kind of gradient that the ray path might have to pass through those high plasma density gradient regions. So in order to check how the ACME radiation will be affected by this kind of strong plasma density gradient region, we developed the 3D framework, and this is what we found. So here in the bottom panel is the predicted light curve based on the ideal scenario, which predicts that the radiation after they are produced here, they will get refracted in this manner. But what we saw is that if you see closely, then you can see that the sequence is actually opposite. Here blue comes first, then red. Blue and red corresponds to south and north magnetic hemisphere respectively, whereas here red comes first followed by blue. So what it means is that the radiation not only can get refracted this manner, but also this manner. We also found that the IM or inner magnetospheric plasma can also give rise to different cutoffs for the oppositely circularly polarized pulses, and also they can give rise to secondary pulses in the light curves. So altogether, what we learned is that this auroral radio emission is significantly more affected by the stellar magnetosphere than what had been perceived, and that's a good sign for a potential stellar magnetospheric probe. So in the next few slides, I will give one demonstration of how one can use this wideband observation of auroral radio emission from these stars to get information about the stellar magnetosphere. So here I am showing you the pulses, the right circularly polarized and left circularly polarized pulses observed from the magnetic late V star HD 133880. This rotational phase corresponds to this magnetic null, and this rotational phase corresponds to this magnetic null. This is the line of sight magnetic field variation of the star as a function of rotational phase. And our aim was to characterize how the pulse arrival time dependence on frequency, it how we can how this arrival time of the pulses varies as a function of frequency. So we will call this difference in pulse arrival time as and at different frequencies as lag. So in the if we ignore any contribution in the inner magnetosphere, then we expect that over a small frequency range, the lag will be proportional to this quantity lambda 1 square minus lambda 2 square. But when we plotted the observed values, this kind of pattern was found. This is for the RCP or right circularly polarized emission. This is for the LCP or left circularly polarized emission. And the straight line
2 minutes
here,
remaining.
sorry?
2
Uh,
minutes remaining.
okay, yeah. And the straight line corresponds to this linear relation between this lag and this quantity lambda 1 square minus lambda 2 square. And you can clearly see that they significantly vary from this linear relation, which is probably not surprising because we are now talking about wide frequency range. But what is interesting is that the way they deviate from this linear relation is different from the RCP and LCP pulses, which suggests that the two magnetic hemispheres have different kind of plasma density distribution. To understand it in a little bit more detail, we used our 3D framework and we simulated the light curve considering this kind of a distribution where there is a background plasma density and there is a high density gradient region. And we examined the effects of two quantities. One is the absolute scaling of this plasma density distribution, and other is the width of this disk, which we will call as sigma. And what we found is that the effect of changing the absolute density scaling, which is the NP naught, is only on the value of this lag. So they, for example, if you compare these two panels, you can see that their behavior is almost similar, but the y-axis are significantly different. Whereas the effect of changing this sigma or the width of the disk is that the y-axis do not change significantly, but the way they behave as a function of this quantity is becomes very different. So what we got from this exercise is that the RCP pulse, which is more like this one than the LCP, it sees more of this disk, which is the region with high plasma density gradient than the LCP pulses. And this suggests a kind of inclined disk-like plasma density distribution. So, so with that, so this is, I think, the future uh, potential that we can of auroral radio emission. So auroral radio emission from this, sorry, this should be MRPs. It's a treasure trove of information about the stellar magnetosphere. It has a unique property of being highly directed, so hence it can serve as a unique and complementary stellar probe, provided we succeed in characterizing its behavior. Thank you.
Okay, thank you very much. Do we have questions for the speaker? Either raise your hand or put them in the chat. Well, let me start with one. So is it likely that a binary companion of some kind is responsible for the inclined disk that you're postulating?
So I would say that there has not been any binary signature discovered in any of its property in any other waveband. So this is that. So that's what I would like to say, that there is no binary companion or any signature of a binary companion for this study is known.
Any other questions for the speaker? There's something in from Jackie in the chat. She writes, "This is so beautiful. Is this target viewed fully edge on? And do you see all four pulses in all MRPs, or does it depend on orientation?"
Okay, so till now, in all the discovered MRPs, we see all the four pulses. Yeah, and it's based on the it's all consistent with, because we know for these stars the inclination angle and obliquity, this observation actually matches with our expectations, so we should be able to see four pulses. So we see four pulses, so that are all consistent with uh, the the model and observation.
Okay, and then there's a couple more. One from, we have time for maybe one more from Miguel. Are you considering the effect of the misalignment between magnetic field axis and the stellar rotation axis? Could this explain the variation of the lag in the signal?
So the misalignment, I mean so misalignment between the rotation and dipole axis is called the obliquity. So that of course affects the signal, but this effect what I have modeled is is a residual effect after we consider that obliquity. The obliquity as a for the star is well known, and that of course produces some signature, some changes in the light curve, but still then after considering the obliquity, or even after considering the obliquity, this kind of signature remains. So only obliquity alone cannot um, explain the behavior.
Okay, thank you. And there's one more question from Tim Bastian in the chat. So if you could answer him offline, because
Okay.
I'm afraid we have to move on to the final speaker in this session. So thank you again to Bernali for the very nice talk. And so the third and final stellar talk that we have today is by Akshay Suresh from Cornell, who will be talking about radio emission from Epsilon Eridani. Oh, and you your time is, again, 12 minutes, and I'll give you a warning with 2 minutes remaining.
Can you hear me?
Yes.
Yeah, thank you. Hi, everyone. I'm Akshay Suresh, and I'm a graduate student at Cornell University. Today, I'll be talking about the radio emission from the nearby K-type star Epsilon Erie, and particularly highlight the role the VLA has played in unraveling the emission from Epsilon Erie. So to start off, here's a brief introduction on Epsilon Erie. It's a K-type star, so it's slightly cooler and less massive than our sun. It is very nearby, located at 3.2 parsec distance. And on the right, you have a figure comparing the scale of our solar system with that of the Epsilon Erie system. The Epsilon Erie system extends far beyond that of our solar system, and there are two confirmed members in this system. The first is a Jupiter mass planet, Epsilon Erie b, at 3.4 AU separation. The second is this outer debris disk, a really wide disk at a central separation of 64 AU. The width of this disk is about 20 astronomical units. Additional proposed but unconfirmed members of the system include two outer planets and warm belts interior to the orbit of Epsilon Erie at 3 AU, and another belt, a dust-producing belt at 20 AU. Now, due to the proximity of this system, Epsilon Erie has been a prime target for early searches for extraterrestrial intelligence and more recently, stellar and planetary radio emission. Early searches for SETI include Project Phoenix by Jill Tarter and Project Ozma by Frank Drake. Now here is a timeline of radio detections of Epsilon Erie. And you can see starting in around 2007 to 2008, we began to make a slew of detections across a broad range of radio frequencies. The VLA in particular has been quintessential for detecting Epsilon Erie at frequencies below 40 gigahertz. These are the frequencies where emission from the chromosphere and the corona dominate. Majority of the detections are of continuum emission, but we have one really curious flare detection at 2 to 4 gigahertz in a study led by Tim Bastian. So I'll discuss this flare in detail later in my talk. For now, let's focus on the continuum emissions. Putting together all these multi-epoch measurements into a single spectrum, here is the observed spectrum from Epsilon Erie. And you can see that if you convert the flux densities to brightness temperatures, the range of temperatures that you see, 10 to the 4 to 10 to the 6 Kelvin, is consistent with an optically thick thermal interpretation. And leveraging our knowledge about the sun, at the highest frequencies, the emission comes from the chromosphere above 100 gigahertz, and the corresponding temperature ranges are in agreement. And as you go towards lower frequencies, you see progressively higher heights in the stellar atmosphere. So the stellar corona begins to show up more and more on the stellar disk. And therefore, you see an increase in temperature going down to lower and lower frequencies. Now here, this relation can be encapsulated with a simple equation where the disk average brightness temperature is related to the coronal temperature and the chromospheric temperature. The factor F sub c, which is frequency dependent, is the filling factor, or you can think of it as the fraction of the stellar disk occupied by coronal hotspots. Now, this is very good. We understand the coronal and chromospheric continuum emissions really well, at least in the quiescent, for the quiescent Epsilon Erie. But what are the alternate models? So previously, just looking at the 10 to 50 gigahertz spectrum, an alternate model which was proposed was stellar wind emission. So you have thermal emission from a stellar wind expelled by the star. But the characteristic spectrum from such a stellar wind follows nu to the minus 0.1 in the optically thin regime and nu to the 0.6 in the optically thick regime. And clearly our most recent data points at 2 to 4 gigahertz disfavor the wind model. Therefore, stipulating that any wind flux be less than our observed flux of 29 microjansky at 2 to 4 gigahertz, we place an upper limit on the stellar mass loss rate. And this is particularly significant because Epsilon Erie has been historically thought of as a young, profusely high mass loss system. And it doesn't seem to be the case, which models for Epsilon Erie need to take into account. Moving ahead to the flaring emissions, as I mentioned previously, Bastian et al. In 2018 or 2016, they discovered a very interesting 940 microjansky flare from Epsilon Erie. At the peak, the Stokes-V fraction, or the fraction of circular polarization, is about 30%. And what makes this flare extremely exciting is that if you translate 940 microjansky to the sun, you would expect a flux density of 10 to the 8 Jansky, or 10 to the 4 solar flux units. And here is a plot from Nita et al. 2002 showing the cumulative burst rate distribution of solar radio bursts at 2 gigahertz. And notice that for this red dashed line, which denotes a flux of 10 to the 4 solar flux units, the expected event rate is like 1 in 25 days, which makes this discovery exceptionally extraordinary and also a really rare event. What is even more curious about this flare is its localization. So in the next slide, I show the localization of the flare. Here, the X and Y axis denote position offsets in RA and DEC from the host star. So the asterisk symbol in the origin is the host star Epsilon Erie. The flare has been localized to about 1 arcsecond away from the star. And curiously, the confirmed planet is at about 3.4 AU, and this star is at 3.2 parsec distance. So that's roughly in agreement with the position offset of the confirmed planet. But is it really coming from the planet, or is it the star that's produced this flare? And the answer is we still do not know. Now here I've plotted in red and blue 2 different orbital ephemeris for the confirmed planet. Red is an old ephemeris with very limited radial velocity detections, and it predicts a highly eccentric orbit for the planet. The blue is an updated ephemeris based on 30 years of radial velocity data and upper limits from non-imaging. So since you have a radial velocity detection and an imaging non-detection, the preferred orbit is edge-on, which is why it's shown as a straight vertical line. And however, the orbital eccentricity predicted is 0.07, which is a nearly circular orbit. We do not have a good handle on the inclination or the face of the planet along this orbit, which means the planet could be anywhere along the blue line, or it could be slightly displaced from the blue line in either direction, left or right. And hence, we consider 2 possible scenarios. One is like a stellar flare emitting non-thermal gyrosynchrotron. And the second is, could this be a sign of star-planet magnetic interactions? In the latter case, you have a stellar flare or energetic electrons from the star, which impinge upon the magnetosphere of a planet and produce cyclotron maser emission at the local cyclotron frequency. So if you consider 2 to 4 gigahertz emission, the local magnetic field at the planet should be of order a kilogauss, which is extremely powerful for a Jupiter mass planet, about 3 orders of magnitude stronger than Jupiter itself. Now, we were very intrigued by this system, and together with some collaborators, I attempted a follow-up observation looking at the system for 12 hours and with sub-arcsecond accuracy, sub-arcsecond localization with the VLA in its most extended configuration. What did we find? Well, we were unfortunate. We didn't see any detection of any flare repeats at a phi sigma threshold of 95 microjansky. And in a bid to unravel why we saw non-detection, I happened to come across the activity cycle of the star. So this is the y-axis is the chromospheric activity measured as emission of the calcium, singly ionized calcium and potassium lines. And the x-axis is the year. Notice that all the data points are fit well by this empirical 2.9-year cycle, which is quite regular until like 2019. The radio flare detection by Tim Bastian happened around the peak of the cycle in 2016. And we tried to schedule our observations close to a subsequent expected peak around 2019 to 2020. But guess what? The star did not follow its expected activity cycle. The activity sort of flattened out, or it became acyclic, and which is rather interesting, and we do not have a good explanation for this. This is indicative of anomalies, magnetic anomalies on the star itself. And with the star exhibiting unusual magnetic activity, it is necessary to continue optical monitoring of the system and follow periods of high activity with radio observations to identify future flaring repeats. And so with that, here is my summary slide. We have detected thermal continuum emission from the quiescent Epsilon Erie at a broad range of frequencies. We saw a curious flare at 2 to 4 gigahertz in 2016, but the origin of this flare is still unknown. Epsilon Erie, since it's entered an acyclic activity phase, it is necessary to continue optical monitoring of the system and couple it with radio observations to identify potential repeat flare occurrences. Thank you for your attention.
Okay, thank you very much. Okay, I see a question from Gregory.
Hi, Akshay. If you go back to the plot that shows the cycles, it seems like that there are a fair number of periods of acyclic activity already in the source. for instance, around 2007, possibly in 2005. So how odd is that acyclic activity? Is it really that surprising?
I would say it is fairly surprising because if you look even around 2007 here, over at least a 1 to 2 year period, it's a kind of flattened out, or it's not flattened out, it's followed the expected trend. But then here, like starting from like 2018 and by 2019, where you expect the points to be close to the peak, it's instead at the stellar minimum. So that's rather significant and not seen elsewhere in the activity cycle.
Thanks.
Okay, I thought I saw another hand briefly a moment ago. Are there any other questions for the speaker? There's a note from Jackie in the chat. Great job putting together so many pieces about this star. For the quiescent spectrum with the gyroresonance emission mechanism, does it provide an explanation for where the peak in the spectrum occurs?
So I should add that here the emission is thermal and gyroresonance is the prime. I haven't discussed it, but gyroresonance is the primary source of optical depth. And let me go back to the continuum emissions figure. So here you're referring to, I presume you're referring to the peak in the spectrum around 6 gigahertz. And I would say that is related to how the filling factor varies as a function of frequency. So you see a flattening of the filling factor, and that is reflected in the overall spectrum. And notice that between the flux density and the brightness temperature, there's a nu square dependence. So gyroresonance determines the optical depth, and it ensures that you're in the optically thick regime throughout the full range of frequencies from 2 to 50 gigahertz. So it does not explain exactly why the spectrum is peaking at 6 gigahertz. That has to do with the conditions on the star and the fact that the coronal filling factor seems to flatten out at the lowest frequencies.
Okay, thank you. Do we have time for perhaps one more question? If anybody has one. One from Hari. Are there radio observations for the same epoch that shows a periodicity or quasi-periodicity?
Radio observations that show a periodicity, I presume you're referring to any flaring emissions, but okay, from 2005 to 2020. No, this system has not, we could not detect this system due to the limitations of radio telescopes prior to 2007 or even 2010. So if I go back to the timeline, the first detections were made in 2013 by Tim Bastian. So we don't have a lot of data on the system, and all the detections were just continuum emissions. So we haven't been able to track its activity cycle in a regular manner at radio, at least. We do have X-ray and optical activity cycles, and very curiously, the X-ray continues to exhibit a regular 2.9-year cycle, but the optical light curve has shown this anomaly around 2019 to 2020. So this trend is seen in optical, but not in X-rays. So I suggest that you look at Kofara et al. For more details.
All right, well, thank you again, Akshay, and to all the speakers from our first session. And thanks to everyone for staying very, very well to time. And I think I now hand things over to Stephen White, who's going to be chairing the solar system session.
Thanks, Lynn. Yes, as Lynn said, we now move inside the solar system with 4 talks covering planets, the sun, and other objects. And we start with Imke de Plata from UC Berkeley. Imke, if you'd like to load and take over. Thanks. I'll give you a warning at 15 minutes, Imke.
Imke, if you're speaking, we can't hear you.
Okay. So thanks for the invitation. It was fun going back in time and remember the old VLA days, like, well, in particular the people, and also these huge heavy disk packs that we have to move around. And then I was sitting next to Eric Greisen, who was adapting apes on the fly, so I could actually proceed reducing planetary data. And the other kind of cute memory is Barry Clark's advertisement, clean components for sale. And then, of course, above all, the big, huge stakes in that all. So those days were really fun. So in this talk, I will address both the early scientific results and also more recent ones. So we observe planets because ultimately they help constrain models of our solar system. And nowadays, they also provide benchmarks for exoplanets. So radio observations by themselves are unique in that they probe regions in planetary atmospheres and subsurfaces that are inaccessible to other wavelengths. And so with interferometers, we can actually map the atmospheres below the visible cloud layers. We can map subsurface structures of rocky and icy bodies, including also planetary rings. And we can constrain the magnetic field configuration and electron population, in particular for Jupiter. So in the following, I will give many examples of VLA observations, and needless to say that each topic could easily cover a full talk, so it will be very, very brief. So Mercury, during the day, its surface will heat up. Heat is conducting downwards so that the subsurface is heating up, and at night the surface cools off via radiation into space, and heat is conducted upwards from below the surface. So due to Mercury's 3-to-2 spin orbital resonance, there is an uneven heating pattern, which results in so-called hot longitudes at the site facing the sun every time the planet is closest to the sun. So that is in Calorus Basin and the opposite hemisphere. So at radio wavelengths, we typically probe about 10 to 20 wavelengths into the surface. And so by observing over a range of wavelengths, we can map the brightness temperature at different depths. So the map here on the left shows these hot longitudes, actually down to over a meter below the surface. So how much the temperature varies between night and day, and hence also the temperature contrast in the hot longitudes, depends on the composition of the crust and also its compactness with depths. So by comparing these data with insolation and radiative transfer models, we showed that Mercury has essentially a basalt-free crust. And that suggests that there is no volcanic activity from the deep layers, and hence it must still have a hot core. So these conclusions were later confirmed by the MESSENGER spacecraft. So the image here on the right shows a residual map after subtraction of the model. And it shows in particular that the poles are much colder than expected. And that is caused by permanent shadowing in the craters. And this is also where ice was found using radar measurements. Radio maps of Venus suggest that the planet is overlaid by at most a few centimeters of solar dust. And so the low radio emissivities here in these green areas in the Aphrodite region suggest the presence of very highly conducting minerals such as pyrite, iron, and sulfides, which is indicative of past volcanism. So the map of the polarization here on the right is very typical. It increases towards the limb, and its strength depends on composition. But the signal, however, can be decreased by surface roughness, so it's not so easy to interpret. So a radio spectrum of Venus shows an increase with wavelengths when you probe deeper, warmer layers of the atmosphere down to a maximum of about 700 Kelvin near the surface. And beyond that, we start to probe the subsurface layers that we just discussed. So by modeling the spectrum, people have found that there is a tiny amount of sulfuric acid, about 1 to 2.5 part per million, and maybe a few tenths of part per million sulfur dioxide within and below the cloud layers. Early observations of Mars focused on the surface and the subsurface. And Don Rudy obtained maps at 2 and 6 centimeter, which are not shown here. And he developed a season-dependent calibration standard for Mars, and that is actually still used today at ALMA. So water has been detected in its stratosphere, as shown here by the emissions along the limb, where the path length through the atmosphere is longest. And the colored background is the emission from the subsurface. So by modeling the line profile, the total precipitable water vapor has been shown to range from about 0 up to 20 micron. And for comparison, at Mauna Kea in Hawaii, it's usually a few millimeters. So in the 70s, I observed Jupiter's synchronous radiation with the Westerbork radio telescope, and that showed the radiation belts here. And I built a model at the time to simulate these belts. Well, when the VLA was completed, we could resolve these radiation belts, as shown here in this legacy image from the VLA. So then using Bob Salt's software, we made tomographic reconstructions of these data, and that really shows the warped surface of the magnetic equatorial plane, where most of the electrons reside very well. And also it shows the high latitude emission rings shown here as the emission peaks. So a comparison with models showed that these high latitude emissions were somewhat enhanced in brightness because the moon Amalthea is kind of redirecting some of the electrons along magnetic field lines into these regions. And then closer to the planet, Jupiter's ring is absorbing a fraction of the small pitch angle electrons. So these 3 rings are seen mostly as separate rings. We further noticed that the magnetic field must be much more complex than indicated by the dense spacecraft-derived magnetic field models. And what's interesting is that the largest deviations were found near longitudes where the Juno spacecraft found a large negative, or the so-called blue spot in its magnetic field. In 1993, Carolyn Shoemaker discovered a comet Shoemaker-Levy 9, in orbit about Jupiter. And this comet had been tidally disrupted into over 20 pieces. And each of these pieces were expected to crash into Jupiter in 1994, as shown here by this artist impression. So we observed this with the VLA, and we saw huge changes in the brightness distribution. Here we see an image before, and here one after impacts. So following each impact, a fireball rose up through the atmosphere, and that was visible here as plumes by the Hubble Space Telescope. And each of these plumes is then preceded by a shock front, and that shock front entered the magnetosphere and essentially energized the electrons everywhere in these main radiation belts and locally in the high latitude regions. In December of 1995, the Galileo probe entered Jupiter's atmosphere. And here we show images taken in the visible at 5 micron wavelengths in the radio. So at 5 micron wavelengths, we see thermal emission from the lower atmosphere in cloud-free areas. So that is the North Equatorial Belt, NEB, the brown belts here on Jupiter. The Galileo probe entered here in this hot spot, also seen as a bright region, seen here in the visible. But at radio wavelengths, we can actually probe below the clouds, and because the clouds are transparent. But radio maps require integration times over many hours, so we cannot see any longitudinal structure here, just the cold zones, light zones, and the warm belts, brown belts, depending on how deep we probe. So how deep we probe depends upon the abundance of ammonia gas, which is the main source of opacity, and also on the wavelengths. So contribution functions are shown here on the left. where at 1 or 2 centimeter, we probe within and just below the upper cloud layer, the ammonia ice cloud layer. And at 6 centimeter, we probe sort of within the water cloud. And in between, we have the ammonia hydrosulfide layer, or NH4SH cloud layer. So the Galileo probe measured the ammonia abundance at about 3 to 4 times the solar value in the deep atmosphere, as shown over here. But modeling the VLA data with radiative transfer models showed that the ammonia abundance must globally decrease from this high Galileo value down to levels below the solar value even in the upper 2 to 3 bar level. And in the belts, it's even lower than that. Well, to overcome the lack of longitudinal structure, Bob Salt developed software to essentially take out the planet's rotation. And that reveals the same hotspots as seen in the infrared. So here we see at the radio wavelengths, the hotspots. This is where the Galileo probe entered. And here we see the same at 5 micron. And in the hotspots, the ammonia abundance is even lower than in the NEB, down to several bars at least. Fast forward, after the VLA upgrade, Jupiter's zone belt structure can be distinguished in great detail, as shown in this image here, after subtraction of a uniform limb darkened disk. And this actually is a composite of 2, 3, and 6 centimeter data. The high brightness temperatures are again the belts, and the low ones are the zones. All the way around, we see this red glow, and that is Jupiter's synchrotron radiation that we just discussed. So we show here scans through each image, north-south scans. And from these, you can also see that the high brightness temperatures are actually at the interface of a belt and a zonal region. And the low brightness temperatures all correspond to these white zones. So we show again the contribution functions here, which show that we probe depths in the atmosphere from the upper ammonia cloud layer down into the water clouds. So we effectively now have spectra at each latitude on Jupiter's disk, and we can match that with radiative transfer models. So as mentioned before, the main source of opacity in Jupiter's atmosphere is ammonia gas. So we can derive the altitude-dependent ammonia abundance at each latitude, as shown here in this colorful graph. So here we show, as a function of the planetographic latitude, south to north, and as a function of pressure from high pressures, 20 bar, up to the visible cloud layers, the ammonia abundance. So as an example, we show here a spectrum and also an ammonium profile in the cyan color for the equatorial zone and in red for the north equatorial belt. So we had adopted the Galileo probe measurement for ammonia gas at levels below about 8 bar. And you can see that ammonia gas is at its full column in the equatorial zone, but that it's much depleted in the north equatorial belt. Now, in theory, we can probe deeper levels by going to longer wavelengths, but in practice, the radiation gets overwhelmed by Jupiter's synchrotron radiation. However, Juno, in orbit about Jupiter, is not much affected by the synchrotron radiation. And so in the future, we can combine Juno data from the deep atmosphere with VLA maps at higher altitudes. So we applied the Salt derotation technique also to these recent data, and the results are actually quite stunning, shown here at 2 and 6 centimeter data. Of course, you can clearly see the zones and the belts, but you can also see, it just disappeared, the great red spot, oval BA, and you can see many hot spots. And you can, here's the great red spot, you can see large dark plumes, in particular here at 6 centimeter wavelengths. So all these variations in intensity are due to spatial variations in the ammonia abundance, and they provide information on atmospheric dynamics. So in the plumes, for example, ammonia gas is brought up from the deep atmosphere, it rises up to above the main cloud deck, And in the hot spots, dry gas is going down. So ammonia gas is depleted down to about the 8 bar level. So the hot spots and the plumes together are manifestations of the so-called equatorial Rossby wave, a planetary, large-scale planetary wave in planetary atmospheres. The data also show a lot of small vortices in the upper few bars, the so-called weather layer, where condensation takes place. Moving to Saturn, starting with 2 legacy images at 2 centimeter wavelengths at different ring inclination angles. The thermal emission from the atmosphere is shown in red and the rings in blue. And in fact, the rings are mainly seen because of Saturn's radio light reflected off the ring particles.
4 minutes, Imke.
Multi-wavelength images, by using images at different wavelengths and different ring inclination angles, we notice large variations in zonal bands with wavelengths and over time, and they're all caused by variations in the ammonia abundance. Now, by flipping an image like this horizontally, and then subtracting it from the original image, we see asymmetries in the rings, and those are caused by so-called gravitational wakes or self-gravitational clumps of material. More recent maps show the ring structure in great detail, and these rings have been modeled with David Dunn's Monte Carlo scattering model. So the bulk of Saturn's rings is composed of water ice, but it's the small fraction of non-icy material or dirt that reveals clues about the system's origin and age. So the fraction of dirt is at most a few percent, and it's probably brought in by micrometeorites, which then puts an upper limit to the age of the rings of about 200 million years. So the rings are very young. By subtracting a uniformly darkened disk and the model of the rings just discussed, we can clearly see the banded zonal structure on Saturn's in Saturn's atmosphere. And in particular, we also see this hexagonal structure, the hexagon, in the northern hemisphere, which has been seen in the visible for the past few decades, but has never before been seen in the radio. So by taking out Saturn's rotation, we see this intricate pattern of bright and dark regions, ammonia abundance variations near the equator, and we see a lot of or less ammonia, high brightness temperature at higher latitudes, which is at the latitude where a great storm was found in 2010, 2011. The upper part is a Cassini map from 2011, also showing, of course, this large storm because it had just happened. And by comparing these 2 maps taken 4 years apart, we can deduce the evolution of the storm region. Okay, moving towards Uranus, the first maps of Uranus already revealed this warm pole, indicated here by a little cross. And that was predicted based upon a steady increase in the brightness temperature in single dish measurements since the 60s, while its pole moved into view. In 2005, both poles are visible. And for Neptune, we also see a warm pole, just the South Pole. A comparison with models then shows that the opacity must be low at the poles, down to many tens of bars. Comparison further reveals that both planets must have a very low ammonia abundance, presumably because all the ammonia is taken up in this ammonia hydrosulfide cloud. And that's interesting because it means that the N to S ratio is less than 1. It's 5 on the Sun. So that really tells us something about formation models. The spectra further showed that these ice giants, most of the radio opacity is in fact attributed to H2S rather than ammonia gas. Recent maps show the zonal bands on each planet quite nicely. And these maps at different wavelengths have been modeled in terms of the hydrogen sulfide opacity as shown here on the right. So the big difference between the cold sort of mid-latitudes and the very warm poles is indicative of a global circulation pattern where air rises at mid-latitudes, It dries out at the higher levels in the atmosphere through condensation, and then the dry air descends at the poles, moving all the way from the stratosphere down to 40, 50 bar level. So really a huge circulation cell. So that's some conclusions and future directions. So the VLA has contributed much to our knowledge about the upper few meters of crust, composition and compactness, the atmospheric composition and dynamics of the giant planets, and also Jupiter's radiation belts and cometary impacts. So we've seen tremendous improvements in the data after the VLA upgrade, in particular these nice derotated maps of Jupiter. And we expect a similar leap in data quality with the NGVLA. And for that, I will refer you to Brian Butler's talk later this morning. Thank you.
Thank you, Imke. Questions?
I have a question, Stephen,
Yeah, go on, Brian.
or Imka. So, what was the first time you went to the VLA?
It was either 1980 or early 81. we moved to the US in October 1980. And so as soon as we could observe, we just drove over there and observed and reduced the data. So I don't know if you remember, but the only time you could actually use the computers was at night. So the first thing you do at night is take your tremendously huge, heavy disk pack, swap it out with disk packs from other people that were already in the computer. And then you could just start your data reduction during the night.
Yeah, you couldn't reduce data during the day because Rick was using all the computing resources.
That's right. That's right. And then you took Rick's pack out. So you stopped the computers and you could just continue with your own data.
Rick objects to that discussion. Any other questions? So let me ask, on the age of the young age of the Saturn rings that you discussed, isn't that somehow inconsistent with the timescale for solar system evolution? At this stage of the solar system, you'd have young rings there?
No, because if the material is brought later in, I mean, the historical view was that the rings and Saturn kind of evolved and formed together. But you can also have material that just comes in later, and that is sort of what we are now thinking of. And there are several pieces of evidence that point to these young rings. But I mean, this kind of meteorite one is one, I think, of the strongest pieces of evidence. And others are, I think, the way that little moonlets at the edge of the ring are moving away from the rings. And I think there's one other piece of evidence that I forgot about now. But so people now are indeed thinking that the rings are young.
Okay, time for one more question. I'm not seeing any more hands, so thank you very much, Imke, for a wonderful talk. Those images of Jupiter and Saturn are always just stunning.
Yeah, that's why I had to show images.
We move on. The next speaker is Jason Cooey from NRL, and he will be talking about Faraday rotation observations in support of Parker Solar Probe. Thanks, Jason. I'll give you a warning with 2 minutes to go.
Sounds good. So I'll just flip on the proverbial virtual laser pointer here. So I'm Jason Cooey. I work at the U.S. Naval Research Lab in the Remote Sensing Division. And this morning, or this afternoon in my time zone, I'll be describing our program here to use the VLA to supplement Parker Solar Probe. So Jackie gave a pretty good overview of the sun structure, but just to remind everyone, the corona is kind of the sun's outer atmosphere of highly ionized gas, and as it propagates away from the sun, sort of evolves into what we refer to as the solar wind. And in particular, I'll be talking about perihelion passages of this satellite called Parker Solar Probe, which I'll get back around to in a little bit here. So the name of the game is Faraday rotation. And this is a phenomenon that occurs when you take a linearly polarized signal and propagate it through a magnetized plasma, such as the corona. And that induces a rotation in the plane of polarization that is proportional to the wavelength squared, and the proportionality parameter, RM, or rotation measure, actually is what contains the information about the physical structure. So it's a line of sight integral containing the plasma density and the magnetic field along the line of sight. So in principle, you need, really nice models of both of those or independent data for them in order to actually disentangle their contributions. So for the coronal observations, historically, we would select sources with linear polarized intensities greater than about 5 millijansky per beam. But with the upgraded VLA, we can actually do these, an order of magnitude better now. So basically, we can get sensitive FR from lines of sight with intensities of 0.5 or below millijansky per beam. And we also tend to observe at wavelengths rather, of 1 to a few tens of centimeters, because that's what gives us our sensitive FR measurements for the corona. So we really like L band, S band, and C band there. So what can coronal observations do using FR? Well, they can return important information about the coronal magnetic field strength and structure, and have been used to validate as well as determine new empirical models over decades. They've been used to probe the internal plasma structures of coronal mass ejections, and Jackie described these earlier, but I'll just remind you, these are the primary drivers of space weather events, so it's really important we understand their magnetic structure. They can detect coronal magnetic field fluctuations. They can detect electric currents in the corona. And those are important because, they can place constraints on coronal heating models, such as wave turbulence heating or dissipation heating. And so I'll point out here, everything you see in red, these are all VLA observations over the years. So the VLA has had a very rich history contributing to our understanding of the corona's magnetic field and plasma density structure. And of course, the VLA has contributed to many other solar science topics. So you can see Tim's talk right after this one, or Steve Spangler's talk tomorrow for more details. So Parker Solar Probe. This is a spacecraft that aims to get in right up close to the sun, less than 10 solar radii, or 4 million miles from the photosphere. That is very, very close. It has 4 instruments on it: Sweep, Fields, ISIS, and a white light imager called WHISPER that is NRL developed. And Fields in particular is important to us because that's what measures or detects the magnetic field in situ in the corona. So the reason it wants to get in so close, and of course the reason we do our observations with the VLA so close to the sun, is because this is where the solar wind accelerates from sub to supersonic speeds. That's where the solar wind becomes super alphanic. It's where a lot of the highest energy particles are born. So it's a very important region for both solar physics as well as just stellar or astrophysics in general. And I'll just point out that almost as long as the VLA has been in existence, that's how long the concept for solar probe has been in existence. And so it's taken quite the revolution to get this thing up into space. And of course, now it's revolutionizing solar science. So this is a video that kind of gives you a feel for, what does perihelions look like or will look like in 2024 or 2025 when it's getting really close to the sun. So the images you're seeing are actually from Secchi white light coronagraph images here. And you can see that, we really expect it to fly through, all these streamer structures you see in the sun, all these massive eruptions of plasma, these coronal mass ejections you see. So that's just going to be really neat. So where does Faraday rotation come into the picture? Well, as PSP continues getting gravity assists from Venus and swinging in closer and closer and closer and closer, as I said before, it's only going to get to about 9 solar radii from the sun, whereas Faraday rotation can probe the magnetic field and plasma structure, down to 2 and even closer to the sun than 2 solar radii. So this gives you kind of a diagram of how we set up these observations. We choose background linearly polarized radio sources to act as beacons. And we select them such that the lines of sight either lie upstream, sampling the plasma before it comes out to then be sampled by Parker Solar Probe, or when Parker Solar Probe is in and around perihelion, we basically choose sources that track right alongside its trajectory, or as close as we can with the sources on sky during that time. So NRAO was kind enough to let us do this pilot program for 3 perihelions, number 5, 6, and 7, across 3 different array configurations at 1 to 2 gigahertz. So this setup here kind of gives you an idea of what we do, at or very close to perihelion. We essentially track the VLA across a series of naturally polarized radio sources and just kind of hopscotch back and forth across these to get our FR measurements. So I'm not going to go into too many details on these results. A number of my students have submitted pre-recorded talks, so please see that section on the VLA 40 website for more details. So I'll just highlight some key features here. Perihelion 5 is quite entertaining because it's during C array configuration. So for the historical or legacy VLA, the rule of thumb was you're not going to do this in D array or C array because they have so many short baselines that basically the sun gets into the side lobes and you get this solar interference that plays havoc with the phase structure, and you shoot yourself in the foot. But because of COVID, essentially the pandemic restructuring the VLA schedule last year, we got a chance to observe during C configuration. And as it turns out, largely thanks to the massive upgrade the VLA underwent, I'll direct your attention to the blue data here. We can actually do very sensitive Faraday rotation observations with C configuration now. So that was a delightful surprise for us. So perihelion 6 occurred in September last year, and I'm going to use this here to kind of highlight the power of this approach. So this approach of simultaneous VLA FR measurements with in situ PSP measurements. So what you see in the top plot here is detections from PSP's field magnetometer. That's all the red data. And if you want more information about this modeling, you can see Vance Kreider's talk. But I'll just point out that, a model that was derived by Sakurai and Spangler from VLA observations still does pretty good, almost 30 years later here. And even a very physical magnetic field model, this dipole quadrupole current sheet, blue data here, magnetic field model, from about 20 years ago, does a very good job still during the solar minimum conditions of these observations. And one of the other things I'll highlight is, especially these 3 models are very tight, and you could choose any of them really to kind of give you a feel for what's happening beyond 20 solar radii. But in the realm of VLA Faraday rotation here, you can see that, especially down below 10 solar radii, not only do these models start diverging dramatically from each other, but also their ability to reproduce the data very dramatically. So one thing I will highlight is our stuff that got below 5 solar radii on this particular set of observations The physical DQCS model does a better job of representing what we saw with the VLA than the more simplistic power law models featured here.
2 minutes, Jason.
Thank you. So for perihelion 7, I'll just sort of summarize, that at its closest, PSP is only ever going to get down to about 9 solar radii. So everything below 9 solar radii, that's where the VLA and the GBT are going to continue to be important for understanding the plasma density structure and magnetic field structure. So I'll just advertise here. We do have a set of observations geared up for perihelion 10. That'll be really exciting because PSP will finally be in our backyard, our Faraday rotation backyard at 15 solar radii or below. It's about 13.3. And we also have Tim Bastian and I observations set up, or proposed rather, sorry, for the VLA and GBT next year for 12 and 13. So looking ahead, one of the things we want to do is take wide field imager for Parker Solar Probe WISPR data. You can see it in this video. This is the white light imager flying into the sun, and it's just returning beautiful, beautiful images like the video you see here showing these finely detailed structure of streamers and coronal mass ejections, and hopefully more of those coming up here as we get towards solar maximum. So the idea is we want to basically develop a tomographic method to determine, of course, the locations of these streamers, as you see in this simulation, that pass over, under, and right through as PSP flies through the corona. And once that work is done, which it's being done by a PhD student, Megan Kinney, working under Craig DeForest at the University of Colorado Boulder, we'll be able to, run our lines of sight through this so that we can use the WISPR data to provide detailed coronal density information so we can then disentangle that contribution from the magnetic field. So I'll close here by once again advertising. If you want to find out more details, you can see the pre-recorded talks of my students. And if this kind of thing excites you, you want to join our program as a postdoc, or if you want to utilize our data and collaborate with us, by all means, please contact me. Thank you.
Thanks, Jason. Questions?
Stephen, I have a question for Jason. Well, go ahead, Brian. You were in first.
A very quick one. How long does Parker Solar Probe operate for?
So its primary science mission is sort of to the end of 2024 and into early 2025. Of course, we're hoping that it's, like Stereo or SOHO, it'll enjoy an extended lifetime, but nominally about 2024, 2025. So
thanks.
Certainly.
Steve?
Yes, very nice talk, Jason. That's great stuff. One of the questions I had is, are you kind of talking to the Parker Solar Probe people, the teams, like Stuart Bale, for instance, to kind of mesh what your efforts are?
Yes. So we, of course, enjoy the auspices of working at NRL. So that's where WISPR was developed. So we're working on trying to start a new program, a new base program in a couple of years, or to get it finished, I guess, in a few years, with Brian Wood and a few others, Mark Linton at NRL on the WISPR side of things. And then, of course, conversing with Stuart Bale and some of his contemporaries on the fields data. But one of the nice things with PSP is it does make all of its data essentially publicly available within kind of a latency of a few months perihelion. So if you wanted to, you can, you could just go over and download their magnetic field data, for instance, or sweeps, particle counts.
And they also do a good job of coordinating observations prior to each perihelion. So there is a lot of coordination there. Any other questions? If not, thanks again, Jason. Look forward to seeing the results. And we will move on to Tim Bastian from NRAO Charlottesville, who will talk about VLA observations of the sun. You're muted, Tim.
Okay, can you hear me now?
Yep.
Okay, great. Thanks, Stephen, and thanks to Jason and Jackie and Bernali and Akshay for introducing some of the concepts and terminology that I'll be using during the course of my talk, which is a few VLA highlights from observations of the sun. Just by way of introduction, I think Jackie's already done a good job. It's a mere 5 microparsecs away, but it's interesting as an astrophysical object because so many fundamental processes that we encounter in astrophysics occur on or within the sun, from magnetic energy release to shock formation and propagation, MHD turbulence, and so on, all of which can be studied in quite a bit of detail, either using remote sensing observations from the ground, or even in the case of the sun and solar wind, in situ observations. Now, ground-based radio observations have played an important role for the past several decades, with the VLA featuring prominently. But I should probably point out that exploitation of a general purpose telescope like the VLA, which serves a broad set of constituents, is not without challenges, because the sun itself is big, of order half a degree in size. It's bright, it dominates system temperature. It's complex, so you need lots of Fourier components. And that stands in tension with the fact that it's time variable, from timescales of milliseconds during flares all the way up to decades. And it may surprise some of you to learn that the VLA is not available on a daily basis to our community. We need to share. Nevertheless, the VLA and JVLA have contributed myriad insights into a number of outstanding problems. I'm going to give you a very quick and very light view on just a few of these at a fairly superficial level, but I hope it gives you at least a flavor of the kinds of things the VLA has been doing. Let me start with flares. Really, even before the telescope was available and commissioned and dedicated back in the late 70s, when there were just a handful of antennas available, the community was already beginning to use it to make new observations. The very first observation I'm aware of was done in 1978 by the Caltech group, led by Ken Marsh, with Hal Zarin and Gordon Herford. An example of a flare observation from 1979 is shown in the middle inset there. And the first high resolution two-dimensional images, few arc second resolution at 15 gigahertz, so the first microwave observations in 2D are shown in the grayscale to the left, superposed on grayscale H alpha. So one of the struggles in the early days was simply to understand the spatiotemporal relationship between emissions at the various wavelengths, particularly optical and hard X-rays. Note that 10 antennas only were used for this early work, but self-cal was already in play. Active regions, well, these are the sort of host regions on the sun where activity occurs, flares, coronal mass ejections, filament eruptions. A lot of early work was motivated by observations that were done at the Westerbork Synthesis Radio Telescope, the WSRT, a linear array, which sort of teed up motivation for very large array observations of solar active regions, also occurring in the late 70s. Here's an example from 1979 from Ken Lang and Rob Wilson. Note the difference between the LCP and RCP brightness distributions. This has been an enduring problem that people have been interested in for a long time, and it extends well beyond just radio observations, but into UV, EUV, optical, and soft X-ray observations, namely the nature of the plasma environment in and above solar active regions and how it evolves in time, ultimately producing the myriad activity that we witness. I like this paper from 1998 by the Maryland group, Zhang Li, Stephen White, and Mukul Kundu and others, which sort of put current state-of-the-art modeling to the test by sort of validating some of the assumptions made concerning the structure of the magnetic field in active regions. It is not enough to simply take a line of sight spectrum. You need to take into account the fact that the magnetic field itself is highly structured. And what was shown here, using dual band observations, 4.9 and 8.4 gigahertz observations, is that a potential field extrapolation is not sufficient to model an active region. In fact, you need to take into account currents and stresses within the magnetic field using force-free calculations. And in so doing, these authors were able to very elegantly, I think, demonstrate the importance of force-free extrapolations to bind together the models of solar active regions at that time. And the models have only gotten more sophisticated, but I can't really go into those today. Just as an aside, I think it's worth sort of pointing out that some of these early developments also pushed some developments on the theoretical side. Dulk and Marsh in 1982, as a means of more easily interpreting some of the observations of incoherent gyrosynchrotron emission during flares, developed approximate expressions that could be used very quickly and easily by the community for the emission and absorption coefficients. It's interesting to me that these were widely adopted by the stellar community and continue to be used. You can see the citation rate of the Dulk 1985 annual review article to this day. It has, going on 1,000 citations. Another interesting example is the discovery of coherent circularly polarized coherent radiation spike bursts in the late 70s. Studied spectroscopically for many years, but imaging has been more problematic. Melrose and Dulk proposed that, in fact, taking a page from the planetary radio community, that the cyclotron maser instability, which drives these, is in fact responsible for driving these spike bursts. This is basically using what we know about auroral kilometric radiation on Earth and Jovian emissions and mapping it into the sun and stars. And it continues again to have influence to the current time, beginning with Robert Wing Lee and collaborators in 1986, who did a blind survey. It's pretty much served as the basis for nearly every search for radio emission from exoplanets since. A recent example being Jake Turner and collaborators. And as Barnali and Jackie mentioned earlier today, it's likely the responsible mechanism for auroral emission from brown dwarfs, from early type magnetic stars, and even DME stars. Solar wind. Well, Jason walked you through some more recent results. In fact, the solar wind has been probed using extragalactic background sources for many years. Some very nice work by John Armstrong, Bill Coles, and others in 1990, who showed that angular broadening measurements that manifest as loss of spatial coherence as a function of baseline, shown in that middle panel in the middle set of figures there, can be used, in fact, to place constraints on solar wind turbulence. And what they found for the scales probed by the VLA in its A configuration was that the turbulence spectrum is far flatter than expected from Kolmogorov. And not only that, it's highly anisotropic. It's the density and homogeneities are drawn out along the magnetic field. To the one of the images is shown rightmost, showing the anisotropic scatter broadened image in the imaging domain. That particular paper was beginning to sort out some of the statistical optics phenomena in the observational domain, in particular, in this case, something called refractive scintillation as opposed to diffractive scintillation, which many of you are probably familiar with. Let me fast forward now to the Jansky VLA, which represented a significant step forward for our community. For the solar community, it wasn't so much sensitivity, but it was access to broadband performance with octave bandwidths available for single bands. And then, of course, these bands can be stitched together for continuous frequency coverage from 1 to 18 gigahertz in the case of solar observing, which is really fantastic because imaging spectroscopy has always been a hope and a dream for the solar community. An example of the kind of observations we can make is shown in the leftmost panel there with, in the early days of the JVLA, type 3 radio bursts, which are electron beams, which emit coherent plasma radiation. Shown at the bottom is the correlation of the type 3 radio emission with the hard X-ray emission, the same electrons streaming down in the opposite direction and splashing into the chromosphere. In the middle, you see the corresponding sources corresponding to those type 3s, and it looks like a little thunderstorm with lots of little flashes and winks. The red contours, by the way, are the hard X-ray emission. And in the rightmost panel, we sort of gather up that and integrate over the storm, and we see from red, which is high frequency, to blue, we have this envelope of trajectories tracing out the magnetic field above the energy release region. So really, really exciting to be imaging these type 3 trajectories directly. Another example from Bin Chen and collaborators are observations of a solar flare. Shown to the left is EUV observations from the Solar Dynamics Observatory showing the eruption of a flux rope, which drives a fast coronal mass ejection. In the middle panels, you see sort of the location of the flare on the limb, reoriented upright, and the diffuse blue stuff is continuum radio emission, the non-thermal gyrosynchrotron emission. But at the loop top, we see both a hard X-ray source and slightly above that, a radio source, which is coherent, and a dynamic spectrum, which I term a vector dynamic spectrum, because we're not integrating over the sun, we're sort of vector averaging and producing a dynamic spectrum as a function of time and frequency at that location. And we see that it's multitudes of stochastic radio spikes. And a very detailed analysis, which is spread out over 2 papers, concluded that these spikes were associated with the termination shock resulting from the magnetic reconnection outflow. So again, sort of fundamental insights into solar flare physics. Same applies to active regions. The continuous frequency coverage is a boon. Here is a sort of sweep from 1 to 8 gigahertz of a prominent bipolar active region. The snapshot I and V maps for 7 gigahertz are shown below, but it's very interesting to see the emission give way from thermal free absorption to gyroresonance absorption as we sweep to higher frequencies. And as mentioned by several previous talks, the gyroresonance absorption occurs at discrete harmonics of the gyro frequency, and so it allows us to measure quantitatively magnetic fields in the corona. So modeling efforts underway, as sort of shown to the right, are going to be modeling this in some detail. Solar wind, again, the JVLA represents a significant step forward. As Jason mentioned, it has much more sensitivity, which allows access to many more background sources. And so for both angular broadening sorts of observations, as illustrated on the right, on the left there, we have access to multitudes of background sources, which can probe the corona and the inner heliosphere, even granting that Parker will be getting into 10 solar radii. We're beginning to see new features in the structure function. The little inset there shows the structure function for a particular source. The image is shown in the inset to that. And you see that the structure function shows a break, which we associate with in the presence of an inner scale to the turbulent spectrum. Jason gave you a very nice talk on Faraday rotation measurements of the corona. He had a recent paper on multi-point measurements through a CME, in fact. This was work sort of coming from Steve Spangler and colleagues and students starting in the mid-noughts and continues to this day. And I hope that Jason conveyed the excitement surrounding the launch of Parker Solar Probe in August of 2018, which will be making in situ measurements of particles and fields, plus the white light whisper imaging progressively nearer the sun, using Venus to get closer and closer, ultimately down to 9.8 solar radii, but already to 13 solar radii starting spring of 2022. So I think it's important and critical that the JVLA provide global context to these measurements. Looking forward, well, NGVLA, of course, is yet another leap forward. I refer you to the science book that was edited by Eric Murphy and others. There's a solar system chapter, and there are 3 chapters dealing with sun and solar wind, which, if you're interested, I hope you refer to. Thank you all.
Thank you, Tim. Questions? Steve?
Steve and I have a question for Tim. Very nice talk, Tim. That was a real tour de force. I have a question about the gyrosynchrotron emission, the centimeter wavelength flares. Decades ago, there was kind of a part of the difficulty in interpreting those was comparison of the centimeter radio wave with the hard X-ray emission. And part of the reason before we got imaging was that it was clear that although you're dealing with the same electron population, were probably very different parts of the solar atmosphere producing those emissions. Could you summarize for us how much the VLA, as well as imaging satellites have helped clarify that?
Yeah, thanks, Stephen. Well, you're absolutely right that was one of the major preoccupations for many years, was the relationship between microwaves and hard X-rays, because the light curves looked extremely similar. And if you took the derivative of the soft X-rays, that also yielded a hard X-ray or microwave light curve. So yeah, I would say that the VLA, as I said, played a role in disentangling the spatial relationship between optical hard X-ray and microwave emission. It was certainly not the only player, though. I did not go into it because this was a VLA talk, but a very important instrument that came along in the early 1990s was the Nobayama radioheliograph, which operated at 17 and 34 gigahertz. And that, I think, sort of, that together with the Yoko, the Japanese mission Yoko, which had a dedicated hard X-ray telescope, sort of nailed down the details of the relationship between the non-thermal hard X-ray footpoint emission and the gyrosynchrotron coronal loop emission. Although one of the big surprises from Yoko is the hard X-ray loop top sources as well. But we can talk about this offline if you wish.
Thanks, Tim. We have to move on. Jackie's cat, if she would elaborate her question, perhaps you can answer that in the chat. The final talk in the solar system session is going to be given by Brian Butler, who's going to talk about observations of solar system objects with the NGVLA. Brian.
Thanks, Stephen. Okay, so I haven't been visiting the VLA for 40 years or observing, but close to. I first went there in 1988 as a grad student. Actually, it was before I had started as a grad student at Caltech. Interestingly, Luis Rodriguez was there the first time I visited the VLA in the fall of 1988. And it's nice to see so many familiar faces, even if it's only virtual. Hopefully sometime soon we can meet in person again. I also visited shortly after the AOC at that time, then the DSOC was built. If you recall, there were little hotel rooms on the bottom floor, on the first floor, and I actually stayed in one of those for almost a full month as a grad student. I don't think very many people ever stayed in those, but that was an interesting experience. Okay, so I'm going to tell you about solar system observations. IMCA and NGVLA specifically. IMCA has given a fantastic overview of the past observations. You're not going to see any equations, and I'm not even going to talk about science in this talk, because I'm going to assume that you know that if an observation can be done, there's interesting science behind it. And IMCA has covered a lot of it. I mean, any one of these topics could easily fill up the short 12 minutes that I have. As Tim just pointed out, we submitted a few chapters to the NGVLA science book. Some of those turned into a handful of decadal white papers, but IMCA, myself, Bob Salt, Ariel Moulet, Chris Mokel, Josh Tollefson, Catherine DeClear, Mark Gerwell, and Stephanie Milam wrote the sort of big chapter on an overview of solar system science with NGVLA. And then there was a bistatic radar chapter written by Marina Brozovic, myself, Jean-Luc Margot, Shantana Naidu, and Joe Lazio. So details are there. So I'm going to talk about each of these topics, I can only pick sort of one example. So, giant planets means mostly Jupiter, but also a little Neptune. terrestrial planets, icy bodies, radar. I won't talk about sun. It's different physics. You've already heard this morning lots of talks about it. Minor bodies, asteroids, comets, there's lots of interesting things that can be done. There's just not time, nor am I going to talk about extrasolar giant planets. So of course the power is of the NGVLA is in the sensitivity and resolution, both roughly 10 times what we can do with the current VLA, which is roughly 10 times, not in resolution, but in sensitivity, what we could do pre-upgrade. So solar system objects, sun and radar aside, are typically a few tens to a few hundreds of kelvins. So you want brightness, temperature, sensitivity, at least a Kelvin, and really quite a bit better, 1/10 of a Kelvin or 10 millikelvins. At 1 centimeter wavelength, which is Ka band now and will be band 5 for NGVLA, depending on the resolution, because of course that's a trade-off for brightness, temperature, sensitivity. NGVLA will have a brightness temperature sensitivity of order 1/10 of a Kelvin in of order 1 hour. And that's for not just using the compact configuration, that's using hundreds of kilometers baselines. For resolution, you know, aside from the sun and the moon, the objects in the solar system are typically a few tens of arc seconds, like Venus or Jupiter, to a few tens of milliarc seconds, Pluto or KBOs. And again, at 1 centimeter wavelength, depending on the baselines and tapering, the resolution will be a few milliarc seconds to a few hundred milliarc seconds. And that's just if you use the core. Okay, to put this in perspective, linear resolution on these bodies, again, 1 centimeter, and this is using about 300 kilometer baselines. On Mercury, 4.3 kilometers, Venus, about 2 kilometers, Mars, 3.5 kilometers, Jupiter and the Galilean satellites, 31 kilometers, Saturn and Titan, 58 kilometers, Uranus and its moons, 130 kilometers, Neptune and Triton, 210 kilometers, and Pluto Charon, which is at 36 AU, 260 kilometers. So on the right is a picture from New Horizons. The flyby was in 2015. Of course, we got spectacular images. And that resolution element in the lower left is about what we'll get with NGVLA, which is really just spectacular. So we'll have, you know, tens of pixels on Pluto. Okay, so giant planets, thermal emission from the atmosphere, synchrotron from the electrons trapped in the magnetospheres. They also have cyclotron emission, but it tends to be at lower frequencies than NGVLA is going to operate. Jupiter has had its synchrotron emission detected from Earth, but the others haven't, but they have been, detected by spacecraft. There's a long history. IMCA showed observations of the giant planets with the VLA. So, but before the VLA upgrade, we did just longitudinally averaged, or Bob Salt's deprojection technique, which he invented in the early 2000s. But they were fairly crude, the sensitivity. I mean, it's fantastic for the time, but what we can do now, good Lord, I'm going the wrong direction. What we can do now is, IMCA showed this projected on a globe and rotating, and this is just flattened out into a projection, is really spectacular. And this is a KU band image taken in 2013. I think this was, the data was taken then. And we've done many observations since, and NGVLA will do this with higher resolution and sensitivity, and it's just going to be fantastic. So Neptune, similar to Jupiter, we could do longitudinally smeared images, and even post upgrade, you can do Bob Salt's deprojection technique, but the sensitivity is a little less than what we like. But you do get a lot more sensitivity, so you can start to see more structures with post upgrade than you could before, like this equatorial brightening, which we could maybe see hints of before, but was really tough. We've done simulations of what NGVLA could do on Neptune, 30 gigahertz. So again, 1 centimeter, 2 hours observation, 1,000 kilometer baselines, which is a little longer than the current REV-D mid configuration. The max baselines are about 800, a little more than 800, I believe. But in any case, you can see the fantastic job that, so it's model, with the disk subtracted and no deconvolution, and then simulating all of the deconvolution and comparing with what VLA or ALMA can do. And that's in our chapter in the science book. So with NGVLA, the idea is like the VLA upgrade, going from longitudinally smeared to deprojected images, we'll do the same for Uranus and Neptune. Terrestrial planets, thermal emission from atmospheres and surfaces, and some line emission as well. Imke showed some of this. There's a long history of observing these bodies. I'm going to show you only some Venus possibilities. So we made a bunch of observations in the late 1990s and constructed a model. Venus had the Magellan spacecraft, which visited and had a radar and a radiometer on it in the early 1990s, early to mid. And that model is shown to the right, and you can see that at the higher frequencies, K-band, you see atmosphere basically. At the lower frequencies, C-band, you see surface mostly. So NGVLA at the lower frequencies will do a spectacular job of mapping the surface. So in band 2, which is roughly 4 centimeters, resolution will be maybe 30 milliarc seconds-ish, 20 kilometers at Venus, elongation, that's not even at conjunction. And you can easily resolve individual lava flows. So I've shown here, I had to blow up the resolution element of NGVLA by factor 4 because it was so tiny, it was just a little speck on the slide. Okay, icy bodies, satellites of Jupiter and Saturn, and Neptune for Triton. Pluto Charon, largest of the KBOs, have been observed with the VLA, but here we really are sensitivity and resolution starved, even post-upgrade. ALMA has been used recently, however, to make really nice images of the Galilean satellites and Pluto Charon. Titan's atmosphere is tough, though. You can't do it with ALMA because it's all atmospheric, so it's a similar problem to Venus, so they don't penetrate to the surface. So these are some observations we've done of Galilean satellites relatively recently with ALMA. On the left is Europa, on the right is Ganymede. The Europa is Sam Trumbo, Mike Brown, and myself, and Ganymede is Catherine DeClaire and collaborators, a group of us. So NGVLA will make images at similar resolution. The images on the left, the resolution is about 20 milliarc seconds. NGVLA is a little better than that at 1 centimeter and will probe deeper into the subsurfaces. Titan. So VLA has not made resolved images of the surface of Titan. The resolution just isn't there. But this is a projection of the Cassini radiometer, which mapped most of the surface at 2 centimeters. This is from Mike Jansen's work. And NGVLA will be able to do this. The resolution element is shown here. Just make spectacular images of Titan. I'm glossing over the potential imaging problems of trying to make images of bright distributed, relatively bright distributed sources with potentially millions of pixels across. By then, the imaging specialists will have solved that problem.
Few minutes, Brian.
Thanks, Stephen. I'm going to show a little bit about radar. So VLA has been used as a receiving telescope for bistatic radar. Goldstone is the transmitter to image Mercury, Venus, Mars, and the Galilean satellites, Saturn's rings, and detect Titan. It was used with Arecibo post-upgrade for some asteroid observations, but obviously that is not going to go forward. So these were observations we did of Mars in 1991. I'm going to skip the movie because there's another one. We repeated that experiment in 2003. Mars rotates rapidly enough. This is a configuration that you have to make about 10-minute snapshots before a pixel rotates through a resolution element. But you can see it makes a beautiful image of, you can see the polar cap, you can see the volcanoes. If you project that onto a cylindrical projection, it looks like this. And then Goldstone and NGVLA can do factor 10 better in resolution, plenty of sensitivity. Again, the resolution of the NGVLA is this little tiny dot. So it'll be about factor of 10 better. And Galilean satellites, we did this in 2000. Ganymede and Callisto, you can resolve them, but they're kind of blobby and it's only a few resolution elements across. NGVLA will be able to do this pretty well, but when you divide the received flux density into that many beams, you still have a bit of a sensitivity problem. But if we could get a new powerful planetary Ka-band transmitter at Green Bank, which is currently being investigated, that would make a fantastic instrument. Resolution factor 4 better, because you go from X-band to Ka-band, and sensitivity factor 16 better, because in the radar equation you have a 1/λ squared. Okay, so NGVLA will be a fantastic telescope for making images of giant planets, terrestrial planets. I didn't talk about water in the atmosphere of Mars, CO in the atmosphere of Venus, various things in the atmospheres of the Galilean satellites, things like that. Icy bodies will be able to image even Pluto with sort of tens of pixels. KBOs, the largest KBOs are sort of 50 milliarc seconds across. And radar, it will be a fantastic bistatic radar, even with Goldstone, but if a Ka-band transmitter, a few hundred kilowatts at least, is put on GBT, that will make a spectacular instrument. Okay, thank you.
Thanks, Brian. Questions for Brian? Steve. Oh, sorry, that wasn't a... Steve, you're wanting a question? You're muted if you are. No, okay.
Okay, well, anyway, since you invited me to, I've got a question. Well, one of the things I was thinking, Brian, is that you're showing these projected NGVLA images of like the Galilean satellites or Venus and so on. You must be putting a lot of emphasis on getting very short spacings in the NGVLA. Then otherwise all this extended structure is going to go down the hole in the UV plane. I mean, you couldn't do that with the present day VLA with the, what was it, 40:1 baseline ratio. So I assume that's something that's a major design consideration for you. Is that right?
Absolutely, yeah. So NGVLA is not reconfigurable, currently at least. And so, and it has an awful lot of antennas. So there are 114, in the current configuration design, there are 114 telescopes within a 4 kilometer, what we call the core. There's also a short baseline array of smaller antennas of order a half a dozen, maybe as many as twice that, a dozen, which will measure the really short spacings. So yes, that's a big consideration, and there's a lot of effort ongoing about how to combine observations that have such a distribution of baselines. You know, you've got the long baselines, 800 kilometers, but an awful lot of short baselines. So you tend to get a big skirt on the beam. You get a nice sort of inner beam, and then you get this big skirt on the beam. And so Viviana Rosero and Chris Carilli and others have been looking at this thing we call taperability, which is how you can weight the different antennas to get a nice beam out. So yeah, short spacing, that's one of the joys of NGVLA, is you get everything at once.
Any more questions? If not, thank you, Brian, and thanks all the speakers from this section. We're about 5 minutes over, Anna. Do you want to start at the 11:45 your time?
Yes, we will start the scheduled time, but before everyone disappears for the break, which will be 25 minutes or 23 minutes, I have a few announcements. I'll try to, and important ones, I try to go quickly through them. One moment. I'm sorry. First is that if you do remember, we actually mentioned it at some point that we are going to give everyone a celebratory gift back. And for that to happen, we do need some information from you. Let me do that. 1 second. I'm so sorry. am the host, and yet I am struggling here. I do apologize for that. Okay, let me share the screen. To provide us with the information that we do need, we will need you to go and fill in a questionnaire for us. For that, do go to your registered page or account that you have on this event. You will see this already registered sign. And over there, just put the email address that you registered with your confirmation number. Once you log in, you will see the additional pages that are available for the registered participants. So just click on the post-registration and survey. And over there, you will see this page with a link to the questionnaire. And it would be fantastic if everyone could do it, everyone who would like the celebratory gift. If you don't want, that's also totally fine. If you just fill it in, if you don't mind filling it in and telling us that you don't want, that would be great too. From the other things, and I will be reminding everyone about this throughout the conference. Regarding a few other ones is I will open the breakout rooms if anyone would like to have more kind of one-on-one or 3-on-3 or whatever small discussions, virtual coffee rooms for informal chats. I just wanted to also remind everyone to check the highlight poster talks that we have on our website. We have a wonderful 17 of them, or 18, and also there is a Slack VLA 40 workspace for which I was giving links throughout the session for all follow-up discussions, and we encourage everyone to go and talk further over there. And also there's a scrapbook for the VLA 40th birthday, and I put the link in a second. And I see that some people already started sharing, which is absolutely fantastic. But other than that, thank you all, and we have a break for 20 minutes now. Also, if for the next session, if anyone would like to check their slides, feel free to do it at any time throughout the break.
Yeah, I guess I'll do that now, Anna.
No worries, that's fine. I'll be here all the time.
See if I can just share. So
yeah.
Did that work?
Yeah, I could see the PowerPoint slideshow like on top, but that's it. I mean, I can see it in a presentation mode, but it does say PowerPoint slideshow at the top. I don't know if you wanted to do that.
That's interesting. Oh, because it's in a window.
Yeah.
Okay. I think I'm going to leave it that way, though, unless I can figure out how to get rid of that. I may just leave it that way. Okay, but at least it works. I can stop sharing. Great. Thank you.
No.
I'm going to try, Anna, if that's okay.
Sure, thanks. Okay, I actually should write down who is all good. Oh, you're first, David. Sorry, I just slept like 4.5 hours. I don't remember everything.
Are you seeing my
John, I do see. Yeah.
Okay.
Oh, okay, now your video is also better because it was very.
Yeah, I have my analog screen cover on before.
Oh, that's what it is. Okay. All good.
All right. I'll stop. Thanks.
Can I try as well?
Sure.
My Mac.
Yeah. Oh, it's here, you're John. Oh my goodness, I'm just trying to find mod.
Can you see?
Yep, all good. In a nice presentation mode.
Okay.
Pick you up. Okay, you're third.
Thank you.
And of course, we can hear you well.
All right, I'll try mine. This is Anuj. So let's see. All right, I hope you can see it. Cool.
Yeah.
Okay, fantastic. All right. Okay, that does it. Thank you very much.
No worries. And I'm also kind of like, we're sharing it now and everything. And just like I had a problem. So many windows open. So I know it might still happen. But no, it's always good.
All right, wonderful. Thank you, Anna. Thank you.
Hi, this is Guillem Anglada.
Hello.
Hi, I will try to share the talk, and I'm not sure what to do.
Oh, okay. You
Share
should-
screen, I
Yes,
think. no?
precisely.
Okay, so I will. So
Full screen should work.
but thanks. So can you see it well?
No,
No?
I think, well, we can see the window, but not in the full screen. I think what you may want to do maybe, because I think I remember with the PDF, if you first make like the presentation full screen, and only after that share the screen of that full one.
I think also by sharing the whole screen, I would try.
You might. You have only one
Yeah.
screen?
I share the whole screen and then make the presentation full screen. Can you see it
Yes.
now?
Yes, now it's
Okay.
perfect. Now just
So can you see the changing them?
Yeah.
And can you see my pointer?
Yes.
Okay, so thank you very much. So
No.
the trick is to share the whole screen, not just the window.
I'll
Where
make sure that I'm around paying attention at the very beginning of the talk, so I'll remind in case.
Thank you very much.
No worries at all.
Anna, can I try my presentation? This is Luis Rodriguez.
Yeah.
Let me see. Here we are. And then I have to say, is this okay?
Perfect.
Thank you very much.
Thank you. Also, I should also, you are perfectly done. Yvette, would you like to try your slides?
Yes, that's why I showed up a few minutes early. Let's give it a shot here. Mhm. It's funny, you do it a million times, but you're still like, okay, what exactly are the sequence of events here?
I totally understand. Um,
Okay. You see it?
Oh, yes, sorry. Yes, I do. In a good mode presentation.
Okay, I'm just gonna skip ahead. GIF is GIFing. Okay, cool. Well, I won't give it all away then, so.
No, thanks. Hi, Ylva. I was just checking. Amy said that you and Amy talked.
We did. Yeah, so we'll swap a bit midways.
I don't know whether Amy is around, but Amy could as well just start from Lewis.
That's right. Yeah, I think that'll work good.
Yeah. Perfect. I think, oh, we have like 3 minutes left. Right. Yeah, I love the images that people use for the Zoom backgrounds. Great. I just saw yours, Ylva, as well, and I think the others used them.
I should pick something suitable for this occasion.
Okay. I wonder whether Olga is online. Hi, Olga. Are you in front of the computer? Maybe?
Yeah.
Hi. Would you like to check just to make sure that your screen sharing works?
Just a second. Let me check which of them should be this. Yep. Can you see it?
Yeah. Oh, yes. Perfect. Now I can see it in the presentation mode, and it's nicely progressing.
Cool.
Perfect.
Great. Thanks. Yeah. Stop sharing.
Brilliant. And I think also Anna Carla. I don't see Anna online. Oh, she's the last one of the session, so maybe she'll come later. Okay. All right, so I'll leave it to you, Ylva and Amy. Do start whenever you see fit.
Yeah, I guess we'll wait until 11:45, but try to start right at that time. It's a very long session.
Yeah, I know. I'll start recording just on the dot then. Cool.
All right. It's 11:45. Welcome back, everybody. We're going to start the third session. We're going to move on from the solar system objects and get into exosolar planets and disks and star formation a little bit later on. So this is a long session. We have 10 talks. So just reminding the speakers to try to stick to your time. For the longer talks that are 20 minutes, I'll give a 5-minute warning. And for the shorter ones, I'll do a 2-minute warning. So the first one out is an invited talk by David Wilner from CFA, and he's going to tell us about new views of planet-forming disks, VLA to the NGVLA.
Okay, let's see if I can share my screen here. Hopefully you can see my talk.
Yeah.
Yes, okay. So I'm really honored to present this talk on protoplanetary disks at this VLA anniversary celebration. Disks are the inevitable outcome of gravitational collapse with angular momentum, and they've been an integral part of the theory of planet formation really for generations. And in this talk, I'll focus on the role that the VLAs played in advancing understanding of these protoplanetary disks, especially the evolution of dust grains in disks. And at the end, I'll briefly look towards the future with the NVLA. And in 20 minutes, I really can't be complete. So what I show will be selective. And I apologize to you if I don't show your favorite disk result. Okay, so, oops, my cursor there. So in addressing the origins of planetary systems, we are really fortunate that nature provides us not only with the fossil record of our solar system and planets in extrasolar planetary systems, but also large samples of young stars that are surrounded by disks of gas and dust where planets may be forming now that we can observe directly. And there are hundreds of these disks at a distance of about 150 parsecs, where the solar system subtends about 1 arcsecond, and many thousands out to a kiloparsec and beyond. So in the standard core accretion picture of planet formation, submicron interstellar grains in these disks collide and stick and grow to pebble sizes. And these pebbles grow to kilometer-sized planetesimals, much like Kuiper belt objects, which are leftover planetesimals in our solar system. And then these become large enough to interact with gravity and develop into the cores of giant planets and rocky planets. So the step from pebbles to planetesimals is a little bit problematic because they don't stick so easily. Oops, sorry. They don't stick easily. They're trying to get this video to run there. They're sort of too big for sticking chemically, and they're too small for sticking gravitationally. And this has been a problem for planet formation for a long time. Moreover, these pebbles experience significant gas drag in the disks, and that makes them rapidly migrate inward. And this radial drift is faster than the growth time scale, and the large drift velocities make collisions all destructive. And so this is a problem, and I'll return to this a little bit later in the talk. Okay, so why are radio observations relevant to disks at all? So here's the spectral energy distribution of TW Higher. That's the nearest pre-main sequence star surrounded by a gas-rich disk, and one of my favorites. And you can see that the stellar emission is roughly a black body that peaks in the optical, and then dust in the disk emits at a range of temperatures that spans from the infrared all the way out to the radio, here to at least a few centimeters. And here are the ALMA and VLA bands on top of the spectral energy distribution. So one thing that you can take away from this plot right away is that emission in the VLA bands is very faint. And it's not at all energetically significant. So there must be other reasons why these wavelengths are interesting to observe, and indeed there are. So first, at these long wavelengths, you avoid high dust opacities. So the emission provides a direct tracer of dust structure and also dust mass. Second, these long wavelengths are sensitive to large grains, comparable in size to the wavelength. So these are the interesting pebbles that are really the last observable link from the dust grains to planetesimals. And then, of course, out at these long wavelengths, the stars aren't very bright, so contrast with the star isn't a problem, unlike in the optical, say, looking at scattered light. And finally, interferometers like the VLA provide the high resolution needed to image them and the sensitivity to resolve them. So a potential complication at these long wavelengths is there also may be ionized gas, especially bipolar jets in the younger sources. And Luis Rodriguez is going to talk about those later today. So the first VLA observations of disks that I am aware of were actually done 40 years ago this week, though I don't think anyone at the time appreciated that they were observing disks. So these were observations of the Orion Nebula. And among the many radio objects that the VLA revealed in the Orion Nebula was a population of partially ionized globules. These are compact sources with very high emission measures. Churchwell et al. Proposed that these were in fact the result of photoevaporating disks around young stars in the nebula. This was a pretty bold interpretation at the time, since disks around young stars had not yet been seen directly. And a few years later, it was images like this from the Hubble Space Telescope that showed the disks directly in silhouette against the nebular background within their ionized cocoons, and confirmed this idea. And the modern view of the Orion Nebula is really impressive. So this is, again, a Hubble Space Telescope image zooming in on the trapezium. And you can see the many so-called proplyds for protoplanetary disks pointing back to the O-star Theta 1c. It's especially clear in the lower left-hand part of the picture. And here's a recent VLA image from Jan Forbrick, which shows all of these same sources in incredible detail and more. But this ionized gas and also the dark silhouette seen in the optical actually tell us very little about what's happening inside the disks themselves. And one needs to go to an optically thin tracer of disk material to do that. So the next major step for the VLA was the Q-band upgrade in the 1990s. So here's the long wavelength spectrum of HL tau, particularly famous disk source, showing at long wavelengths a partially thick free emission in the centimeter from a jet, and dust rising more steeply in the millimeter. And Luis Rodriguez, in particular, noted from the spectrum that if the VLA could be made to work at the shorter wavelength of 7 millimeters, then the emission would be dominated by dust, and it should be possible to image the disk material. So this motivation, among others, led to the installation of the new Q-band receivers, as well as the development of new ways of observing, including reference pointing and fast switching and some crude dynamic scheduling based on the weather. And I'll just say, as a young postdoc in the mid-1990s, I was really excited to be involved in this, and I am extremely grateful to all the NRAO staff and my collaborators who supported this effort. And here's an image of HL tau from that era, showing the resolved dust in the disk at scales below 100 AU. And when pushing down below 10 AU, one can see the high brightness jet, which is perpendicular to the disk. And this kind of data provided exciting new constraints on dust surface density at solar system scales that we didn't have from any other wavelength. Here's another example from this era showing two resolved 10 AU scale disks separated by about 45 AU in the L1551 system. So these disks are likely truncated by a tidal interaction, but they still have enough mass individually to form planetary systems. So images like this were important to establish the presence of disks and some basic properties. Now, the next issue that the VLA addressed, as I alluded to at the beginning, was grain growth, which is a key part of the planet formation process itself. So first, a a quick primer on spectral signatures of grain growth at these wavelengths. So the spectral shape of the dust mass opacity, which is kappa here, is diagnostic of the grain properties, and in particular, the maximum size. So this type of work was pioneered by Beckwith and Sargent 30 years ago in the millimeter, and later revisited by Bruce Drain, again, in the context of protoplanetary disks for a variety of grain materials, an example of which is shown here in the lower right. So basically, as grains grow, their emissivity drops and the mass opacity spectrum gets flatter. So the spectral dependence in this regime is often approximated by a power law with an index beta, with beta tending to 0 for larger and larger grains. And so at wavelengths where optical depths are low, beta essentially can be read off the spectrum because the flux is just proportional to the mass opacity times the surface density times the temperature. So this is a way to get at the grain properties. An issue is that if there is optically thick emission, that also looks like a pretty flat spectrum with a beta of 0. So it's necessary to resolve the disk emission to account for this. And there were quite a few studies with the VLA along these lines in the 2000s. Here's one example. It's a set of VLA 7mm resolved images of disks in torus. When combined with shorter wavelength photometry, gives spectral indices that are much flatter than interstellar grains, implying growth to millimeter sizes. Now with the Jansky VLA upgrade, it started to become possible to look within individual disks for spectral index variations. So that was the next step. So theory, as I sort of cartoon sketched at the beginning, predicts that grains will both grow to centimeter size and undergo radial drift. So this plot shows a calculation of grain size versus disk radius from the Bernstein et al. Models, where the takeaway is you can see that there's a radial size sorting with centimeter grains, which are towards the top, concentrated at small radii on the left. So what do the observations show? Well, from data from the Disks at EVLA project that was led by Claire Chandler in papers by Laura Perez and Marco Tazzari in particular, the data show that the dust disk extent decreases with increasing wavelength. So one way to see that, this trend, is in the visibilities as a function of baseline length. So the VLA wavelengths for all these different disks here on the right are in red, and the visibilities fall off more slowly than the shorter wavelengths, which are in blue and green. So the emission at the long wavelengths is more compact. So this trend effectively represents a radial gradient in the spectral index of the dust emission. And this implies a radial gradient of the maximum grain size. So this kind of analysis here shown for 3 disks shows that the value of this beta goes from something which is quite low at radii of a few tens of AU to something that approaches interstellar out at the outer reaches of where the disks are detectable at 100 AU. So this result is qualitatively consistent with the theory, except as I mentioned, that radial drift, in fact, should remove all of these pebbles on a very short timescale, much less than the stellar age. So there's still a problem, and the advent of ALMA actually is pointing perhaps to the solution of this problem. So prior to ALMA, and in this era with the VLA, the best dust images that we had of disks were basically like these. So this is HL Tau again from CARMA and TW Hydra from the SMA. And as I'm sure you've seen before with the ALMA long baselines, the emission in these disks and many others is resolved into a series of concentric rings with a wide range of widths and depths. In fact, HL Tau here shows at least 7 dark rings, and TW Hydra shows at least 4, and only one of those would actually be detected if it were at the distance of HL Tau. So the question is, what is the origin of this substructure and what role does it play? Okay, so one possibility is that these rings result from any number of fluid instabilities, like MHD zonal flows, which tend to get stretched out into rings. So these instabilities create local gas pressure bumps, gas pressure maxima, where the radial drift, instead of all being inward towards the star, actually converges. So within these regions, radial drift stops and the high velocity collisions don't happen. And the pebbles are concentrated in ways that can promote planetesimal growth. So another possibility is that the gaps are actually carved out by orbiting protoplanets. So these kinds of features have long been predicted in disks. And in one case, PDS-70, and I show that little image on the right, planets are actually seen directly in the central cavity in the infrared. And ALMA even sees circumplanetary dust associated with those planets that are seen in the infrared. So there are certainly situations where planets are clearing gaps and cavities. But if planets are responsible for these features, then the planetesimal formation must have happened somehow at an even earlier phase that we're just starting to investigate. And yet another sorry, 5 minutes?
5 minutes remaining, yeah.
Okay, and yet another possibility is that the rings reflect compositional changes. So as the pebbles drift inward, they can warm up and they can cross condensation fronts and release ices back into the gas phase, and this modifies their mass opacity and it changes the emission. So probably all of these mechanisms are operating and we need to sort them out. So the VLA is really helping here by providing resolved spectral index information at very high resolution. So here's the ALMA image and a deep high frequency VLA image of HL tau, both at 7 AU resolution. And the analysis here by Carrasco-Gonzalez shows first that the VLA emission is optically thin. It shows this overall radial spectral index gradient that we saw at lower resolution in lots of sources, but also that the gaps are generally associated with locally higher spectral indices. So this likely implies smaller grains in the gaps. And this is most consistent with clearing by planets, although some of the innermost features in HL tau may be coincident with these snow lines where ices evaporate. And we really don't know if these HL tau results are broadly applicable. And high resolution VLA images like this take tens of hours of observing time. So only a few more are even underway. Another aspect of the increased sensitivity of the Jansky VLA upgrade is you can observe a lot of sources at modest resolution. Here are some examples in Orion, and John Tobin is going to talk about this a bit later today. All right, so this takes us to the NGVLA. So one significant limitation of the VLA and ALMA is they can't resolve the terrestrial planet zone, the planet forming region within a few AU. This is also just generally completely opaque to ALMA, so adding longer baselines to ALMA is not really going to help that much. One really needs to go to lower frequencies. So to understand these innermost regions of disks, we need a facility that operates at wavelengths of 3 millimeters and longer to avoid the high opacities, that provides roughly milli-arc-second resolution to probe sub-AU scales at 150 parsecs where all these sources are located, and has sufficient sensitivity to image thermal dust emission at these scales. And that is the NGVLA. And ongoing simulation efforts, primarily from Luca Ricci's group, show that planet-disk interactions from Earth-like planets on Earth-like orbits in disks will be detectable with the NGVLA. And there's a nice poster talk on this topic that I urge you to look at. So this is the basis for one of the NGVLA key science goals, which will open up the parameter space of forming planets in both mass and semi-major axis within disks, which will overlap much better with studies of mature exoplanets. And because of the orbital timescales at these small radii are so short, just a few years, a truly incredible prospect is that we should be able to make movies of the dust orbiting at these in these zones. For example, this one is a simulation where there's a snapshot taken every month with a Jupiter mass planet, and it shows the proper motion of the orbiting dust features. And this kind of data will really help us sort out the mechanisms and what's going on. Okay, so just a few concluding remarks. Protoplanetary disks were not part of the original VLA science case, so maybe there's a lesson there. And ongoing upgrades provided access to thermal dust emission in a spectral region of lower opacity that is unique to the VLA, which gave us early constraints on disk structure at 10 AU scales, evidence for global grain growth through resolved images and shallow spectral indices, direct evidence for the radial drift of pebbles as predicted, and support at some level for gap clearing by planet disk interactions. And it will really be exciting because the NGVLA is going to uniquely extend imaging of dust emission into the terrestrial planet forming zone. And I'll stop there. Thanks.
Thank you very much for that nice talk. It sounds very interesting and tantalizing with the prospect of seeing time evolution for these disks. Questions?
I have a question. This is Luis Rodriguez. David, has rotation being observed in the plane of the sky for some of these disks? There seems to be enough data now to try that. Do you remember anything in that sense?
So I'm not aware of any results that show proper motion, but you're right that particularly with ALMA at the longest baselines, the orbital times are such that azimuthally asymmetric features do move on a time scale of, say, a graduate student, and it should be possible to detect such motions. In general, the features are not sharp, so it takes some significant motion to sort of beam scale motion to actually measure them, and that's still many years. There may be some new possibilities. For example, the circumplanetary disk in PDS-70, which is pretty sharp, although it's quite hard to image. If it really is a circumplanetary dust disk, then we should see it orbit, just as we see the planets in the infrared. Yeah, it's a great question. It's something that we should be able to do now, particularly with ALMA.
We have time for more questions.
Yeah, hi, this is Amy. David, how many of those disks of the star forming or the disk forming stars can we see with that resolution with NGVLA? Do you know what the estimate is? I guess it depends on the baselines too, but.
Right. Well, it depends on the baselines. It depends, on how long you're willing to observe, and it depends, quite strongly on exactly what resolution you need, because pushing the beam down to, say, 1.5 milliarc seconds or something really does cost you some signal to noise. But I guess the short answer is many disks have very bright inner regions. That's where the column densities are largest and the temperatures are highest. So to the extent that they're, still optically thin, but, not very thin, then you have, brightnesses of, 100K or some such. So just like with the solar system objects that Brian mentioned, if you can get a brightness temperature sensitivity of, 1 or a few K, then you can image those inner regions. So I'm optimistic, that it's at 150 parsecs, that it's, many tens, right? And, at 5 AU resolution, and one can go out to a kiloparsec, then it'll be many, many hundreds, more than there'll be observing time to do.
Great, thanks.
All right. If there are no further questions, thank you, David.
Great, thank you.
And I'll also remind people that you can use the chat to post questions in. Then we'll move on to next speaker was Yvette Sanders, also from the CFA. And she will talk about a pilot radio search for magnetic activity in directly imaged exoplanets. And I'll give a 2-minute warning.
All right, thanks. Do you see my screen?
Yes.
Okay, then. All right, hello everyone. Thanks very much for the opportunity to speak here today. As I said, my name is Yvette Sendis. I'm a postdoc at the CFA, and I'm normally looking for transient radio signals that are much, much further away from us, millions of light years away, like TDEs. So check out my pre-recorded talk. I'm going to take a sec to plug that. But today I'm going to talk to you guys about a paper I recently submitted, which was really fun for me because this is the first time I actually looked at sources within the galaxy where some of the light was actually as old as me and things like that. So that was pretty fun and exciting. And yeah, so I'm going to tell you guys a bit about this search for magnetic activity in directly imaged exoplanets. So to begin, radio emission from exoplanets is a key to understanding a lot of things about exoplanets. So for those who are not familiar, we're interested in detecting this radio emission for many reasons, but in large part, it's because it's a key to understanding things relating to the magnetic fields of these exoplanets. So you could learn if you detected radio emission from an exoplanet, aspects such as the interior of the planets, star-planet interactions, anything, so things about stellar wind interactions potentially, and even down to things like atmospheric escape. So if you have a magnetic field or not, how much of the atmosphere is being stripped away from an exoplanet, you could potentially learn about that. And you could even answer questions about habitability. Think about how important it is on Earth that we have our magnetic field to enjoy life on Earth and not be affected by stellar flares, things like that. So there's a lot about magnetic fields that we really don't understand yet around these exoplanets that would be really good to know. To date, most of the work, when you think about radio emission from exoplanets, what people have been searching for has been taking systems that we have in the solar system that we heard about earlier today, like Jupiter, and scaling them up to exoplanet distances. What this often means is you are usually looking more in the megahertz regime because that's where Jupiter is at its brightest, and then it, decreases fairly steeply when it comes to its emission strength when you go up to gigahertz, when you think about its maser emission. So to date, we've had a few tentative detections in the megahertz regime for exoplanets. So most recently, in my personal, Turner et al. Came out a few months ago with a tentative detection from Tau Boötis using the LOFAR radio telescope in the Netherlands. And there was also Ventham et al. Also using LOFAR. On the right here, I'm showing you guys just really quickly, they basically had a roughly 6 sigma detection here at the top, but if you did the integrated spectrum, you get to an 8.6 sigma detection. So that's of course very interesting around Tau Boötis, this is around 20 to 30 megahertz. But it's not conclusive yet because, the resolution on LOFAR is 45 arc seconds. So that's not very detailed. So there's questions about, how can you distinguish between the star and the planet? Jackie talked about this a bit earlier today, for example, and I think some other people have as well. So there's still work to be done there. If we think about exoplanet searches with the VLA, especially for published detection so far with the VLA, because if you go through the archive, there's a lot of unpublished observations looking for this sort of emission, but for published, you mainly see it in P-band and L-band, as I said, looking at solar system analogs, scaling upwards. So Tim Bastian and Joe Lazio have definitely done a lot of work in this in the past, but nothing detected yet with the VLA either. So one thing though that has been more fruitful with the VLA and is worth considering is emission from ultra-cool dwarfs. So M7 and higher, so L dwarfs, P dwarfs, T dwarfs, these have been detected flaring at gigahertz frequencies, also quiescent emission at gigahertz frequencies, mainly in C-band where the VLA is most sensitive. So this was first discovered with the VLA by some REU summer students looking at brown dwarfs. Nobody was really expecting it. We still don't fully understand what's causing this emission. It does appear to be inherent to the brown dwarf. It's not because of a stellar interaction or something like that. And also, similar to what you see in Aurora, things like that. And it does seem about 7 to 10% of UCDs have some sort of emission that you will see with them. They'll also be flaring. So sometimes, you can be looking, you'll see a flare. Sometimes you're not looking, or you're looking, you don't see a flare. So there's a lot of studies that have been done very successfully in the VLA over the years about UCDs. But then there's, of course, this question of how low does this emission go? We see it as far down as T-dwarfs, which have similar effective temperature and somewhat similar size to the most massive exoplanets we have. So does this gigahertz emission, is it possible to maybe look for it with the VLA? So what we did in our study is we targeted directly imaged exoplanets. So if you look into the NASA exoplanet database, which lists, there's over 4,000 confirmed exoplanets today, you can do some simple cuts just to say, okay, everything within 50 parsecs that's been directly imaged that you can see from the VLA, so not too far south. And we also said a limit of 13 Jupiter masses. So that's kind of the conventional cutoff between exoplanet and brown dwarf, just so we make sure we're not looking at those. Let's point the VLA at these systems and see what we see, because if they're close enough, the angular separation, if you're looking in A configuration with the beam width, is actually in C-band good enough that you can resolve or distinguish between the exoplanet and the star. So this is just an example of what one of these directly imaged exoplanets looks like in optical. This is 51 Ari over time, over a few years. You can see it orbiting and you can see it. And you can have similar resolution with the VLA if you look. What we had was a sample that was 5 systems with 8 exoplanets total. And we had 2 archival observations that we found in the VLA database, and 3 systems that hadn't been looked at before. So we targeted them with 3-hour observations. So in case there's any flaring or some change over time, we would also have a long enough sample observation that we could take a look at that. So first of all, I should say, we still have not detected exoplanets in the gigahertz, but we did learn a lot. So I'm going to tell you guys a bit about this. So just some examples of what we were finding when we were looking at this data. So we first had emission detected for, there was a system called GeoPSC. We detected emission at the star. It's this figure here on the left. And the planet was sufficiently distant from this faint emission that we detected that you could confirm that there was no emission coming from the exoplanet itself. Similar, there was a system, Ross 458AB, detected quite fairly brightly. And it's a known flare star, but it's 102 arc seconds separation from the exoplanet. Just for the record, the directly imaged, there was about 1,000 AU from the parent star, if you're wondering how the separation can be so big. It's also fairly close to us. So once again, no detection, but you can very easily see if you're using this method of, A configuration and 6 gigahertz, okay, do we have emission here where it's not and what it's associated with? A little more complicated was we had an interesting source around 51 Ari. So this is the same system I was showing you guys earlier with the GIF, where it was the optical observations of that directly imaged exoplanet going around its star. And what we see here is when we were looking in 2018, when we had these first observations, there was a candidate source that was about 4 arc seconds from the star, potentially associated with the system, because it was, varying fairly largely in its brightness over the 3-hour observation. There was no directly imaged exoplanet there, but could there be a candidate? It's also a 5th magnitude star, so you can't just look in optical to see if there's maybe a little galaxy there or something like that. We did follow-up observations and used astrometry from Gaia. The system should have moved 200 something milliarc seconds in about 3 years. The candidate moved less than 20, so the conclusion is this was a background AGN. But still, as I said, it's very exciting for me because I usually look much further with the VLA to actually do things like astrometry. With our results, though, we can take them and we can compare them to the UCDs that have currently been detected and not detected. So what we have here on this plot is on the x-axis, we have spectral type. So M dwarf all the way down to exoplanet size. You do this a lot when you're talking about UCDs because we don't have precise masses for all of them. So spectral type is a rough idea of the mass. And then of course we have the luminosity here on the y-axis. And what we're seeing here is the yellow are detections of UCDs, where the square is the quiescent emission that you might detect in the system. The blue or the circle, yellow circle is if you have flaring emission. The line is just to connect the two. So that's the same object flaring, because as you can see, some things have only been detected in flares. It's a little complicated. And then we have upper limits both for UCDs and for this work. And what you can see here is we are comparable to the flares that you are seeing from UCDs in the limits that we're getting to from our exoplanet study. Another way you can look at this is for the detected UCDs, you often have the masses for those. So we can compare mass and luminosity, and also for published upper limits on exoplanets that have been so far looked at. So what we see here is the red are the exoplanets in this work. The blue are the UCDs, and then the green here are previous works, what I could find in the literature. If I'm missing something, let me know. This is only for gigahertz emission, I should emphasize, not including anything from the megahertz. And what we see here is most of these green previous observations are actually from the historic VLA, not the current VLA. I didn't find too much that was using the current VLA. That was also, you know, comparable and good constraints and luminosity. This one observation that's down here was by a Spanish group, Guerrero et al. In 2018. They were looking for UCD emission in general, looked at one of these directly imaged exoplanet systems. So that's where that observation comes from. And what you can see here that's very interesting is the mass constraints here are starting to overlap, where you're going from the smallest UCDs that we've seen flares from and the biggest exoplanets. So we're in this very interesting regime where you're starting to see overlaps. You can see we are, you know, for systems where this one had a lot of RFI, it was an archival observation, but if you go down here, we're starting to get to really low limits where you can even start ruling out quiescent emission, not just the flaring emission from these exoplanets on the level that would be similar to UCDs.
2 minutes.
Okay, thank you. So just to, you know, think looking ahead, these results are definitely encouraging. But it's also clear that we do need to expand the sample if you want to know if does this sort of emission exist or not. And the interesting thing is, because we know roughly how often UCDs flare, you only need a few dozen exoplanets really to know, and good observations to similar limits of just a few hours, to say for sure, does this emission exist or does this emission not exist? And the other thing that's very nice is, you know, people have definitely looked in the past with the VLA systems, but there's just so many exoplanets now. If you look within 20 parsecs of Earth, what the VLA can see, which is roughly what this plot here is showing, you have over 60 systems with over 100 exoplanets, which you could see with the VLA and get similar luminosities to what I just showed you from just a short observation. So there are, of course, difficulties. So of the stars that I have in this plot, they're pretty much all either radio velocity or transient detections. So then that is not as simple as, okay, let's have our nice directly imaged exoplanet, take a look, things like that. Though you could do, because they are just so many of them are so near, using Gaia astrometry, you probably could do VLBI to distinguish between the star and the planet. So there's some potential hope there that you would hopefully, if you made an observation, did some follow-up, you'd be able to figure this out. It sounds like a lot of other people are talking about this as well, how to do these follow-up observations to confirm if emission was from an exoplanet or from a star. So it would be cool to talk about that later. But yeah, of course, any stellar emission is also, of course, valuable, because that would tell you a bit about any sort of space weather an exoplanet would have. Anyway, let's hope the TAC agrees with me on that particular point. But anyway, just to wrap up here, we conducted a survey of directly imaged exoplanets within 50 parsecs from Earth. We didn't detect any emission, but it's promising in terms of what you could potentially do with further observations from the VLA looking for this sort of emission. NGVLA will definitely determine if this emission exists. Also, it's a VLA conference, but there's quite a few systems still in the Southern Hemisphere that, you know, Meerkat, ASCAP, SKA, all those guys, you could probably get a bigger directly imaged exoplanet sample using those. And it would be really cool if we saw this emission, and then we know a lot more about planetary magnetic fields, habitability, all sorts of interesting questions about exoplanets. So thank you very much.
Thank you. Let's see, questions. There's a comment in the chat from Miguel Perez Torres saying that they have found evidence for 1.7 gigahertz radio emission due to star-planet interaction in the Proxima Centauri using the compact array.
Okay, great. I'll have to look into that.
So I'll ask one. You have the quiescent emission.
Mm-hmm.
Is that expected to be at a very stable level, or would there be any benefits of like monitoring of that?
So I don't think it's necessarily like that well predictable, or that predictable is kind of the answer. Like if you see the quiescent emission, as I said, the flares seem to be a bit more random. I don't think there's too much periodicity with the UCD flaring emission that we see. So I do see one hand.
I see a hand, Gregory.
Yes. So, quick question with regards to the idea of follow-up, as opposed to just following up sources where we know there are exoplanets. Is there any value in following up anything else where we're detecting flare emission with stars and trying to see if that flare emission is actually spatially located with the star, if we can see a slight bit of a positional separation?
Yeah, sure. That's a good question. I think the issue there, so one of the LOFAR papers that I mentioned, which is actually the first one that was published, they had something similar. They were detecting flare emission. They said, okay, it looks like this flaring emission should be from an exoplanet in this orbit. Optical people went and checked. There's no evidence of an exoplanet in that orbit. So you can do it, but in terms of where do you set the limits for your fishing expedition and things, how do you convince the TAC? I mean, that's kind of the thing. You could probably spend a lot of time in this, but you really have to make a good, compelling case that you have a good chance of seeing something. So if you know there's an exoplanet, you probably have a slightly better chance.
It might be interesting in the age of all the large surveys where this stuff will be coming commensally, then you don't have to convince the TAC.
Oh, that's for sure. And I think that's really the advantage to some of these low frequency all sky surveys is, if you have very bright flaring emission, you can see it. But in gigahertz, it's a bit hard. It's hard to get, say, VLAS to get to the limits that you need with the VLAS observations. Maybe once they integrate them all, it might be worth looking.
There is one last question in the chat before we move on. Jackie, and of course, there come a couple of more, just as I said that. But Jackie is asking whether it's worth expanding to terrestrial planets or mainly stay focused on directly imaged large planets.
Well, so yeah, it's probably worth expanding the sample, because if you don't really know how far this emission is going, then, who's to say? It's just, there aren't, say directly imaged exoplanets, as I said, you have some advantages to them. They're unfortunately a very limited sample. So yeah, in the future, you probably need to go out to more of the terrestrial sized planets as well and see if this emission is possible there.
Right, thank you. There are a couple of more questions in the chat, but I'll just ask you to look at them and answer them in the chat, and we'll move on to the next speaker. Thank you very much for that.
Yep, sure thing.
The next speaker is Marta de Simon from University of Grenoble, who is going to present on VLA and hot corinos.
Yes, I'm showing the screen. Wait. Okay, can you see it?
Yes. Yeah, now it's in full screen mode.
Cool. Okay. So hello everybody, I am Marta De Simone and I'm a PhD student at the University of Grenoble-Alpes in France. And first of all, I would like to thank the organizer for giving me the opportunity to present my work with the VLA in this very interesting conference. In particular, today I would like to bring you with me in a new intriguing journey on VLA and hot corinos. First of all, let's start with a consideration on our neighborhood. So far, more than 4,000 exoplanets have been discovered, and they are part of a large variety of planetary systems that are actually different from each other and from our solar system. Definitely, in order to understand the origin of such diversity, it is crucial to characterize the early stages of the formation of a planetary system. And to do that, we use a powerful observational diagnostic tool that is the chemical composition. Indeed, the chemical complexity starts since the beginning of the star formation process. Here we have a sketch that show you that the star formation process starts with a pre-collapse clamp that collapse, forming a protostellar core, then a protoplanetary disks up to a stellar system. And the chemical complexity actually is inherited from the first stages towards the end. So the early stages are really important, and we will focus on these ones. The prestellar phase, where the dust grains are covered by ice mantles, and in these mantles starts the formation of hydrogenated species. While in the right after the collapse, the central objects start to hit the surroundings and to sublimate this ice mantle, releasing these species into the gas phase, where we can see them. Indeed, these regions are compact, hot, and dense, and they are called hot corinos. And given that the chemistry is dominated by the ice mantle sublimation, they are rich in molecules, in particular in interstellar complex organic molecules. Already at this stage, at the stage of hot corinos, we can see a chemical differentiation. Indeed, not every protostars possess a hot corino region, and only less than 20 hot corinos are discovered so far using millimeter facilities, as the Iron one and ALMA. Moreover, more of them are actually binary systems that shows different millimeter spectra. Here we have two examples, IRAS-4A, where we have the two binary, where the hot corino is detected only in one of the two, while in IRAS-16293, we have hot corino in both companions. What is the origin of this chemical differentiation? We can try to investigate two possible explanations. The first one is an observational bias due to the fact that the dust can be optically thick at millimeters and at millimeter wavelengths and absorb the lines. While the other one is that the chemical differentiation observed is actually intrinsic and real and can be a consequence of the different composition of the grain mantles formed in the prestellar phase. In the first case, what we have is that the protostar at the center is embedded in the thick cloud that actually absorbed the emission of the molecules that are behind. If we get rid of the dust contribution, this emission can pop up and shows a forest of molecules. In the other case, in the case of the grain mantles, to investigate, it's not so easy to investigate the composition. Indeed, from infrared observation, we know that the major component of the icy mantles are the species that I show here: water, CO, CO2, CH4, ammonia, and methanol. But these observations are very difficult to obtain in low mass protostars, as we need bright air continuum, and they are almost impossible in prestellar core. So the idea is to go to see these species when they are released in gas phase in the protostellar phase, where there is the hot corino region. So when these species are released, we can actually observe them. And in particular, the critical tracers are ammonia and methanol, as water is observational very difficult due to the terrestrial atmosphere. CO is optically thick and confused with the environment, and CO2 and CH4 do not have a permanent dipole moment, so we cannot observe at millimeter radio wavelengths. So to investigate both possibility, actually the centimeter observation are the key. As in this spectral band, we have that the dust is slightly optically thin. We can observe both methanol and ammonia and several lines. And With interferometers, we can go to planet formation scales, so below 50-100 AU. And in this perspective, the VLA is actually the best and the only facilities to investigate that for its frequency coverage, sensitivity, and high angular resolution. I will show you now a pilot project that we did in this, going to that direction. We observed methanol and ammonia towards IRAS-4A. IRAS-4A, as I told you before, is a binary system that a millimeter wavelength shows a very different spectra. Indeed, the source with the brightest continuum emission actually do not show any sign of molecule emission, while the 4A2, that is the weakest, has a hot Corino region. Indeed, the relative abundance of the species in the two protostars are of the order of 20-100, are estimated to be. So there could be several possibilities of why IRAS-4A1 does not show a hot Corino, and they can bring to the two outcomes, or they are really chemically different, or they are not. We investigated this first possibility that was to understand how much the dust was contributing. And actually, we observed methanol with the VLA observations towards the source, and we detected several methanol lines towards the two sources. We could disentangle the emission from the two sources, and we could perform a detailed analysis in order to derive the gas properties of both protostars and the column density of methanol. We found high density, high temperature, compact size, and we could confirm that both protostars have actually a hot Corino. So we compared the centimeter observation with millimeter ones, and we could derive the dust opacity at millimeter wavelengths, and we could confirm that actually the dust was responsible in obscuring the hot Corino towards IRAS-4A1. These raise also a warning that ICOMS abundances are derived at millimeter wavelengths can be underestimated. On the other hand, we investigated also the ice mantle history of these two objects. As I told you before, the ammonia and methanol are the critical tracers for the grain composition, and they are relative, and they are grain surface products, so they are formed on the surface of the grains. So the relative abundance depends on the pre-collapse clamp temperature and density. Here there is a plot, is just an example of an astrochemical model that follow the ammonia over methanol abundance ratio with respect to time at different gas pre-collapse clamp density and temperature. In few words, an old grain mantle or a colder or a denser grain mantle will be richer in methanol and form, and methanol is the precursor of many other more complex molecules. So with this observation, as I showed you here we have on the right the methanol that I showed you before. Here I show you all the transition we got, and actually we have also ammonia. Ammonia that we have 5 transition with a large upper level energy. So we have for the first time the detection of a high energy transition of ammonia in this source, and we can actually disentangle the two protostars, and we see also here a compact emission. As we did for methanol, we could derive the gas properties for both, also for ammonia, and we could derive an abundance ratio, given that they were tracing the same gas. So we could derive for both protostars these values. We have upper limit, as the methanol was unfortunately very optically thick in these two protostars, so we could estimate only a lower limit on the column density. But that was giving us actually some interesting results, because we compared our observation with astrochemical model predictions. We have here thanks. We have here the ammonia over methanol ratio versus time is the same I showed you before, but more detailed. And we have here the curves at different density of the pre-collapse clamp with different line shape, and at different colors. The different colors correspond to different temperatures. And the orange and the blue band represent the observation. So the ammonia over methanol ratio derives towards 4A1 in orange and towards 4A2 in blue. What we can see is that we can actually constrain the ice mantle history for these sources, but in particular for 4A1 we can only constrain the temperature. So we find values below 12 Kelvin. But for 4A2 we can actually say more. We can constrain both temperature, finding values below 8 Kelvin, the density of 10 to the 5 centimeters to -3, and actually also the collapse time around 10 to the 6. So these results clearly show how powerful is this method in retrieving the history of hot Coriolis rain mantles at planet formation scales, and how crucial are the VLA observation in this perspective. Just to summarize, I hope I convinced you that this centimeter observation are really crucial to study the hot Coriolis, and considering that the chemical complexity will be inherited in later stages. But so far we investigated only one case, so we need more sources. We would like to compare sources of different star-forming regions in different environments. And of course, to characterize the whole chemical complexity, we need to complement centimeter and millimeter observations. But of course, we look forward for NGVLA for its powerful sensitivity, high resolution that will allow us to go to resolve closer binary system and objects that are also farther away. So I thank you, and I'm happy to answer your questions.
Thank you, Marta. Questions? Is there a molecule or a transition that you think would be interesting to observe that you can't do at the moment, but that you might be able to do with NGVLA with better sensitivity?
Yeah, I think that already now with these observations, with these observations, we tried to observe other more complex molecules, more complex than methanol, for example, formamide, glycolaldehyde, that are prebiotic molecules, but we didn't have enough sensitivity to do that. So if we have with NGVLA, the sensitivity will be higher. So I really hope that it can help on that. So we can also say more about the chemical complexity and not stopping on the methanol. That so far we can do only with millimeter observation to have a full census of the molecular complexity in these sources.
Thank you. This is very interesting. Anna is reminding us that we can put questions in the Slack channels as well, and they won't disappear from there. Okay, I think in the interest of time, I'd like to move on to the next speaker. So thank you again, Marta.
Thank you.
And our next speaker is Anuj Sarma from DePaul University, who is going to talk about the Zeeman effect and methanomersers.
All right, thank you. So greetings from a nice warm day in the Chicago area. Not something you can say all the time. I'll be talking to you today about the Zeeman effect in class 1 methanol masers. Now, ultimately, of course, this is a story of star formation. And so that's where I'd like to start. We know that stars form in these sub-parsec scale cores deep inside giant molecular clouds, when gravity has triumphed over any opposing agents like the internal pressure, and one of those ands could be the magnetic field. And indeed, 40 years ago, the magnetic field was thought to play the major role in opposing gravity. But then in the 1990s, turbulence started to cut in to the action. Although now we have evolved to a more sophisticated role for the magnetic field, where not only is it a regulator of star formation in concert with turbulence in many cases, but is also a major driver of these different stages of star formation as it channels mass and momentum into disks and outflows. So magnetic fields, in that sense, therefore, are known to play an important role in the star formation process. Although, of course, what the exact nature of that role is remains a matter of doubt or debate. And some of it is theory, but a lot of it is the scarcity of observations, because polarization observations aren't the easiest observation to undertake. And so certainly a lot more needs to be done in this field. But today, I'm going to be talking about one particular tracer of the magnetic field in a star-forming region, and that is a maser. Masers, of course, have a role beyond just tracing magnetic fields. They are compact sources, they are bright sources, and as a result, they offer a very nice tracer of all the activity that is going on in these star-forming regions at high angular resolution. Now, just to remind everyone, a maser, of course, is just the same as a laser, except it's at microwave wavelengths, radio wavelengths. So the idea here is you need three things. You need population inversion, you need stimulated emission, and then you need amplification. So the first part, population inversion, is achieved either by collisional processes or radiative processes that pump molecules into an upper level from where they settle into the upper level of the transition, a kind of metastable state. So you get the inversion in the population. And then along comes Einstein's photon for stimulated emission. And for each incoming photon, you get two outgoing photons, which are, of course, gives you this nice emission, nice in-phase emission. And then, of course, the process continues and you set up a chain. So 2 becomes 4, 4 becomes 8, and so on. Now, if you had a laser, maybe a laser pointer that we would be holding in our hands if this were an in-person meeting today, then, of course, the way you achieve this is by bouncing the signal back and forth between two mirrors. However, in the interstellar medium, the path length itself serves as the amplifying path. And so as it traverses through these velocity coherent paths, the maser action develops. And eventually, of course, we look at the signal on the Earth. So the particular kind of masers that I'll be talking about today are class 1 methanol masers, which are known to form in outflows where shocks provide the collisional pumping that produces the population inversion. Their cousins, class 2 methanol masers, of which I will not be talking today, are formed in the disks closer to the protostar by radiative transitions, which provide the pumping. The radiation provides the pumping. For class 1, the collisions provide the pumping. Here is a nice picture of these class 1 methanol masers from the master's thesis recently defended successfully by Nicole Wenner, my student at DePaul. And in it, this is, of course, was originally also was seen by Araya et al. In 2009. And Nicole's thesis was on looking at variability of these masers. But you can see nicely how these class 1 methanol masers, of which Nicole found 57 in this region, very nicely trace the bow shocks from these outflows. And this will be one of the regions that we'll be looking at for the Zeeman effect. The Zeeman effect, of course, remains the most direct method for measuring magnetic field strengths in the interstellar medium. The idea is if you don't have a magnetic field, the two levels in question will split in the presence of a magnetic field, and therefore you can leverage the opposite polarizations in these lines, and that's in particular the difference between the right and the left circular polarization, which is formally called the Stokes V signal, and which, because of the slight separation between these lines, typically ends up with this well-known S shape, and you can use that to measure the magnetic field. So we are engaged in a long-term effort to measure magnetic fields with the VLA using the Zeeman effect in a large number of tracers in a variety of star-forming regions. This effort, of course, precedes my entry into the field in 1996, so it had gone on for a long time before then. I hope it'll go on for a long time after me, but right now, the methanol maser effort is directed for this specific talk, the efforts with Emmanuel Momjian of NRAO and myself. And over the years, we have looked at a number of these methanol maser Zeeman effects. So let me highlight, given the time, let me highlight only a few of our results. The first one would be the discovery in the 44 gigahertz class 1 maser. This actually, the discovery in the 36 gigahertz predates this, but I've given the choice of things to focus on, I figured I'd focus on this. This is a relatively simple region. There are a few maser spots, but only one very prominent one. And that's what we targeted for the Zeeman effect. And again, here you are seeing the sum of the right and left circular polarizations, the so-called Stokes I, and the difference. And the dark black line here is essentially the derivative of the Stokes I, which has been then scaled by the fitted magnetic field. You'll notice that I'm expressing these in hertz because it's a product of Z and the line of sight magnetic field. That's because for a long time, the Z factor was not known. Langhar published Z factors some years ago, but we have preferred to stay in this. But for the purposes of this talk, Z is of the order of 1 hertz per milligauss for the 44 gigahertz line. And so any number you see in hertz is also roughly the magnetic field. So the magnetic field as revealed here in OMC2 is about 20 milligauss. What's interesting about this source is that 2 years later, we looked at it again, and the maser had gone up in intensity after 2 years. So this is the earlier observation in 2009. This is the later observation in 2011. So the maser had gone up by about 50 Jansky per beam here. However, the field remained roughly the same, 20 milligauss. And this was at that time, until that time, around that time, there was always the question of whether these maser observations were looking at fields that really were peculiar to the maser regions or whether they had some connection to the large scale fields. And this showed to us that they did have connections to the larger scale field. They were tracking the larger scale field. The next region is DR21OH, which is in the Cygnus X region. And you see this very nice, rich picture here with hot molecular gas, cold molecular gas. But we're interested particularly in this filamentary structure, this particular filament here, which is the DR21 ridge, which is shown as an IRAM in the contours here. And in particular, we'll focus in on this very young high mass star forming region, DR21OH, where, as I showed you, from Nicole's thesis, this time without the lines, because we're going to focus in on these two masers. This one in 2009 was the strongest maser, and this one was the second strongest maser. But by the time we observed it, this became the second strongest, and this became the strongest, which actually is the topic of Nicole's thesis, an upcoming paper. Now, We found Zeeman detection here. We did not find a Zeeman detection in this maser. And for this maser, we fitted with two components. The Zeeman detection comes primarily from this blue component, and it's of the order of about 55 milligauss. Thank you. So again, in the order of tens of milligauss. Another one, DR21 West, if you go a little bit down from DR21OH, this region over here, and around this part in the near IR image, you see the outflow in shocked molecular hydrogen. So this is the part we're looking at. The masers show up in this kind of pattern, and you see masers again of the order of about 20, 25 milligauss as traced by this. Here we have two detections in these two inch stuff. So again, of the order of 15 to 25 milligauss. Finally, the most recent one, which is a new discovery in a different line, the 25 gigahertz line, where from the 2009 data taken in the deconfiguration of the VLA, so it's a combination of these two spots, we have about, this is higher now, about 160 milligauss, whereas here we have same data, but with the C configuration in here, same component though, and the same magnetic field. So the question is, what have we learned here? So far, we have Zeeman detections in 3 class 1 methanol maser lines, and the fields traced by these are of the order of tens of milligauss, although 25 gigahertz seems to be tracing a slightly higher field. If we assume that the shocks amplify the field in proportion to the density, then this ratio stands true. So knowing the post-shock field through this Zeeman measurement, and these are in post-shock densities of the order of 10 to the power 6 per centimeter cubed. And knowing the pre-shock density, we can measure the pre-shock field. This is remarkable because at this resolution, there are very few such results. So to end, let me state my wish list here, which is the replacement for future work. So we would like Zeeman effect measurements in class 1 and class 2 methanol maser lines in lots of places, including specifically weaker masers with the NGVLA. It'd be nice to get other lines, specifically H2O masers, so that we eventually have a vast repository of Zeeman effect measurements, both thermal and non-thermal masers, and are able to understand the role of magnetic fields in star formation. With that, I'd like to thank you for your attention, and particularly the NRAO and the organizing committee for giving me this opportunity to give this talk. Thank you very much.
Thank you, Anuj. Let's see if we have questions. Good. I did notice, I looked at, yeah, go ahead, who was talking?
Thank you. Then is it clear if you are dealing with a collisional pumping or a radiating pumping?
I think as far as the current understanding is of class 1 methanol masers, it is of the ones we're looking at, that we are certainly looking at collisional pumping. Now, of course, in the field of, and I don't know if enough work has been done to say that, you know, as firmly as possible, because there have been recent instances where H2O masers, for example, which for a long time were thought to be exclusively collisional, there's been some work which shows that, you know, there may be pathways of radiation that go along the shock front and then cause some additional radiative thing. So there might be something like that that comes up from more detailed studies, but as far as I understand, the current understanding is that they're collisional. And you can see the bow shock patterns that are causing these masers out in the outflows.
Additional questions?
I guess there are some in the chat here.
Oh, yep, there's one. Can you make proper motion measurements to determine space motions?
Yes, we haven't, I guess we haven't gotten around to that. We're still in kind of semi-discovery mode here because we're trying to target all the lines we can get. So we've gone through, and so this answers another question that's in the chat. We've gone through 36, 44, and 25, and now we're going through a host of others to see what we can find. But the proper motion is certainly on on our list. repeated measurements to make sure, just like in OMC2, that the magnetic field has remained the same, indicating that it's a larger region, the larger magnetic field that we're tracing. So all of that is on the cards.
And the very bright masers that you have, they are 100, 200 Janskis. You picked the brightest ones, isn't it?
Right.
You have plenty more than, yeah, okay.
Right.
So
In the discovery,
limited to the.
yes, we picked as the brightest ones possible. And that's where I guess the NGVLA comes in one of these days. We'll go down and down and down. Although in the 25 gigahertz, we were in tens of Janskis rather than hundreds. So it looks like there may be something special about the 25. There's kind of different kinds of regions, etc. So that may be doing that. But the 44 and the 36 were still in pretty reasonably bright masers, and we're picking the brightest.
All right, we'll thank Anuj again and put additional questions in the chat or in the Slack channel. And we'll continue through the program. Next speaker is Olga Payandina from the Joint Institute for VLBI, ERIC, and she is going to tell us about the Maser Monitoring Organization and the VLA and how they can facilitate observations of star-forming regions.
Yeah, thank you very much for the presenting me, and thanks for the opportunity to give this talk. I'm going to present our latest results, and especially results that we got with VLA. First of all, what's the Maser Monitoring Organization? There haven't been many Maser-oriented talks, so I figured that I should present our organization first. We kind of combine all the monitoring, Maser monitoring programs, most of them at least, and try to collaborate and search for Maser bursts, Maser flares. That's a change in their flux density. We have several branches. MTO itself, which is a monitoring program, MTO VLBI follow-up. With MTO VLBI, we manage all the follow-ups of these flares that we find, and MTO IR, which is infrared observations of the bursting sources. Because still we can, for example, confirm burst in a protostar only with IR observations, not without it. So we work with massive stars, and here I would like to highlight some difficulties that we face with them. Because with the low mass stars, we have this kind of barcode. We can observe them in optic and find out their ingredients, their evolutionary status, and stuff like this. With massive stars, we have some problems, and we need to find this kind of barcode for them. What are these problems? First of all, most of massive protostars, they are located at very far distances. So we need good resolution, facilities that able to achieve good resolution. The main problem is that these kind of objects, they evolve very fast. So at the very first steps of their evolution, they're still deeply embedded in their natal clouds. So we see the cloud instead of the star that we observe. And in this sense, what can help us is exactly cosmic masers, because they can shine through these clouds. And they give us this kind of a barcode, because with the particular masers, we can detect particular parts of the protostellar system. For example, with 6.7 gigahertz masers, that's class 2 methanol masers that were mentioned in the previous talk, we can detect accretion disks around massive protostars. With 22 gigahertz masers, water masers, we can detect jets in these systems. And with 44 gigahertz masers, methanol masers, again mentioned in the previous talk, we can observe these bipolar outflows in the system. When I want to talk about our results, the main thing how we should think about masers, that they're kind of things that we have with MRI scans with contrast. They highlight regions of particular physical conditions. And that's exactly what we need. We need to find all these parts of a protostar system. But we need to understand that, for example, if we see accretion disk highlighted with masers, that's not actually the whole thing. We can see all the ellipse of this accretion disk. Instead, we can see all these boundaries, all these paths, and it's kind of a maze rather than the whole things like outflows and jets. In order to find all these small pieces of the massive star systems, we started the high cadence monitoring of known maser sources, and that's exactly where MTOL come to play, because it's a widespread network of single dish telescopes, and we can manage these observations with them. With this QR code, you can check our website and see much more information on our organization. So the two main types of events that we try to find and we aim to observe. That the first one is maser superbursts. That's we can observe them only in water masers, so they are related to jets. This type of maser bursts is super rare. We have only 3 examples so far, maybe 4. I'll show you one example in my talk. And this one is particularly related to just kind of when we have a sudden increase in path of maser amplifying material on the line of sight of observer, when we can have a overlap of multiple maser regions. Because in these maser jets, we have a lot of turbulence, and clearly we have some overlaps of maser cloudlets. But another thing, even more interesting, it's accretion bursts. They are related to the very earliest moments of creation of massive protostars. We have similar thing in low mass stars. It's a bit easier to observe. And again, with this type of burst, we have only 3 or 4 examples. Also very rare one. A bit of history. Actually, our organization was established only in 2017. So so far we got just several big events detected. The one that I am going to talk about highlighted in red, but here you can see the whole list, whole coverage of our sources that we monitor with single dish programs involved in MTOL. The first source that we detected, it was superburst, so water maser in a jet. You can see that we had a bunch of observations with absolutely different facilities, VLBI, even Radiostron, Space VLBI, but particularly interesting results we got with VLA. thanks to VLA, we were able to resolve continuum sources in the field, in the region, because the source was not well studied, and we had just no idea how many protostars we have in this region, and which one produced these jets of water masers. Here on this map, VLBI and VLA data is overlapped, and you can see that thanks to VLA data, we were able to precisely image this kind of U-shaped thing that traced exactly the path of these cloudlets overlapping on our side of view. So it was crucial for understanding of this source. With the next source, we got another type of burst that was an accretion burst. It was highly, we couldn't observe it directly with far infrared observations because it was absolutely new type of a burst. It was the first near infrared dark burst. So we understood that actually an accretion burst thanks to maser observations. And in this source, for the first time, we were able to observe a propagation of a thermal radiation heat wave in the accretion disk around the central source. These results, they are from VLBI observations, but we have several pretty nice results obtained with VLA. For example, thanks to observations of really faint and rare maser transitions, we were able to detect spiral arms within the accretion disk in this source.
2 minutes.
Yeah, thanks. Here you can see that there was a drastic change in the accretion disk traced by masers. Here in the first epoch, we can see that was actually an accretion burst epoch. We can see these kind of spiral arms. And on the post-flare epoch, we already see some kind of a ring around the source, something completely different. And it happened just in 3 months. There is difference of just 3 months between these two maps. Another thing that there was a huge difference in the maps of water masers. We also work on this data right now. That's a larger region because with methanol masers we talked only about this protostar, and we can see that actually the whole region was affected by these changes. And that's the latest example. Thanks to the VLA, we were able to locate the flare masers because, again, this source was not well studied. And even though we wanted to observe it with VLBI, we just couldn't because we had no idea where exactly this maser emission comes from. And thanks to VLA, we were able to resolve 2 continuous sources here, and we found that actually water masers, there are 3 locations of water masers within the source. And we were able to conduct successful VLBI observations after observations with the VLA. And thank you very much again. Please check our website if you want to see these publications. And if you are interested in working with us or in our results, we'll be happy to collaborate. Thanks.
Thank you, Olga. That's an impressive data set you have. Questions? There is one in the chat from Lynn. SIO masers have been detected towards Orion, source 1, and a handful of other massive YSOs. Have you also searched for SIO lines in any targets?
That's not our primary thing to do because if you search for bursts, you need to monitor very variable masers, and the most variable masers are actually H2O water masers or 6.7 methanol masers. I don't know much about variability of COO masers, but as far as I know, they are not that variable, and it's harder to detect them. So maybe as a follow-up, we observe them, but not as a primary target.
Yeah. Anush?
Yes, so I was wondering, what is these flares that you're seeing, how far away from the source, like as traced by perhaps water maser emission, how far away in physical distance are you seeing these flares? And can you track kind of episodic activity? In what is the interval between these episodes, please?
Yep. With the, for example, if you have accretion burst, in the case of accretion burst, right? With the flares of water masers, we actually see a light echo, not a real perturbation of matter. That's still a heat wave, right? So it's a bit different. And we try to find episodic trace of the episodes. But so far we got only one episode for different sources, and we try to observe find episodes with water masers, because following bow shocks from the sources, you can interfere several episodes of accretion, right? So we try to do it for several sources, but again, it's more of M2O VLBI work rather than our primary set of telescopes monitoring with M2O. But yeah, we try to do it.
Okay, thank you very much. Great talk, thank you.
Thank you.
All right, thank you, Olga. We'll move on. We're a few minutes behind schedule. Next speaker is Mark McKinnon from NREO, who is going to tell us about the NGVLA we're waiting for.
Thank you, Ilva. I'll be giving a very high-level overview of the NGVLA. On Thursday and Friday, Eric Murphy and Rob Salina will review the scientific and technical aspects. Let me begin by just sort of a summary history of the VLA. It was approved by Congress, the US Congress, in 1972. Only 3 years later, the first antenna was put in place. And by 1980, the array was in full science operations and dedicated as what we celebrate today. The NSF approved a major electronics upgrade called the eVLA in 2001, and the Jansky VLA came into full science operations in 2012. Since that 1980, there have been over 7,000 refereed papers with an excess of 300,000 citations, 500 PhD theses. The VLA is among the most productive telescopes ever. So it kind of begs the question, it's 40 years old, how do you follow an act like that? We believe the answer is a next generation VLA, where the scientific frontier is thermal imaging at milli-arc-second resolution. The high-level goals of the NGVLA are to have something that's 10 times the effective collecting area of the VLA or ALMA, and 10 times better spatial resolution than those two instruments. And pause and just think a little bit about what that means. 10 times the effective collecting area means nominally 10 times the number of antennas, and 10 times better spatial resolution means you have at least 10 times longer baselines than those instruments. The frequency range will be 1.2 to 116 gigahertz. The array will be located in the Southwest US and Northern Mexico, centered on the present location of the VLA. And overall, we view it as very low technical risk. We submitted a reference design for the NGBLA in 2019. Rob Salina will be speaking to you more about this, but that frequency range of 1.2 to 116 gigahertz will be covered by 6 frequency bands and 2 refrigerated dewars, as you see in the table on the right-hand side. It's composed of 3 components: a main array that has 214 18-meter diameter antennas, offset Gregorian antennas, a short baseline array made up of 19 6-meter antennas, and a long baseline array also made of 18-meter antennas across the US continent, and there'll be 30 of those. This is what the main array looks like. You see what it looks like in the Southwest US in the upper right-hand corner. Again, antennas in eastern Arizona, mostly in New Mexico and West Texas, extending down into northern Mexico. As you zoom in on the center of that, you see this pinwheel pattern in the lower left-hand corner. And if you zoom in further still, you see this random location antennas with the short baseline array denoted by those green dots. This is the layout of the short baseline array. And I should mention that 4 of the 18 meters compose a total power array for this. And lastly, this is what the long baseline array looks like. It's the yellow dots on this map. They are located in locations that are familiar to us, close to or at existing VLBA sites, other radio astronomy observatories. But what is different, these are not single antennas as they are with the VLBA. They are ranging from 2 to 4 antennas at these locations, primarily for more collecting area on those baselines as well as calibration purposes. This slide shows a performance comparison of the NGBLA with other instruments that are in operations or plan to be so. The plot on the left is sensitivity taking the form of effective aperture by system temperature as a function of frequency. The salmon color is the NGBLA, the purple is SKA1, the red's the existing JVLA, and blue is ALMA. I'll admit we've not quite done ALMA justice here because its frequency range extends well beyond the right side of that graph. But the main thing we want to convey here is the NGBLA sort of fills a frequency gap between SKA and ALMA. So we do not view NGBLA as competing with those instruments, but complementary to the science that's done with those instruments. On the right, another slice in performance space, this time angular resolution as a function of frequency. And you see that the NGBLA provides exceptional angular resolution at centimeter wavelengths that compares to or exceeds that of planned optical instruments. Eric's going to talk to you more about key science goals, but I thought I would give you a teaser here. There are 5 primary science goals. We want to unveil the formation of solar system analogs, solar systems much like our own. When we find those systems, we want to probe the initial conditions for planetary systems using astrochemistry. We'd also like to use pulsars found at the galactic center to conduct fundamental tests of gravity. We would also like to understand the formation and evolution and of stellar and supermassive black holes in the era of multi-messenger astronomy. And finally, charting the assembly, structure, and evolution of galaxies across cosmic time. And again, Eric will say more in detail about these goals. What I would like to mention is these key science goals have been done in close collaboration with our community. Both Rob and Eric have been exceptional in bringing our community together to determine the science goals and technically how we achieve those. We've done that by a variety of science meetings, short talk series, community studies, NGBLA town halls, advisory councils, and science working groups. And I'll note this bottom picture is of the first and only so far international NGBLA science meeting held in Mitaka in September 2019. Just a few highlights to give you an idea of what's been happening over the last couple of years. Our science book was published in December 2018. There were over 286 independent authors, well in excess of 80 chapters in this book. It was quite the tour de force. In preparation for the decadal survey, we then assisted the community in submitting science white papers back in January 2019, following up by a separate paper describing the NGVLA facility in July of that year. Rob led the effort to complete the reference design concept for the NGVLA. That's a 3-volume set you see here in the lower right-hand corner, 54 chapters describing how the NGVLA achieves the science goals. There was an independent cost review in October of 2019, and then Tony and I presented the entire concept to the Decadal Survey RMS Committee in February 2020, just before the pandemic outbreak. More recently, we commissioned 3 independent conceptual design studies for the antenna design. Following that, we received proposals to produce the design for the 18-meter NGVLA antenna. That contract was awarded to MTech Antenna Technology out of Wiesbaden, Germany, and that effort is well underway now. Again, Rob will be speaking more about the antenna design in his talk. Our project is organized according to this organization chart. I won't delve into detail other than to note that it consists of 10 integrated product teams. It's very much in the definition style from the NSF, Major Research Equipment and Facilities Construction. And as you can see towards the top here, we have actively engaged technical advisory committee and a science advisory committee that contact the project through both Rob and Eric. This is the timeline for the project. At the moment, we are waiting to hear the recommendation from the Astro 2020 Decadal Survey. The last rumor I heard is that that is supposed to be delivered in early September. Assuming that we do well in that recommendation, we'll submit a proposal to the NSF for MREFC money to fund our design and development. We expect a prototype antenna to be delivered to the VLA site for performance testing in 2024. After the completion of the final design review, we'll enter into NGVLA construction in 2025 with initial early science in 2028 and full science operations in 2034. Everyone wants to know what something like this would cost. In our decadal survey submission, the total project construction would cost $2.3 billion, and that's in 2018 dollars. We are also seeking international contributions at the level of 25%, which would mean 1.75 billion would be the contribution from the United States. For the operations cost of this instrument, our target goal is $92 million per year, again in 2018 dollars. The US share of that would be 69 million, which is about 3 times what it costs the VLA and VLBA to operate today.
2 minutes.
Thank you. And I will wrap it up, Ilva. The NGVLA is being designed to tap into the astronomy community's intellectual curiosity to enable a broad range of scientific endeavors. The key science goals, the science use cases, science book have all been completed. Our reference design with the credibly costed and high technical readiness concept, it was completed for the decadal survey. Just this last June, we awarded the contract for the design of the 18-meter antenna. We don't see any major challenges as far as the technology goes. The main challenge for this, again, that Rob will speak to, is optimizing cost performance, manufacturability, and reliability. That's all I had, Ilva. Thank you.
Thank you very much. Let's see, a question or two.
Needless to say, that wasn't about star formation or exoplanets.
That's right, there was something else in between. I guess we'll all just really wait for the 2020 decadal survey results to come out. Well, I think there is plenty of space to do questions in the chat or the Slack channel, and we'll take this opportunity then to move on in the program. So thank you, Mark, for that overview. Next talk is an invited talk by Luis Rodriguez from the Institute of Radio Astronomy and Astrophysics at UNAM, and he's going to tell us about radio jets from young stellar objects. And at this time, I'm also going to hand over the session to Amy, who will take care.
Thank you, Ilva. Let me start by saying that I was at the BLA for the first time in June of 1978. That was before most of you were born. And it has been a fantastic experience. When I was there in 1978, there were only 10 antennas in place in a more or less east-west array. So you really had to integrate over most of the day to get a good UV coverage. The idea of a snapshot wasn't possible yet. I was there with Jim Moran, probably the best person to be with, one of the experts in interferometry at that time. At that time, the United States didn't have that many experts in radio interferometry, but this improved around the BLA. And as other speakers have done, I really would like to thank the institution and NRAO and all the people there that help us so much and taught us so much and so many things about interferometry. Happy birthday, BLA. The topic of my talk is going to be radio jets from young stellar objects. It is interesting to remember also historically that one of the things that produced the detection of these radio jets was the study of these mysterious nebulosities that were discovered in the 1950s by George Herbig and Guillermo Haro, the famous Herbig-Haro objects. In this sequence of modern photographs taken with the Hubble Space Telescope, we can see the HH object number 1, the first discovered, Herbig-Haro 1, and we can see that it is moving in the plane of the sky. This was known around 1980, and also the pictures are so good that give away the fact that what we're seeing is some sort of bow shock. At that time, that wasn't clear, and George Herbig himself was the one that discovered that Herbig-Haro objects were moving in the sky, and this led to people searching for stars that were not located in the Herbig-Haro objects, that were displaced, that were actually powering the Herbig-Haro objects remotely. And this was happening in the way of jets. And one of the really major discoveries was made by the BLA. And in here we have again an HST image of the Herbig-Haro 1 to the right and 2 to the left system. And what is powering them? Well, in the center of both HH objects in 1985, Prado et al. Reported the detection of a very compact radio source, an elongated radio source that is one of these jets associated with young stars. Now we know that these jets are the base, the origin of the larger scale jets that are seen in the optical of the Herbig-Haro objects and of the molecular outflows that result from gas that is entrained by these jets. Here we have a mosaic of different jets that have been imaged with VLA across the years. You usually see the main body of the jet, a very compact source that is very closely associated to the star. And sometimes you get to see jet, and you get to see lobes that are produced along the jet. Well, this is a table of some of the best studied jets, and what they show elongated morphology, and the best images indicate that collimation in this jet is present at the very small scales, certainly less than 100 AUs and probably less than 10 AU. They are associated to young objects of both high and low luminosity. They align with other evidences of the outflow at larger scale, like, as I said, the heavy cargo objects. Unfortunately, most of them they are thermal emitters, and that means that they are not very bright, and the fluxes are typically in the order of 100 to millijansky. And sometimes we can follow knots in these jets, and we see that they are moving very fast at velocities of a few hundreds to a few thousands of kilometers. One interesting thing is that when you look at the main body of the jet, you're actually seeing gas that was ejected from the star in the last few years. This is very fresh material. And most of them, the emission, the dependence of the flux density with the frequency, and the dependence of the size with frequency are indicative of collimated outflows of ionized gas that emit mostly free. They will show some beautiful better spectra, but what became clear as we started to observe these objects with the BLA and with the millimeter interferometers is that you had like two regimes. At centimeter wavelengths, the emission will be dominated by the jet, by the free of the emission of the jet. And as you go to higher frequencies, dust will come on very strongly, very steeply with frequency, and it will dominate the emission. But now we know that there is a wide region where both processes contribute, and you have to know very well about jets and also about this to really disentangle what role is each contribution playing. Another important discovery in which the BLA played a key role was that they are present in all phases of star formation, that they are present in very young objects, and even in transitional disks, objects with a transitional disk that are supposed to be more evolved and have started to form planets, you still can see jets associated with the inner parts of the system. And the other very interesting thing is that you can see these jets both in very high mass protostars, objects like IRAS 16457-4247 is associated with a forming O star. So this is very luminous, and it has a very nice jet. And on the other hand, as you go to very low mass objects, to objects in the substellar domain, you still find cases of outflows associated with them. So this is a phenomenon that is present across all the mass spectrum. And I don't know, maybe sometime we will see jets coming from forming planets. Why not? Since the planets will probably have some sort of disk, we may have a stage in which also protoplanets will have jets, but we don't know that yet. Of course, trying to understand why these objects had ionized gas was quite a challenge. Remember that most of the detections at the beginning were associated with low mass protostars progenitors of solar type stars that we know are very cold and shouldn't ionize any gas. Nevertheless, that we were seeing this ionized gas flowing. With the time, it became clear that this ionization was being produced not by photoionization, because there wasn't hot stars associated, but by shocks along the jet that produced this ionization, and explain why there was emission in free. Over the years, it was also found that there were correlations between the luminosity of the central object and the radio emission. The more luminous the object is, the younger star is, the stronger the radio emission. And also the more power there is in the outflows as measured by various traces, the stronger the radio continuum is. And Anglada was one of the pioneers in this area. And he found that most of these correlations are consistent with the predictions of a model of shock ionization. You have gas moving very fast, coming from very close to the young star, that shocks with the environment or even within itself, and this produces the ionization that we see as free radiation. Well, one of the things that are very challenging and very interesting, and we'll probably be able to finally do with the next generation VLA, is that these jets are ionized gas. So besides the free emission, we expect to see recombination lines. Now, the free emission is weak, so the recombination lines are going to be fairly weak. With the classic VLA, this was not possible. There were a couple of detections of radio recombination lines in apparent maser emission mode, but most of the jets have not been detected in radio recombination lines. And the hope is that the 10 times greater sensitivity of next generation VLA and also the much improved angular resolution will allow to finally detect these recombination lines. That would be great, because we will have from the proper motions of the knots in the sky, we will have the plane of the sky motion, and then from the recombination lines, we will have the radial motion. And we will be able to tackle problems such as how are the jets really accelerated and collimated. Another thing that has become clear is that in many cases, you are actually seeing several objects in a very small region of the sky. With the next generation VLA, it will be possible to follow discrete blobs in the plane of the sky, something that can be done now, well, but with great difficulty. This will be able to get the largest sample of sources. So all this appears to be very promising. And as I said, disks are now getting most of the publicity, but it is clear that in the inner part of this, you need to understand jets to really be able to disentangle both components. In particular, since also David will talk about this, if you want to go and penetrate into the inner parts of accretion disks, you have to work around 7 millimeters. And there you will certainly see also the emission from the jet. So we need to understand them very well to be able to separate both components. And now, one of the problems that is still continues to be around with us is how are these jets accelerated and collimated? And the problem is that all this is happening in such a small scale, probably less than a few astronomical units, that it has been very hard to say. as it happens in the extragalactic field, one of the ideas, the powerful theoretical ideas behind, is the Blandford-Payne mechanism. And this means that the disk around the star has a lot of energy, and using the magnetic field, this energy can be used to launch powerful outflows, and then the magnetic field later can wrap around and collimate the jet. But this is happening, as I said, on very small scales. For example, Emerlin has been useful in showing that the jets are present on very small scales. So all this is telling us that the collimation is taking place at very, very small scales. And that's why it is so hard to advance in this. Another topic that is very important is multiplicity. We all know from the studies of main sequence stars that the most common configuration is a binary system. And of course, we are slowly discovering that this is also valid for star formation, and that we need to have a very high sensitivity, to have very high resolution to be able to understand the different components. Especially in the case of massive protostars, this is a problem because you go and you try to study the jet and you try to study the disk, and you find that there are actually a group of stars there within a fraction of an arc second, and this makes things very, very difficult.
5 minutes, Louis.
Thank you very much. So one of the things that we're also going to be able to do much better is following these knots along the jet and being able to determine the proper motions in the plane of the sky. This has been done already with the classic BLA, and it can be done much better with the Jansky BLA. And of course, if in the future with the next generation BLA, we can get the recombination lines, we will have a 3D picture of how these components are moving in the sky, and we'll probably get a handle on how they are accelerated and how they are collimated. Now, a surprise, that also was discovered with the BLA is that we were very happy talking of thermal jets that emit free emission. It turns out to be that when the young star is massive enough, the jets are fast enough to produce non-thermal emission. That is, in shocks, you will get acceleration of electrons to relativistic energies, and you will have combined with the thermal emission, synchrotron emission. The interesting thing is that this synchrotron emission gives us additional information on the magnetic fields and on the conditions in the jet. And this is also being very interesting, although it complicated the interpretation, of course. As I said, one of the things that one is trying to understand is how the luminosity of the central object correlates with the momentum rate in the outflow. And that there are objects, but we need more objects in particular in the low luminosity end and in the very high luminosity end of the mass spectrum. But as I said, all this is being done both with the Jansky BLA and with the next generation BLA. There will be a revolution in this sense. Well, let me just end saying again, emphasizing that there is now enormous interest in understanding the formation of terrestrial-like planets. This, in principle, will happen within the inner few astronomical units of the disks, and their emission from the jet and the disk are going to be present, in particular, at the frequencies that we need to use to penetrate the disk and really get optically thin observations of the inner parts of the of the disks. And we will have to understand both objects very well. And I think that jets will come back to the limelight. And now, as I said, disks are getting practically all the attention, but we need to understand also jets. Something similar is happening in the case of black holes, that as you get closer and closer to the black hole, of course, you see structure that is probably related to the disk, but you also see the jets, and you have to disentangle these two structures. Well, thank you very much. And again, I really would like to acknowledge and thank both NRAU and all the people from which we learned so much. And I hope to be around by the time the next generation BLA takes its first data. Thank you very much.
Thanks, Luis. Are there any questions? I'll pause a little bit because sometimes people take some time to put stuff in the chat. There's one in the chat. In your long trajectory with radio observations, what is your prediction for the next 40 years?
Well, my hope is that we'll be able to understand how the jets are accelerated and collimated. There is some advance being made. There is some evidence in a few of the jets that jets are rotating. They are not only moving longitudinally, but there is also evidence of rotation. And that supports the idea that they are extracting their energy from the disk, which is what everybody thinks. So my hope is that we will understand how jets are accelerated and collimated, and that will be very useful, not only for protostars, but also, as we said, for black holes, for all these configurations in which you have a disk and jets. And hopefully everything will boil down to the blunt for pain mechanism, but we don't know yet.
Adele Plunkett asks, how many years of observations with NGVLA will be needed to obtain significant proper motion measurements?
Well, excellent question. In the case of the BLA, we really needed like a decade. Now, in here we have better resolution and more sensitivity. So I think that it will come down to a few years. It will come down to a few years. So it will be ideal for a PhD thesis. With BLA, we barely see the blobs and we don't have too much resolution. So you really needed like a decade to be able to really say that things moved clearly. But it will be much better.
Yes, we have another question. She thanks you.
Thank you.
Ari Lohr asks, is the central radio emission polarized? Could it also be synchrotron emission?
Well, very, very interesting question. The central source tends to be dominantly free. It doesn't have polarization linear or circular. The jets are the ones that do show non-thermal emission and evidence of linear polarization, since we're dealing with synchrotron. The central body seems to be sort of the brightest part of the structure, and it is, as far as I remember, free always. So we don't expect polarization, but we do in the more extended components. Linear polarization has been observed in HH8081.
Okay, thank you.
Thank you very much.
Again. And so let's move to our next talk. Our next talk is from John Tobin, and he will be talking about a revolution in multiple star formation led by the BLA and ALMA.
Hi, can you hear me and see my slides?
Yes.
Okay, great. I'm John Tobin. I'm at the National Radio Astronomy Observatory in Charlottesville. And And I'd like to thank the organizers for giving me this opportunity to present the research that I've been doing with ALMA and the VLA. And I'd also like to point out some of my key collaborators, Patrick Sheehan, Stella Offner, Caitlin Cratter, Tom McGath, and Yu Cheng, who is a PhD student who just finished from Virginia. So one of the reasons we want to study multiple star formation is that we know that a large fraction of main sequence stars are multiples. So you can see in this plot on the left that the fraction of stars with companions trends upward from the lowest mass stars to the highest mass stars. And so the FGK type stars, like our sun, are sort of sitting just under 50%. And most stars, like the M stars, are a bit under 40%. And so we know that there's lots of multiples, but where are these multiples? And there's been a painstaking study of the stars in the solar neighborhood done over the past several decades. And this is a histogram and a log normal fit to the distribution of periods or separations of the field solar type stars. And they end up with an average separation of about 50 AU. But there's sort of a long tail here at the end, you get many binaries that are much closer, and you also get a lot that are further away. But this is one of our boundary conditions, is that we know that however multiple stars form, they end up with a distribution not unlike the one we see here. And so then we need to understand how stars are forming. And the way stars form, this is the classic picture from Frank Hsu with the collapsing core. You have an envelope of surrounding gas. It's collapsing under its own gravity, and it's conserving angular momentum. So we have the surrounding envelope, and then the angular momentum conservation in that envelope leads to the formation of a disk. And then the interaction of that disk and protostar drives the outflow and the jet, as Luis just talked to us about. But in the case of multiple star formation, you have to expand on this process. And one of the ways we think multiple stars form is known as turbulent fragmentation. So the properties of the molecular cloud itself, where that star forming core lives, can lead to the formation of multiple centers of collapse. And so you might have more than one core, about maybe thousands of AU apart or less even, each with their own disk driving their own outflow. And they may interact later on and migrate. So this is what's known as turbulent fragmentation, and it's going to produce multiples that are separated by thousands to 1/10 of a parsec or so. But at the same time, you also have these disks, and one of the things that we aim to understand is whether or not these disks are gravitationally unstable. And gravitational instability in these disks can lead to the disks themselves fragmenting and forming close companions within a disk. And so that would preferentially form companions on scales less than 500 AU. And so bringing this back to our boundary conditions here, we know that things tend to form around 50 AU, or at least things end up around 50 AU. But until recently, multiplicity has only been examined for this really narrow range. So the range that I did not gray out, that is where, until about a decade ago, where we had examined protostellar multiplicity. And so we weren't even hitting where most stars are found to be multiple currently. But in the range that we could probe, we were already finding that most protostars were multiples. And to expand on this, submillimeter, millimeter, and centimeter interferometry is the key, because these protostars are enshrouded in dense material, we cannot use high resolution optical or near infrared imaging to see what's going on inside. We need to use millimeter, we need to use interferometry at long wavelengths to see what's inside. And so ALMA and the VLA and EVLA have enabled us to expand this parameter space dramatically by a bit more than a factor of 10. And so now we can routinely examine multiplicity down to about 20 AU scales, depending on the distance to region. And NGVLA is going to give us another factor of 10. So ALMA and the VLA, we're starting to get the peak of where the field stars are. And with NGVLA, we're going to be going down the other side of this log normal. So really, this is, we're in the midst of a revolution understanding how multiple stars form. And the VLA has been leading this. I mean, almost since its inception. This is a very early image from the original VLA from Beeging and Coing, 1985, where they found the outbursting class 1 protostar L1551 IRS5 to be binary, even though they weren't looking for it at the time, but it was there in their data, which just goes to show you how powerful the VLA has been and still is. So now getting on to the survey that I am leading, I'm leading 2 surveys that are known as Van Dam. The first one was of the Perseus molecular cloud, and the second one was of the Orion molecular cloud. So in total, we have about 400 protostars that we have sampled. With the VLA and Orion, it was a smaller number because we did the youngest subset. But what the really important thing here is highlight is that we have a large sample and we're getting down to 25 to 50 AU separation. So we're able to probe past the peak in that separation distribution for the log normals, or for the field solar type stars. So this is an overview of Orion and the protostars we targeted. And so right here is the main Orion nebula, but we're using the global picture of Orion, which includes the full extent of the molecular clouds in the region. And this is an example of some of the data that we are getting toward the multiple systems in Orion. I have these arranged in 2 columns. On the left is the ALMA image. On the right are the VLA data. And the same goes for the second column. And so, for instance, one source that Luis showed in his talk, HH1MMS, this one is actually a binary that we detect with the VLA. It wasn't so obvious with ALMA itself due to the slightly lower resolution, but we resolved it to be binary with the VLA in Ka band at 9 millimeter. And we also see an extended jet here at 9 millimeters. So as Luis said, to understand the disks, we also need to understand the jets because they are probing into these, they are extending into long wavelength dust emission. But the other thing to highlight though is that in this source here, HOPS 288, we have a very, very high surface brightness area of emission that we detect with ALMA. And in fact, we detect no evidence of fragmentation there itself. And that is because this emission at the ALMA wavelength of 0.87 micron is optically thick. And so we need the longer wavelengths of the VLA to probe through that optically thick emission at the shorter wavelengths. And at 9 millimeter becomes optically thin, and we can resolve a binary there towards this fairly dense opaque object. And the same is true in a couple of these other regions. So these are wider views of a more hierarchical multiple system, but I'm going to zoom in on a couple of them here. And here's another case where we have bright, smooth emission that we see with ALMA. Definitely looks like a disk and it's rotating. And that's work from Yu Cheng, which should be submitted soon. But then again, we see a binary here resolved with the VLA, and we do not really have a hint of it with ALMA. And again, you see a nice jet coming from the protostar at 9 millimeter. And then a similar situation is happening here with this protostar, where with ALMA, it's not really obvious, but with the VLA, we can definitely resolve something budding off of this protostar. And so we're revealing some of the closest binaries that we can find with the VLA. And the opacity limit really makes things hard for ALMA in certain situations, especially for the youngest protostars. And just to further drive that point home is that And these structures, these are some of the youngest protostars in Orion, and this is work from Nicole Carnath. These are the images from ALMA at 870 micron, and they are completely opaque. And here in this object, when you switch to the VLA, there are actually two sources there. But because of the opacity of the dust emission from ALMA, you can't really discern it until you go to the longer wavelengths. Now getting back to the multiplicity, putting all of our detections together, we can come up with really great statistics that are starting to rival the statistics of the nearby field solar type stars. So on the left is multiplicity fraction versus class. So class 0 being the youngest, flat spectrum being the most evolved. And on the right is companion fraction. So companion fraction is the average number of companions per star, whereas multiplicity fraction is whether or not it's just, is it a multiple or is it a single? And so for the class zeros in this range of separations we're exploring, class zeros are really the only ones exceeding the field solar type stars, both in terms of multiplicity fraction and in terms of companion fraction, but the others are consistent. But that is just for the aggregate multiplicity statistics, but we can do a lot better than this because we've resolved these systems and we can look at their separations. And this is the distribution of separations that we see. So the separation is plotted on the X and the frequency is plotted on the Y for our full sample. And the field solar type stars are plotted here. The log normal of the field solar type stars are plotted here. And you can see that the protostars are inconsistent with this distribution of field solar type stars. And you can demonstrate that statistically. Right, and I'm running out of time, and so I'll speed through these last few bits. And so for the class zeros, this double peak nature is, or bimodal distribution is strongest. And then if you go to the more evolved protostars, the double peak nature of the distribution gets weaker until you get to the most evolved, the flat spectrums, where they cannot be distinguished statistically from the field solar type distribution. And so bringing this all together, what we think is happening is that these small separations, we're getting disk fragmentation. At these large separations, we're getting turbulent fragmentation. And we think some of these guys that originally had turbulent fragmentation are migrating inward and contributing a bit to the close companions, but maybe not the dominant contributor. And I'll have to skip these last two slides because I'm out of time, but we do indeed have evidence of for disk fragmentation by combining data from the VLA and ALMA, and looking at our companion detections in terms of their frequencies with evolution. We are finding perhaps a signature of migration in our data. And with that, I'll leave my summary here and I'm happy to take questions.
Yeah, there's about a minute per question. So if somebody has something quick, that would be great. Okay, there's a question. What produces the radio emission and what can we learn from that on the system?
Oh, that's a great question. So the radio emission that we're seeing at 9 millimeter, so this is a great example that I have here, is it's a combination of both thermal dust emission and free emission, and that varies from source to source. Some sources are dominated by thermal dust emission, and some sources are dominated by free emission. And so this is why Luis says now we got to understand the spectrum of the emission, because we're getting contamination from the jet at very small radii.
Okay, thank you. I think we should move on. If there are any more questions, feel free to put them in chat and John can answer them. Gim, are you ready to speak?
Yeah. Yes.
Okay, our next.
Can you hear me?
Yes, I can see you and hear you.
I-
The next talk is by Guillaume Anglada, and he will be speaking on the radio emission of young stellar objects.
Hi, my name is Guillem Anglada from the Instituto de Astrofísica de Andalucía in Spain, in Granada. And first, I want to thank the organizers for giving me this opportunity to celebrate the 40th anniversary of the VLA. I will talk about radio sources in star-forming regions. I think the field of star formation is one of the fields where the VLA has produced unexpected results that surpassed the initial expectations. The initial programs at the VLA were trying to detect H2 regions and the winds from Pitauri stars, mainly in the star-forming regions. But now there is a lot of additional sources of emission that appear when one is doing an observation of these star-forming regions. And I want to discuss the tools one has to understand the nature of the sources one can detect in the star-forming regions. As Luis explained it before in detail, now one of the most popular interpretations of the centimeter radio sources in the star-forming regions, I will focus on the continuum emission rather than on the line emission, which is a more complex topic. The standard interpretation is that the most embedded protostars are easily detected through free emission that is assumed to originate in collimated jets. These jets have some properties which can be easily understood in a simple model by Reynolds that usually have a spectral index of 0.6. But one has to remember that this is only a reflect of the density that goes as r to the -2, that it does not indicate the collimation. So even a spherically symmetric spherical wind will have the same spectral index. And also another thing that should be reminded is that if one has a finite jet, this was with a minimum of and the maximum size, one gets a turnover frequency where all the emission becomes optically thin, and a low frequency turnover frequency where all the emission is optically thick, and one gets a slope of 2. This is because very close to the star, the emission is optically thick, and far away it becomes optically thin. And as the frequency changes, we see a combination of free and optically thin and thick emission that then combine to give this particular spectral index. But when we cut the jet, we will give something that can be easily confused with an H2 region. Also, in order to distinguish H2 regions and jets, these correlations that Luis also mentioned are very useful. And I should note that both the expected Lyman continuum and the emission because of shocks in the jet coincide more or less for a luminosity of 1,000 solar luminosities. And above these luminosities, the massive stars has less luminosity than it will be expected by photoionization, and the opposite occurs with low mass stars. But when the accretion decreases and the star evolves, then the sources tend to depart from this correlation, and the massive stars tend to coincide with the Lyman continuum predictions, and the low mass stars become under radioluminous and go below this correlation. That is also an indication of the age of the object. So in addition to jets, there are many other kinds of sources of radio emission that one can find in a star forming region. Also have been mentioned the dust emission from disks and envelopes, and also photoevaporating disks characterized by free emission, non-thermal gyrosynchrotron emission from the magnetosphere of evolved stars, young stars, and also non-thermal lobes, and also extragalactic background sources. So I will put some examples where one can disentangle these different mechanisms, and sometimes one can get very interesting results. So I selected 6 objects that they do not appear especially interesting or spectacular in the first images that were obtained at the VLA. But I will comment on them and will show you that all of them are very well known and very interesting objects. The first one is the prototypical T Tauri star. It was observed to study its stellar wind. However, it appears that it has 2 components, and it's interesting because the stronger in the optical is the weaker in the radio, and the weaker in the radio is stronger in the optical. The radio is highly circularly polarized, and this triggered different use of this emission by measuring parallaxes, and in this way it has been obtained very accurate distance to the star forming region. So something that started to study a stellar wind finally become a tool to measure parallaxes in this work led by Laurent Loeynard. Another interesting source is this one that apparently is a triple source that could look like an extragalactic source at first glance. And in addition, because these lobes have negative spectral index. However, it was realized that by Luis Rodriguez and Chema Torreyes that this source was associated with the molecular cloud because the ammonia, which is a very good thermometer, indicated there was a heating of the molecular cloud just towards the position of this triple source. So it was clear that this was not an extragalactic source, but a prototypical of the kind of object that Luis commented are these jets with a core which is thermal and distant lobes that are non-thermal. The next source in my selection is Agel Tau. This was the first 7mm map of Agel Tau published at the VLA in a work led by David Wilner. And it was interesting because at the work they derived a position angle of the elongation of the source, which is pretty close to the actual position angle of the disk. However, looking at this image, it's very difficult to foresee that this will become such a very interesting object. I should note that in 2009 with Carlos Carrasco, Carlos collected all the data in the VLA archives of this source and obtained this map at 7mm in color, in contours, and 1.3mm. And it's interesting that in this code, perpendicular to the direction of the jet, Carlos noted that there was a gap which coincides with the gap that was many years later discovered by ALMA. The interesting of this is obvious, because as has been noted by David before, because the emission at 7 millimeters is optically thin, as it had been exhaustively demonstrated by Carlos in several papers, and it's very useful to understand the region close to the star at very small radii in these protoplanetary disks.
2 minutes.
Thank you. The next source is the source that doesn't look like a jet or so. It looks somewhat elongated, but it is the famous disk in the star HD 169-142. This was a VLA map from archived data by Dent et al. In 2006. This was the submillimeter array map a few years later, which does not show a structure. However, in subsequent VLA observations at 7 millimeters, a ring-like structure was revealed that coincides very well with the polarized infrared image obtained by Quants. This is the last VLA map obtained by Enrique Macias. It is very challenging because this source is a minus 30 degrees in declination, so it's at the very limit of what VLA can do, but even it can obtain this nice image. Of course, is not comparable with the ALMA image, for which the source is more well suited in declination. Also, this is another interesting source that did not appear. It appears like a jet, but finally, because of the association with dust, it was recently demonstrated that was a photoionized disk, not a jet. So the last one I want to comment is these two sources in Orion. These are the two brightest sources in the far infrared in OMC2 that were observed by Ray Putt, Rodriguez, and collaborators. And they look like a jet, this one, and this one as a compact source with a nature that was uncertain. Further VLA observations at several wavelengths show that as the wavelength decreases, this emission associated with the far infrared 4 source was decreasing, and a small source appeared here. Interestingly, this source has a positive spectral index. This one, which coincides with the infrared source, far infrared 4, also has a positive spectral index, and this lobe has a negative spectral index. The higher resolution images resolved this source as a jet, and in a recent map by John Tobin, this is the VLA emission in contours, and the ALMA emission, this nice perpendicular structure with both the dust and the free emission simultaneously. The other source, which is far infrared 4, also is detected in the VLA as a point source. It can be a disk phase on, or it can be an envelope. And also the VLA showed that these nodes had proper motions away from this source. So this is clearly a powerful jet. This jet is also detected in oxygen 1, and here there is a strong interaction, probably giving rise to this non-thermal emission that requires relativistic electrons, and recently has been proposed also in a recent paper by Padovani as a source of cosmic rays. Thank you.
Thank you. We have time for 1 or 2 questions. Okay, there's a question in the chat. Thank you very much, Guillaume. Is it possible physically to have a simultaneous presence of a jet and an H2 region associated with massive objects? And do you know if there are any examples?
What happens is that in the earliest stages of the massive star formation, jets dominate. It is not well understood why the photoionization does not start. It starts later. So now is well known that when the H2 region is developed, this is a later stage. So it's very interesting to catch the phase where the ionized jet is no more shock ionized, but photo ionized. So there are several groups looking for that. There is a nice model prediction by Tanaka and collaborators in a couple of papers. And there are a couple of candidates, one by Andrés Guzmán and collaborators, and another by Sang and collaborators, that from a point of view are the best candidates for this stage that should be very short probably and very difficult to catch.
Okay, thank you. We've run out of time. If there are any further questions, feel free to put them in the chat and Guillaume could answer them there. Okay, let's move on. Our next talk is by Ana Carla Diaz Rodriguez. There we go.
Hi, thank you.
Hi, I hear you and I see your slides. Ana Carla will be talking about multi-frequency deep radio continuum VLA observations towards OMC 23.
Thank you, Amy. Yes, I will present part of my PhD thesis that I presented earlier this year. I did it in the Institute of Astrophysics of Andalusia with Guillaume Anglada, who just talked. And I am now at the UK ALMA Regional Centre now, at the Jodrell Bank Centre for Astrophysics in the University of Manchester. This work was born as part of the Herschel Orion Protostar Survey, HOPS, with the goal of characterize the protostellar content of the Orion star-forming regions. And over the years, this HOPS project has been complemented with observations at other wavelengths, from the near-infrared to the radio wavelengths, in particular with the VLA at centimeter wavelengths. And the HOPS team has already detected and characterized over 400 protostars in Orion A and B with a broad range of luminosities. And they have particular focus in the earliest stages of formation. These are class 0, 1, and some flat spectrum sources. The thing with these sources is that they are very deeply embedded in the molecular cloud from which they are forming. So if you observe in the infrared, you will see emission from the envelope. But if you want to see emission directly associated with the protostar, you need to go to longer wavelengths to radio observations. And in particular, in the centimeter, we can detect these radio jets that we have been talking about during the evening. And these radio jets trace the base of the bipolar jets that are powered by the protostars. So they are a very good tool to pinpoint the protostar. And also, if with interferometric observation, you have very high angular resolution, and you can use this for studying the multiplicity in the protostar stages. But you also can detect other centimeter radio sources when you observe toward star-forming regions, as Guillaume explained before. And some of these sources are also associated with young stellar objects, but in later stages, class 2, class 3. And you can also detect the interaction of these radio jets with the medium, and also background sources. And then you need to try to discriminate between which kind of emission you have when you observe toward these star-forming regions. Here I show you the distribution of the protostar detected by HOPS in the Orion A molecular cloud. And you see that there is a region toward the north that the protostellar density is higher. And this is called the inter-L-shaped filament because it has an S shape, the filament at this part. And in the northern part of this inter-L-shaped filament, there are the Orion molecular clouds 2 and 3. This region were observed in the past with the VLA at 3.6 centimeter by Rayport and collaborators. And they detected 14 radio sources distributed along the filament, and they associated them with young stellar objects. In particular, they detected radio emission toward the direction of the far infrared source 4, which is the last example that Guillem showed in his presentation. And we were very interested in this particular object. So we pointed the VLA toward it, and we observed it at 4 different bands: 5 centimeter, 3, 1.3 centimeter, and 7 millimeter. This was in C configuration, and we also observed at higher resolution configuration A at 5 centimeter. And as I say, our goal was to investigate the nature of the far infrared source 4, and this is the last example that Guillem showed in the presentation. But now, because we observed with the Jansky VLA, we had maps with a lot of sensitivity. In this high resolution map at 5 centimeter, we reached a sensitivity of 3 microjanskis per beam. And this is, we went 10 times deeper than the previous observations with the VLA. And this allows us also to study a bigger region. And at 5 centimeter, we analyzed a field of view of 12.5 arc seconds of diameter. And we detected 57 radio sources in our field of view. And these are the sources that are marked with plus signs in the middle panel. And then we wanted to investigate the nature of these radio sources, all of them. For this, we use, for example, we use the information that we got from the radio observations. We use the morphology of the radio sources, because if the source was elongated, this was pointing to the detection of a radio jet. If the source was extended, we could be detecting an H2 region. We also, because we had observations at several bands, we could derive the radio spectral index, which gives you the nature of the emission, if it's thermal or non-thermal. But because this was part of the HOPS project, we had access to other observations as well, and we use them. For example, we look for the association of our radio sources with the dust in the region at the scales of the filament with ALMA 3 millimeter, and also at the scales of the disks with ALMA of 8-7 microns. These are observations from John Tobin. And you see, for example, in this case, that we detected with the VLA, the radio jets, and with ALMA, the detection was of the dusty disk, and that they are this system that they are perpendicular. We also look for the association of our radio sources with star-forming tracers, like molecular outflows, and with cavities that these outflows open in the molecular cloud, and you can see the cavities in the near infrared. And we also look in the literature for the counterparts of the radio sources at other wavelengths, submillimeter, far, mid-near infrared, and optical and X-ray, because this also gives you information of what kind of object they are. And with all of these pieces together, we were able to propose the nature of 56 out of the 57 radio sources. Most of them are tracing young stellar objects, and we see emission associated with objects in all the 4 stages of in the 4 groups, no? Class 0, 1, that are the youngest, and most of them are these radio jets. But we also see emission associated with the more evolved young stellar objects, class 2 and class 3. In most cases, these are non-thermal emission, like this case I'm showing here, which is associated with the stellar magnetosphere. And in a couple of cases, we detected we detected thermal emission associated with these objects. So our interpretation is that we are detecting photoevaporating disks in these cases, and this needs further confirmation. We also detected the interaction of the young stellar objects with the medium in the form of these non-thermal knots that arise from the shocks of the jets with the medium. And in this case, for example, this is free emission that is coming from a gas that is ionized, gas that is in the wall of a cavity that you see in the infrared, and this gas is ionized by the shocks produced by the outflow coming from this nearby protostar. And we also detected extragalactic sources, as expected. And here I'm showing you a radio galaxy with the terminal shocks associated. So indeed, we were able to say something about the nature of the far infrared source. These are the observations that Guillem showed in his last example. We were able to disentangle the emission from the thermal emission from the protostar with the non-thermal emission from the non-thermal lobe of the jet of the nearby protostar FAR 3. And the position of this protostar in a region where the shocks are stronger support the trigger star formation scenario for this particular source. So, yes, thanks. Just to wrap up, we observed toward the OMC 2 and 3 regions with the VLA at 4 different bands. We detected 57 radio sources, and most of them were associated with young stellar objects. I showed the radio sources in this map, color coded by the nature. And in particular, we identified the radio jets powering the 9 outflows previously known in the region. And we detected 2 possible photoevaporating disks and 1 trigger star formation candidate. And also, I didn't talk about this in the presentation because of the time, but we also see signs of variability in 13 sources because we compare with previous observations. And 7 of them are also variable at shorter wavelengths. And 3 of them are very young, class 0 and 1, and this is very interesting and needs further investigation. And we also detected components of 17 potential multiple systems with separations less than 3,000 IU. And these systems goes from binaries to quintuples. So thank you very much. I'm happy to take questions if you have it.
Thank you, Ana Carla. There is a question in the chat from Luis Felipe. He asked, you seem to have detected quite a number of radio sources outside the molecular filament. Are these sources part of the region?
Yes, they are. I didn't talk about this because, well, there is a lot of interesting results in this with these observations. I think you are talking about these sources here and also here. You see that almost half of them are young stellar objects. And these are class 2, class 3 objects. They have been observed also with in the infrared. And so they have been already characterized as class 2, class 3 objects. So, well, we call this the perpendicular stripe because they are like distributed in a perpendicular direction compared with the filament. And our interpretation, well, we speculate here is that because this filament is formed by different fibers, and these fibers are coherent in velocity and position, and most of the fibers are elongated in the direction of the filament, but then you have some that can deviate from the position of this filament, and some of them are perpendicular. For example, this region is the one that we observe with the VLA in our observation. So this from this fiber is that the stars form. So because most of these radio sources are young stellar objects, but more evolved than the ones in the filament, we think that they were previously formed in one of these fibers that was perpendicular, or several fibers that were perpendicular to the filament, but the fiber itself have already disappeared because it formed these stars.
Okay, thank you. Are there any other questions? Feel free to unmute and ask if you would like. Okay, well, if there's nothing further, this session has ended. I would like to thank everyone, all the speakers in the session, particularly the speakers and the attendees in Europe, as it's fairly late in Europe right now. I think Anna has a few minor announcements before we go to break.
Yes, that's correct. It's very much the same announcements that I had in the first break in the morning. So if you haven't heard them, you may want to stay, but it will be just very much repeat. Other than that, we'll be coming back in 25 minutes. Right. So for the announcements is, if you have not yet heard, especially our Australian friends, they are just joining in us. All right, sorry, the next one. Next slide. We have a surprise VLA 40 Stellar Laboratory gift back for all the attendees, but we do need some information from you on details, what exactly we're going to send you. So to reach the survey, the questionnaire, please go to the conference website and look for the already registered information and just log in there. You will see your post-registration subsites, and then click on survey. Once you do that, it will explain exactly what it is, the gift bag is, and with a link to a questionnaire. So please do fill in that if you're interested in receiving the gift. Other than that, I just wanted to quickly repeat that the breakout rooms are open. There are virtual coffee. If anyone would like for informal chats, please do use them if you'd like. We have a highlight poster talks. There are around 18 of them. Go onto the website, go NREO.edu VLA 40. We do have a Slack VLA 40 workspace as well that everyone got the invitation to. Please join and start follow-up discussions. Also on Slack, I provided the instructions how to reach the link to the gift bag questionnaire. And of course, share your stories and photos in the scrapbook for the VLA. And again, the link is on Slack. I will repost it to the chat over here, but always you can email us at VLA40@NREO.edu at any time if you'd like any of those pieces of information. Okay, so that's it. If there are any speakers for the next sessions that would like to test their screen sharing, we can do it any time during the break.
Okay, can I, Anna, can you hear me? Hi.
Sorry, yes, of course, yes.
Can I just share my slides for testing purposes? Okay. Okay, can you see the slides?
The screen.
You can see
with your
this.
desktop.
Okay, one sec. And all screens. Okay. How about now?
Yeah. Yes, but they're not in full screen.
Now?
Yes.
Okay, cool. All right. Thank you for testing with me.
No worries.
Hi, I'm also going to test.
Sure. Go ahead.
All right.
Oh, yeah.
Everything looks good. Cool. Thank you.
No worries.
Can I also do a test, please?
Oh, sorry. Yeah, I should have the. Yes, of course. I was just wondering who's speaking, but I have a gallery. That would be easier. Yep. Perfect.
Cool. Thanks.
Where are? Okay. Just click that. We test it.
Yeah, hey Anna, same here.
Oh, hello.
Yeah, coming from very far away. Yeah. Give it a try, just a sec. Now, where's my pointer? Yeah, you see that?
Mm-hmm.
Looks all right.
Yes.
Okay.
It's presentation full mode.
What's that?
It's perfect.
Okay, thanks.
Oh, yeah.
Can I also check my share? Is that all right?
Straightforward.
Okay.
It just immediately went to the presentation mode.
I just wanted to ask one more thing. So the slides that I sent yesterday, I had to make one or two small changes, add a few things. So
Oh, that's fine. They are mainly for a backup. Just in case you have any issue once you, like, I don't know, when are you in an hour and a half, then we'll have them. That's very much.
no, I just wanted to know if they will be posted online somewhere.
We'll get back to the speakers about that.
Okay, yeah.
If we decide to do this. So
Thank you.
just a quick note, if there is anyone else speaking in the next session that hasn't tried to test their screen sharing, but would like to do so, we can do it in the next 3 minutes.
Can I do that?
Absolutely.
Hold on 1 second. So if I just...
Yeah, it worked the first time as well.
Okay, did it? Okay, great. All right, sounds good. Thank you. And you can hear me okay, right?
Of course. Shami, would you like to test your screen sharing, or are you all good?
I'd be happy to if that's something we can do right this moment.
We still have a minute or so.
Okay. Let's see. Does that work?
It's taking a little bit of time. Yes, it just took 15 seconds to load. But other than that, yes, we can see the full presentation.
Very good.
Right. Well, it's 3:05 Mountain. I suppose we ought to get started since we have a very packed schedule here. Emma, are you going to start recording? There we go. All right, welcome to the time domain session of the 40th, the BLA 40th anniversary meeting. We're going to start off with a talk by Genevieve Schroeder, who's going to tell us about dark GRBs and obscured star formation.
Great, thank you. All right, everyone, everything's good?
Do we have some chat or scripts or something on the side there?
Oh, I see. I shared the wrong screen. Well, is this better?
Yes, very good.
Great, awesome. All right, well, hello, I'm Genevieve Schroeder. I'm a fourth-year PhD student working with Wenfei Fong at Northwestern University. And I'm also being advised by Tanmoy Laskar at the University of Bath. And today I will be telling you about my use of VLA radio observations of dark GRBs to uncover obscured star formation. So to start off with some background, long gamma ray bursts, or GRBs, last longer than 2 seconds and are caused by the core collapse of massive stars. And these bursts release a lot of energy in the gamma rays, but they also produce broadband emission from the X-rays to the radio called an afterglow. And we can observe this afterglow to model the burst and determine physical properties of the burst and its environment. But some of these long GRB afterglows travel through dust along the line of sight, And this dust can cause extinction of the optical afterglow, leading to us seeing a suppressed and often faint or undetected optical afterglow. So this is what we call a dark GRB, and this occurs in about 10% of all long GRBs. So dark GRBs come about when the optical afterglow is suppressed, and we'll be focusing on when this is caused by dust extinction. But where does this dust extinction come from? So an easy answer is that the host galaxy itself is overall dusty and the extinction is intrinsic to the galaxy as a whole. But there is some evidence that some dark GRBs come from blue galaxies, so those without a lot of dust overall. And this implies that these dark GRBs occur within or behind local clumps of dust. So this was investigated by Perley et al. In 2013. Perley et al. Looked at a sample of 23 dark GRBs and compared many of their host galaxy properties to optically bright pre-Swift era long GRBs. And the properties I'm most interested in are what's being shown in the plot on the right. So on the y-axis, we have the host galaxy extinction, and on the x-axis, we have the line of sight extinction derived from the GRB afterglow. So this is displayed in units of magnitude and denoted A sub v. First, you may notice that the symbols on this plot are color-coded by the mass of the host galaxy, but this property is not important for my talk. So what you should first note is that there's a dotted line, and this dotted line is the marker of a one-to-one relation of host extinction to GRB extinction. So any burst that falls along this line or within the gray shaded region is considered to come from a homogeneous galaxy where the dust found along the line of sight is intrinsic to the galaxy as a whole. And so that amount of dust is present all throughout the galaxy uniformly. So the pre-Swift era's GRBs can be seen as the diamonds on the left. And you'll note that most of these bursts either fall within this homogeneous region or above the line where the burst itself was not obscured, but the host is dusty. And the dark GRB sample can be seen as squares on the right. So again, a lot of these bursts fall within this homogeneous zone, but there is a portion of dark GRBs that occur within blue hosts that are not very dusty overall. And we wish to contribute to this area of research by investigating dark GRBs that have occurred since this publication and improve on the methods for which we determine both the afterglow extinction and the host extinction in order to investigate obscured star formation in dark GRB host galaxies. So typically, GRB afterglows follow a standard broken power loss spectrum dictated by 3 break frequencies, which evolves in time from the radio to the X-rays. And if we can piece together this spectrum from our observations, we can determine the physical properties of these bursts. But if the optical emission is mysteriously suppressed, as it would be in a dark GRB, we must rely more heavily on the radio and X-ray observations of the burst to figure out the physical properties of the burst. So since X-ray observations are pretty much guaranteed thanks to Swift XRT, us observers are responsible for the radio follow-up of these dark GRBs. And we need to model this afterglow using our radio and X-ray observations to recover the amount of extinction that has occurred in the optical. Furthermore, when you are unable to detect a GRB in the optical, it becomes difficult to localize the burst well enough to claim a host association. So utilizing radio observations can help securely identify the host galaxy. So my sample includes 4 dark GRBs with radio detections, specifically radio detections with the VLA. And 3 of these bursts have had their afterglow modeled previously, with GRB 110709B being modeled by Zotterer et al. And Congas and Frutcher. GRB 111215A was modeled by Zotterer et al., Vanderhorst et al., and Congas and Frutcher. And GRB 140713A was modeled by Higgins et al., though we are contributing radio millimeter observations that they did not use in their analysis. GRB 130131A has not been modeled yet in the literature. So some of these previous models chose to use the typical synchrotron spectrum, which is usually a safe assumption, but not always the full picture. The full spectral evolution was laid out in Greenough and Sari 2002, and we use a special afterglow fitting software that was developed by Tanmoy Laskar and detailed in Laskar et al. 2014, which incorporates all of the physics laid out in Greenough and Sari 2002, as well as inverse Compton effects, jet breaks, and scintillation. This software uses a Markov chain Monte Carlo method to determine the best fit parameters of the burst, including the energy, environment density, and of course, the line of sight extinction of the GRB. So we choose to model these bursts again for consistency across the bursts, and so that we can be confident that the extinction values we derived encompass all of the available physics. So as an example, let me tell you the story of GRB 1407-13A. This burst was discovered by the Swift Burst Alert Telescope in July of 2014, and there was no optical afterglow discovered by UVOT. It was followed up in the optical first by the T100 telescope starting at 1.5 hours after the burst. And it was followed up by a few other optical observatories, with the Nordic Optical Telescope having the deepest limits. We triggered millimeter radio observations with KARMA starting at 1.5 days, then radio observations with the VLA starting at 3 days, and millimeter radio observations with PDBI starting at 4 days. This burst was also followed up in the radio by AMI, WSRT, and GMRT. With all of this data combined, we had a robust data set that could be fit with our modeling program. And here we are looking at the multi-wavelength light curves of the GRB as a function of flux versus time. We were able to match the light curves and the spectrum of all of these observations, and we found that our model of the burst did not reside on the typical spectrum for most of its observed afterglow, underscoring the importance of including the full spectral evolution for the modeling. We also identified evidence of a jet break in the millimeter light curves, underscoring the importance of high frequency radio observations. We were able to determine that the burst must have undergone at least 3.5 magnitudes of extinction to be consistent with the optical upper limits. And for the 4 bursts in our samples, we were able to either find the upper limits or the actual values of the line of sight extinction using this modeling program. I also want to emphasize that the A sub V values we are finding for these bursts are derived from full afterglow fitting, which gives a more robust result than the typical method, which usually assumes the typical spectrum and guesses where the cooling break frequency may be in order to find the extinction value. And this was only made possible through the radio observations of these dark GRBs. So we were able to get the dust extinction from the GRB afterglow, but now we are interested in how dusty the host is. So we use a Python package called Prospector to model the host galaxy of these 4 bursts and determine their host properties. Prospector is powerful because it is able to jointly fit host photometry and spectroscopy, and it's a Bayesian stellar population inference code that we adapted with the help of its founder to use nested sampling to fit the properties of this galaxy. The nested sampling provides full posterior distributions for the precise determination of key galaxy properties such as mass, metallicity, star formation rate, and of course, dust extinction. So following the example of GRB 1407-13A, the host galaxy of this burst was first identified in deep optical observations from the GTC shortly after the burst. And we took observations using the Large Binocular Telescope, MMT, and UCERT. So to give you an idea of how faint this galaxy is, it has an R-band magnitude of about 24. We also included observations taken with Spitzer in our fit, and we took a spectrum using Keck-Elrys to determine the host redshift.
2 minutes left.
Thank you. With Prospector, we were able to retrieve the entire posterior distribution for the host galaxy of 1407-13A, as well as produce a model spectral energy distribution for this host. And we fit all of the host galaxy observations for the 4 bursts, and we were able to determine the median dust extinction of each galaxy. So this is the culmination of all of this modeling. This is a recreation of the Purley et al. 2013 plot I showed earlier. And we found that for 3 of our 4 bursts, they do lie in this region of high local extinction, low galactic extinction, with extinction values of all the bursts ranging from 2 to 12 times higher than the galactic extinction. But what does this have to do with star formation? So we can use the star formation surface density, or sigma SFR, which is the star formation rate per unit area, to compare how much star formation is occurring at specific locations in the galaxies. We can calculate the local sigma SFR using this relationship from Kaneka et al. 2007, which determines the sigma SFR on scales of about 500 parsecs. And to do this, we can use the extinction values we found from both the GRB afterglow and the host galaxy to calculate hydrogen density columns and convert those hydrogen density columns to gas mass surface densities, which we then plug into the sigma SFR relation. So we can calculate the sigma SFR using the extinction values derived from both the host galaxy fitting to get the local sigma SFR if we were to assume that the dark GRB came from a homogeneous galaxy. And then we can compare it to the extinction derived from the GRB afterglow fitting and to see how they compare. So on the right, we are looking at the probability distribution function of GRBs and the ratio of the sigma SFR calculated from the 2 extinction values. We would expect for homogeneous galaxies, the sigma SFR derived from the 2 extinction values would be the same, and GRBs that occur in these galaxies would have ratios equal to 1 and therefore lie around 0 on this plot. This is true for a large portion of the dark GRBs in the Perley et al. Sample, which is not surprising because they did in fact fall in the homogeneous zone on the previous plot. But for 3 of the 4 bursts in our sample, we actually found sigma SFRs 10 to 50 times higher than what we would have assumed if it were in a homogeneous galaxy, revealing pockets of obscured star formation that we would have missed had we not modeled the afterglow. Additionally, the dark GRBs in both the Perley et al. Sample and our sample overall have higher ratios than the optically bright long GRBs, revealing the importance of following up dark GRBs in order to get the full picture of star formation within long GRB host galaxies. So with that, I can leave up my conclusions and take questions.
Excellent. Thank you, Genevieve. We have about 1.5 minutes. It seems that the chat might be taking a little while, so if you have questions, feel free to unmute yourself. And just go ahead and ask, or raise a hand and I can call out. Not seeing or hearing anything yet. So would there be any advantage to adding some other wavelengths to your monitoring, so infrared or like sub-millimeter, or like as you kind of covered up?
Yeah, so infrared can be useful because it's usually not as dust obscured for the afterglow. I think it's just possibly just it's harder to get those observations because you normally need space-based telescopes for them. So we don't often include them.
Fair enough. All right, 30 seconds for anybody else. Greg.
Yeah, so there's just something I couldn't quite understand. And that's because you're finding the star formation rate on the 500 parsec scale. Are you finding obscured formation or by dust, or really the fact that the formation is much more spatially concentrated than homogeneous?
Yeah, I guess that's a good question. So it could just be that the star formation is more just spatially concentrated, and overall the star formation rate of the galaxy may remain the same. We want to look into, because obscured star formation can be found in radio observations with host galaxies being brighter in the radio than you might expect based off of like optical calculations. So that is something we want to look into. It might not come out for this paper, but we can at least place some limits. But that is a good question. It could just be that the star formation is just in concentrated regions rather than where it's hiding in the galaxy as a whole.
All right, thank you very much.
Great. Thank you, Genevieve. Nice talk. All right, we're going to move from really big explosions far away to smaller explosions a lot closer now with Laura Chomek talking to us about classical movie. Okay, Laura, I'm seeing your slides, but I'm
Sorry.
not
All right. Sorry. I needed to unmute. Okay. Sorry. I'm here. So today I'm going to be talking about 40 years of radio observations of classical novae with the VLA. And this work has been done with a really wonderful large team of people, many of whom are in the audience and also listed here. So classical nova marks a thermonuclear runaway. It's an explosion marking a thermonuclear runaway on the surface of a white dwarf. And they occur in binary stars where mass is being transferred from a non-degenerate companion onto the white dwarf. And as that mass accumulates, it increases in pressure until it reaches some critical value where a thermonuclear runaway is reached. And the ensuing explosion is non-terminal. The white dwarf survives, but it does launch a fraction of a solar mass of material into space at a few thousand kilometers per second. And these explosions are typically discovered at optical wavelengths, but they do emit across the entire electromagnetic spectrum. And they're also very common. They're some of the most common explosions in space, with about 40 going off every year in our Milky Way, and about 10 of those actually being discovered and observed. So radio observations date back to the days before the VLA. As you can see here, here are light curves for 3 novae that exploded in the 1960s and 1970s. And these multi-frequency light curves were actually obtained with NRAO facilities in Green Bank that predated the VLA. This was work done by Bob Gelming in 1979. And that work in the early days of that predated the VLA, and also in the first couple of days of the VLA, that work on novae was really led by Bob. And I don't think it would be a VLA conference without giving him a little bit of a shout out. He really was the father of a lot of what we know about novae, and specifically radio observations of novae. So one of the things that Bob's work, along with many other people's work, helped build is a paradigm for our understanding of novae that is really predominantly thermal. So the way novae have been understood for decades is, right, so in this thermonuclear runaway, the accreted envelope is launched into space, usually at a couple thousand kilometers per second. And what happens is that white dwarf is remaining in the center, and nuclear burning that started violently with the thermonuclear runaway can remain nuclear burning for weeks to years after that initial runaway. And so what you have is there's a really bright, hot light bulb sitting in the middle of this expanding ejecta. And so this is the way that the multi-frequency emission from novae has been understood. It's basically just that luminosity from the white dwarf is being reprocessed through the ejecta, and that determines what we see in the radio, but also at X-ray and UV and optical wavelengths. And so at radio wavelengths, people for a long time thought that the emission was predominantly thermal. And when it's thermal, it evolves quite slowly. Typically, the radio light curves can rise for a year or a few years, and then slowly decline. And the work of Bob Gelming and Ernie Sequist and many others demonstrated that you can model the thermal light curves of novae and figure out the total bulk of ejected mass in the system, which is really cool for testing nova theory. So since that work in the first couple decades of the VLA, we've learned a lot at radio wavelengths, at other wavelengths. And this is a short talk, so I unfortunately don't have time to tell you everything we've learned about novae, but it's timely in the sense that we just wrote a review. So if you'd like to learn about some of the things we've learned about novae in the past few decades, you can check out our annual review. But one of the most notable things that's been learned about novae in recent years is that they are sources of GeV gamma rays, which was really surprising. It was a serendipitous discovery with the LAT on the Fermi Gamma Ray Space Telescope. And this was really surprising because in that thermal picture, right, that expanding ejecta just smoothly expands into space, doesn't cause any trouble. You wouldn't expect there to be energetic shocks or particle acceleration, any of the ingredients you need to get gamma rays. So when we realized that the gamma rays are quite luminous, and that implies quite energetic shocks, it really underlined for us how much of the physics of novae we had been missing and not really understanding. And so with that motivation, we went back to the VLA archive and we tried to gather and analyze all of the radio data in the VLA archive, which was a lot of data. We collected data on 36 novae that had erupted over the entire VLA's history, erupting from 1967 to 2018. And we recently put this paper on AstroPH with basically a big compilation of all of the radio data. And one thing to note about these novae is they're really quite diverse in their multi-wavelength properties. And so this nicely samples the diversity of novae. And novae are diverse, they are troublemakers. And so just to give you a little sampling of some of the VLA light curves that have been collected over the last 4 decades, just wanna flip you through a few. So sometimes when you observe a nova, you don't detect it at all with the VLA, or it's quite faint, like in this case of USCO, where, so in each case, in each of these panels, I'm plotting a particular nova, and in the top panel, it's the optical light curve, and in the bottom panel is the multi-frequency radio light curve. So on the right, we have USCO, and it's barely detected at the VLA, although even that detection is interesting. Whereas on the left, we have V1974 SIG, which is often called the nova of the century. And you see it reached a couple hundred millijansky at 22 gigahertz. So sometimes novae can be among the brightest radio transients in the sky, although it's worth noting that because they're thermal, that emission will be brighter at high frequencies than at lower frequencies. Sometimes, like in V392 Per on the left side here, the radio emission from novae evolves quite quickly over just a few weeks, whereas sometimes it feels like it's never going to peak, like in this case of V5667 SAG, where it rose for, I think, 4 years before finally peaking at C-band. Most radio novae only show 1 peak in their light curve, although occasionally they show 2, like in this really dramatic case of V357 Mus, where we see this early radio peak that's coincident with a optical episode of dust formation. And then you see a later peak that's probably thermal. And what we have learned over the years of observing novae is that usually when you see this early bright radio emission, it's an indication of high brightness temperatures in the system, and therefore also indication of non-thermal emission, right? So in novae, sometimes we get radio imaging, as I'll talk about in a second, but often we don't have radio imaging, but you have a sense of how quickly the thing is expanding from optical expansion velocities. And if you have a sense of how distant it is, then you can estimate the nova's angular size, and therefore you can estimate its brightness temperature, and you can get a sense of, right, if it's could plausibly be a thermal source or if it has to be non-thermal. So out of our collection of 36 novae, we found that 8 of them have relatively high brightness temperatures of greater than 50,000 Kelvin, and we say that that's indication of synchrotron emission. And for many of you classic radio astronomers in the audience, you're probably saying that 50,000 Kelvin is not a very impressive brightness temperature to be an indicator of synchrotron emission. We like to see higher brightness temperatures. And we do see that in novae if we observe with higher resolution facilities. So this is an example of what we can do when we image novae at high resolutions with radio facilities. So the color here is a VLA map obtained at 36 gigahertz, tracing the bulk of the thermal ejecta, whereas the black are 5 gigahertz contours obtained at higher resolution with EVN. And what we think is happening is that the VLA is tracing lower surface brightness emission, aka thermal emission, is tracing all that expanding material, whereas the EVN is showing you where the shocks are. And those shocks with the EVN have to be at like 10 to the 6 Kelvin or higher brightness temperature. So that's a really strong indication of synchrotron emission. And with imaging like this, we've put together an image or a picture of how shocks work in novae. So what we think happens is that early on, that when the envelope first puffs up and the first thermonuclear runaway first starts, the envelope puffs up and expands relatively slowly. But then as nuclear fusion, I'll start that again because I didn't time it very well. As nuclear fusion continues on the white dwarf, a fast wind is started and it crashes into the slower material. And when you get that crash, you get shocks, and that's what produces the gamma ray emission and the X-ray emission and the shock in the radio synchrotron. And so it's really with radio emission, combining it with gamma rays and X-rays, that we've been able to piece together this picture of how we think shocks are happening in a novae, and we really think that they are internal, right? So they're within a single explosion between discrete ejections of material.
2 minutes, Laura.
Thanks. So we've now collected all of this beautiful data, and we still have a ton to learn from it. Next steps to do with all of our beautiful light curves would be to fit thermal models and from those we can estimate the total ejecta mass in each nova. And that will be really valuable for testing nova theory, right? Because there are theories for how nova ejecta mass should scale with properties like white dwarf mass. And we can test that, which is really cool. But then if you subtract the thermal model from the total light curve, you should be left with just the synchrotron luminosity. And we can use that to study the synchrotron non-thermal properties of the nova, compare it with the gamma rays properties of the novae, and really understand shocks better in novae. So that's next steps for our big radio compilation. And then I also think the future is really, really bright for imaging studies of novae, because the future hopefully is bright for the NGVLA. And with the NGVLA, we'll be able to do something like this image we obtained for V959 MON. We'll be able to do it regularly, but we'll be able to do it even better. The thermal emission that we'll pick up will be at even higher resolution and even more sensitive. And meanwhile, we should also have the resolution sensitive enough to pick up variations in surface brightness and distinguish thermal emission from non-thermal emission. So that will be really exciting. So thank you very much for your attention.
Nice timing, Laura. Thank you. I love your description of them as troublemakers, by the way. That's fantastic.
You
All
agree.
right.
I know you do.
Oh, yeah, I do. Okay. So we have a question from Jean Elick. Can you say something about the movie? What sort of simulation is it?
Oh, this movie? This is not a simulation. This is a NASA PR movie that they made for our Nature Astronomy paper led by Elias Eide.
All right, a second question from Jose. Could you use this study to predict the next supernova event in the Milky Way?
Oh, you mean like to find like the next, like to find 1A progenitors? Is that the question?
Yes.
We definitely look at all interesting type 1A progenitor candidates. And I would not predict that any of them are about to go type 1A. Myself, I am skeptical of the single degenerate scenario, but that's a subject for another talk.
You stole my question. Greg, you have a question.
Sure. So you mentioned that some of these nova have these high brightness temperatures. Do these nova also have slightly less inverted spectral indices, showing that they're not necessarily fit by the thermal emission?
Yes, they do. Sometimes, so this is an example of that. So you will sometimes, often in novae, you won't see a traditional synchrotron spectrum. Like you won't see like a nu to the negative 0.5 spectrum, but you will see it get flatter than what you expect for like an optically thick thermal, which implies contribution from synchrotron. But I have to admit, spectral index hasn't been as much of a clincher as we were hoping it would be for non-thermal versus thermal distinguishing.
All right, let's see there. Brian, why don't you go ahead?
Hi, Laura. When you were showing the optical versus the radio, is there, those plots, I tried to, as you were flashing through them, do it by eye, but is there a correlate? Because on the first one, what I noticed is you said, well, some we don't see and some are really bright, but the bright one in the radio was also bright in the optical. And do those correlate or do they not?
Yes, they do correlate, but there's significant scatter. But the optical peak brightness does correlate with radio peak brightness.
Okay, thank you.
Yeah.
All right, thank you again, Laura. There's one more question in the chat. If you have time to please address that from Dylan Dahl. All right, but now we need to move on.
Thank you.
So moving from white dwarf stars now to neutron stars, Paul Demarest is going to talk to us about nanograv and pulsar science with the VLA.
Yeah, thanks, Justin. Just get my screen up here. Where's my pointer? How's that look?
Looks good.
Looks good. Great. Great. Yeah, well, thanks everyone for showing up this afternoon to hear about some pulsar stuff. So I'm going to be telling you, here's what I want to cover in this presentation. The first thing I'd like to do is really just kind of give you all a summary of the current pulsar capabilities of the VLA. And this is all post EVLA upgrade stuff. So VLA, aka JVLA or EVLA, whatever acronym you like. It's really become a quite capable pulsar instrument in the last maybe 6 or 7 years. So I'll tell you about how it works and highlight a few results that have been done mainly with these two types of observing modes that I'll cover. We have an imaging mode and then a phased array mode. So that's the first half. And then the second half, I'll give you the super quick review of our nanograv pulsar timing array project, which is a gravitational wave detection experiment. And we're in a bit of a transition period where we are just starting to make more heavy use of the VLA. So the VLA will become an important component of that experiment moving forward. And I'll give you the quick summary of that. So before I talk about the current stuff, I do want to give a brief shout out to a handful of brave individuals who did pulsar observing with the pre-upgrade VLA back in the 90s. And these include some very familiar names to this group, including Mark McKinnon, Tim Hankins, Steve Thorset, and others. I, of course, was not involved yet in pulsar stuff at that time, so I don't know all the details, and I don't have anything else to say about it in this talk, but maybe since this is a historical meeting, it might be fun if Mark or Tim are on the call and are able to share some comments on that at some point. All right, so moving on, as I mentioned, I'm talking about capabilities of the post-upgrade EVLA. So of course, as you guys know, we got a new correlator called WIDAR as part of the upgrade. I'm not really going to go into instrument details, but I absolutely want to acknowledge the commissioning and software team, many of whom I've listed here. These folks have been instrumental in helping me over the past 6 or 7 years, as I mentioned, get all this pulsar stuff going at the VLA. So there are a handful of different ways you can use the VLA to observe pulsars, and just as a note, whenever I say observe pulsars in this talk, I'm talking about actually observing the pulsar signal in the time domain. So you can, of course, observe pulsars just as continuum sources in images, but I'm talking about the time domain signal specifically here. So yeah, and it's a fast time domain signal. As you guys know, the pulse periods range anywhere from a few milliseconds to a few seconds, depending on what source you're looking at. So if you want to resolve the signal in time with the VLA, there's a couple things you can do. The first is an imaging mode, and I'll talk a bit more about that one on the next slide. But that's what we actually average the data up into separate bins as a function of the pulse phase, and you can do things like get an image, one image when the pulsar is on and another image when the pulsar is off, and compare them in various ways. That's pretty useful. The other type of observation that I'll talk about is the phased or summed array mode, and we sometimes call it the back-end yuppie. And in this mode, you phase up all the VLA antennas, you coherently sum all the voltages, and so you get out a single pixel data stream at very high resolution, which by high resolution, I mean something on the order of microseconds, and you can do all sorts of fun stuff with that, once you know exactly where your source is in the image. And then finally, there's one other thing I want to mention, which is just normal plain old imaging data, just dumped very fast on the order of 5 to 10 milliseconds. I'm not going to talk much about results from that mode, but that has been extremely effective for observing fast radio bursts, and you should absolutely tune into the later talks by Shami Chatterjee and Casey Law to hear more about that. Right, so about this binning mode that I've mentioned a few times now, in pulsar astronomer jargon, we would refer to this as folding. Let's see if I can get my pointer. And what this is if you say you have a time series and you know the period of your source. So it's a known pulsar, its period is 100 milliseconds or whatever it is. You can basically split up your time series into 100 millisecond chunks, stack them all up, and average them over many rotations, but keeping the pulse phase resolution. And so the reason you might want to do this is because, say your source is not bright enough to see every single pulse in the original time stream, yet when you stack them all up, you get a nice detection here. So this is done inside the WIDAR correlator hardware. Thankfully for me, the original designers of the instrument had the foresight to build in this kind of flexibility that we were then eventually able to take advantage of. So some of the science cases for this mode, the main one I've used it for in collaboration with others is for pulsar astrometry. So you can use the VLA. Typically we're observing at lowish frequencies, kind of 1 to a few gigahertz for pulsars. So you can get arc-second level local interferometric localizations of pulsars. The reason you might want to do this is because your initial single dish positions are typically pretty bad, many arc minutes. You can eventually get a better pulsar position from timing, but it requires observing the source for at least a year to get the whole Earth going around the sun thing and pin down the position that way. And timing solutions sometimes are difficult because of things like intermittency or timing noise in the data. So this can be a great way to quickly get pulsar localization. Another thing you might want to do is measure whether your off pulse truly is off, and that's an interesting use case as well. So here's a few initial results from this binning mode. I think the first paper to publish results using this was done by Kevin Stovall et al. In 2018. So there was a newly discovered double neutron star binary found at Arecibo. After a few months, we took a short observation with the VLA and got a position down to 100 milliarc seconds. Whoops. And you can see some of the images that resulted from that project down here. So on the left, it's the standard VLA image of the area. You don't know which of these dots in here is the pulsar. If you pull out just one particular phase range corresponding to this nice peak in the profile, you can see, yep, there it is. And then if you do something more clever and do kind of a matched filter using the full pulse shape, you get even better signal to noise. So this has been done a few more times more recently. There's a brand new paper, Agazi et al. That just came out doing the same sort of thing on another double neutron star system discovered at Green Bay. And in PREP, geez, I keep doing that. In PREP, a nice result from CHIME. This is a interesting binary pulsar in orbit about a non-degenerate star. It could be like an O or B star or something. And the VLA localization was pretty key in actually identifying the companion optically and getting science out. So watch out for that coming out soon. The next type of observation I want to talk about is the phased array. So as I've said, this is where you sum up the voltage signals from all the VLA antennas. People on the call might not like me to hear me say this, but this is basically using the VLA as a big single dish. We frequently do this for VLBI as well as for pulsars. In the VLBI case, we send the signal off to the Mark 6 recorder. In the pulsar case, we send it off to a computer cluster and do some real-time pulsar processing on it. The use case for this is all the normal pulsar stuff you might do with a single dish instrument like the GBT, pulsar timing, targeted pulsar searches. Some of the reasons you might want to use the VLA instead are simply for collecting area. This is a bit of a gross oversimplification, but roughly the VLA is something like a 130 meter equivalent single dish. So it's got a lot of area. And it has some nice frequency coverage outside the range available at other telescopes. And there's one special case I want to highlight, which is in the case of the Crab pulsar, the VLA does a very neat trick of resolving out the 1 kilojansky emission from the Crab nebula. And so you can get some cool results on the crab with the VLA that you can't actually get with single dish telescopes. And Natalia's talk coming up next is going to tell you more about that. So some early science results from the phased array included some nice observations of the galactic center magnetar, and you can refer to the papers there, Etoff et al. And Bauer et al. To see what we did there. Just for the purposes of showing some data, here's a nice set of pulse profiles versus frequency. I put this plot together a few years ago. The bottom two bands are from the GBT, so this is the 820 megahertz band and the L band at GBT and VLA S band. Just illustrating the nice frequency coverage we get from the VLA. Right, so I'm going to switch gears a bit for the last few minutes of the talk and tell you about NanoGrav. I'm sure a lot of you have heard me talk about this before. NanoGrav is the North American Nanohertz Observatory for Gravitational Waves. This is a group I've been involved with for a long time. It's an experiment. We're running a pulsar timing array experiment where we want to use high precision timing observations of millisecond pulsars to detect gravitational waves. How this works is totally analogous to how something like LIGO works. Instead of gravitational waves passing through your laser interferometer, tweaking the path lengths, you have gravitational waves passing through the galaxy, tweaking the path lengths between pulsars and Earth. We can potentially detect this with timing. The main difference is we're in science-wise, is we're sensitive to much lower frequencies. So the sweet spot for pulsar timing is 1 over the experiment duration. If the experiment duration is years, you get nanohertz frequencies, and are sensitive to different gravitational wave sources than you would observe with LIGO. And in particular, we're looking at supermassive black holes rather than stellar mass black holes. So it's a complementary part of the gravitational wave spectrum. Let's see. So we've been taking data for a long time. We recently, earlier this year, released what we call the 12.5-year data set, containing surprisingly 12.5 years of data on the longest observed pulsars. All of these data were taken with GreenBank and Arecibo at frequencies from about 400 megahertz up to 2.5 gigahertz, and roughly half the data came from each telescope. The plot on the left just illustrates the growth of the data set over time. You know, we started off with a few pulsars and ended up with the 47 published in this paper. As of mid-2020, we were up to 78 pulsars. So we typically add a few per year as new ones are discovered. But then, you know, tragically, as I'm sure you all know, Arecibo collapsed late last year. So we had to come up with a big change of plans, and I'll get back to what we're doing to address that in a few slides. But first, I just want to very briefly mention our results that came out with this 12.5-year data set. So we have analyzed the data for signs of a gravitational wave background coming from supermassive black holes. And we find some kind of intriguing but not quite definitive stuff. So we found significant evidence for excess low frequency noise in the timing data. The amplitude and spectrum of this noise are consistent across many pulsars. So we refer to this as the common root process. Of course, the big money question is this a gravitational wave signal? And we can't say yet, because so far we only find very weak, if any, evidence for this characteristic angular correlation. So what we're looking for is a correlation in timing fluctuations as a function of angular separation between pairs of pulsars. So the data for that are shown on the bottom here. And you can maybe kind of sort of squint and think it's a 2-ish sigma sort of signal. That would be great, but it's certainly not enough to definitively claim a detection. So we would like to get from here to eventually definitively claiming a detection. And the main way we're going to get there is adding in more data. So we're working on analyzing the last couple of years of data we have from Arecibo until it collapsed. And hopefully this will be enough to say something definitive. If not, we're going to want to collect more data going on to the future. So we've come up with a revised observing plan recently, and this relies heavily on some work done by a grad student at New Mexico Tech who I'm working with, Tyler Cohen. So Tyler has taken the properties of all the pulsars that we know about, along with the properties of the various radio telescopes that we have left available to observe with. And we kind of sorted out which frequencies at which telescopes give you the optimal results. And how this all came out is that we're moving so out of those 78 pulsars I mentioned before, about half were observed at Arecibo. We're moving most of those, except for a few that are just too weak. We're moving most of those over to GreenBank. We're going to observe them at L-band at the GBT. Luckily, we have a collaboration ongoing with the CHIME telescope in Canada, which observes at lower frequencies. So we're able to drop a lot of GBT time that we used to spend observing down at 800 megahertz and replace that with CHIME observations. So that's going to be a key component of the experiment moving forward. And then finally, it came out optimal to actually use higher frequency observations for a handful of them. These tend to be the more distant pulsars that are more heavily scattered. And so we're going to stick in VLA S-band observations for 12 out of those now, I think 71 or 72 sources. So this is the plan for the next couple of years. We proposed this last round and it got accepted. So we're just starting to move ahead with the new observations, and you should watch out for some new VLA and nanograv, VLA influenced nanograv results coming out over the next few years. All right, that's about all I wanted to say. Just in summary, the VLA is an excellent instrument for pulsar science. If this inspired you to want to do some pulsar observations with the VLA, I'd be happy to help you out learning how to do them. Nanograv project, we hope, is on the verge of detecting nanohertz frequency gravitational waves, and the VLA is going to play an increasingly important role in that over the next few years. And I don't have time to get into the details of NG-VLA, but I certainly want to mention that pulsar capability is part of the plan for NG-VLA. I expect it'll play a similar role as the VLA in future pulsar timing array work, kind of not the star, but an important supporting role. And one of the really cool projects we'll be doing, pulsar projects we'll be doing with NG-VLA is searching at the Galactic Center. All right, thanks very much.
All right, Brian has a question. Quickly, please, Brian, we only have 30 seconds.
A very quick comment. The old VLA pulsar system was called the HTRP, High Time Resolution Processor,
Right.
and Mark McKinnon could tell you all about that. But one quick question, maybe I know you're always extremely worried about systematics. So the ones that are being moved from Arecibo to GBT, I guess you're just going to watch for a couple of years and see if you see any evidence of different types of systematics.
Yeah, it's going to be tricky. Unfortunately, we couldn't do anything about losing Arecibo. The way we would have liked to do this is, get overlapping data on some of those sources, when transitioning to a new instrument, and that obviously is not possible. We do have a few pulsars that we have observed the whole time with both telescopes. So we have potentially at least some handle on that kind of stuff. But yeah, we're going to have to carefully watch that and see how and if we need to model any new systematics from the transition.
All right, thank you, Paul.
Yeah, thanks.
So sticking with spinning neutron stars, we're going to move on to a talk by Natalia Lewandowska, talking to us about high time resolution studies of the Crab pulsar.
Okay, thank you very much. Can everyone see my screen?
Looks good.
Okay. So I would like to thank the organizers for letting me give this talk. This is like a special case that Paul just highlighted in his presentation. So today I would like to tell you a little bit about our high time resolution studies of the Crab pulsar, and all of the data that I'm going to show you were taken with the VLA. I would also like to thank my collaborators, Paul, Tim Hankins, and Maura McLaughlin for their continuous support in this study. So I will be talking mostly about these two topics, dispersion measure studies and single pulse polarimetry. So let's start with the first topic. Well, let's start like the big picture question, why actually the Crab pulsar? So why are we interested in observing a point source with the VLA? But the reason is basically what Paul already mentioned, that the Crab pulsar is located in this nebula, as all of you know, and this nebula is actually the reason why the system temperature of single dish telescopes are actually becoming much higher when we observe the Crab with it. So that's a problem for the kinds of studies that we want to do, which mainly focuses on single pulses. So long story short, with the VLA, we can actually resolve the emission from the Crab nebula and actually detect more emission from the pulsar. And then if you wonder again, why the Crab pulsar? Well, the Crab pulsar is pretty weird. When you look at one of Tim Hankins's plots from a couple of years ago, this is a so-called radio profile going from 0.4 gigahertz at the top to 28 gigahertz at the bottom. And when you count all of these emission components that I explained in full names down here, you see that the Crab pulsar has around about 7 emission components. And the interesting thing is that their appearance is also frequency dependent, because you see that the main pulse is prevalent like at lower radio frequencies, but disappears at some point. And Also, some other characteristic that the Crab pulsar shows is that it has two interpulses. One of them we call the low frequency interpulse and the other one the high frequency interpulse. So the open question is, what are the radio emission sites and the corresponding emission mechanisms? And I can tell you that there is no definite answer to these questions yet, but these are the two big motivators for our study. So we took observations of the Crab pulsar in 2016 with the upgraded VLA. That data were taken, these were several observations, but when you put them all together, you get a frequency coverage from 2 to 8 gigahertz. This profile plot was made by Paul shortly after we took the observations. And mind you, the 2 gigahertz frequency is up here and 8 gigahertz are down here. So we detect 6 of the 7 emission components that I previously mentioned in the previous slide, because we are not going down to lower frequencies than 2 gigahertz. And what you can also see very nicely in this plot is that these two interpulses are really two different emission components. They are very near each other in phase, but it's not like the low frequency interpulse goes over to the high frequency interpulse. That's not happening. I highlighted this frequency range from 2 to 6 gigahertz because this is what the results that I'm going to show you will be based at on this frequency range. So the big pro of the upgraded VLA is that we have an instantaneous bandwidth of 2 gigahertz, which means we can collect a lot of signal pulses from the Crab pulsar. And I've been working mostly on the signal pulses from this pulsar that occur at the phase ranges of this component, the main pulse, the high frequency interpulse, and the low frequency interpulse. And as Paul already mentioned, we can go to very high time resolution with this kind of study. So I do study the signal pulses at these 3 time resolutions. So let's go over to the first project. The first project is focused on the search for emission component dependent dispersion measure. So what I wanted to see is when our signal from the pulsar travels through the interstellar medium, as we see here, and when it arrives on Earth, then all of us know that the electrons in the interstellar medium cause a delay in our signal, which you see here. So we usually correct for this. We do this during post-processing by just measuring like 2 frequencies or several frequencies, but this is just a sketch to make you like the principle, to make it clear. So we basically take like 2 frequencies, we determine the delta t, which you see in this formula here, out of such a diagram, and then we correct this like in each frequency channel. So that's how dispersion works. And when you do this correctly, then you get very nice straight pulses and a very nice profile, as you see in this plot. So mind you, I put like 2 profiles in here. The lower one where is resulting from 2 to 4 gigahertz observations, and the upper one from 4 to 6 gigahertz observations. And as you can see the main pulse here as the brightest one, and then you see the interpulse, for instance, here or there. And at 2 to 4 gigahertz or S-band, we still see it as 1 emission component. And then at 4 to 6 gigahertz, we see like out of a sudden like 2 emission components. So that's what is supposed to come out when you do the standard dispersion procedure. I asked the question, okay, when we disperse the data, is really all of the dispersion gone out of our data? So this was the question that I asked. And I used the single pulses here, for instance, from the phase range of the main pulse from 2 to 4 gigahertz to actually I searched for a time delay. And what I did was I looked into all of the 64 frequency channels that we had in the case of this data, and I determined the cross-correlation function of the total intensity of each frequency channel and with respect to a reference channel, which was usually the frequency channel with the highest frequency that I picked. So I converted the time lag that I determined out of the maximum correlation into a dispersion measure value. And that's pretty much what you also see here. So these are all 1 microsecond time resolution single pulses from the CRAB pulsar from 2 to 4 gigahertz. And this is post de-dispersion procedure. And you see that this curve is not straight, which means that there is still a delay in the data that we have not accounted for. So what I actually did, I determined this time delay and I converted it to the delta dm, or the dispersion measure, which is very characteristic for each pulsar. And I calculated the correct dispersion measure out of this procedure for the single pulses from all of these emission components. Mind you, the 2 first entries are from 2 to 4 gigahertz, and the other ones were taken at C-band. And what I noticed while doing this was that the high frequency interpulse, which is the second interpulse that shows up around about 3.5 gigahertz, is that it has like a much larger dispersion measure, which was something that Tim Hankins also observed already earlier, but this time we could determine this dispersion measure with much higher accuracy than he did before. So this was the first project. And the second one focuses mostly on the polarimetry of the CRAB pulsar. So in this plot, you see a profile of the CRAB pulsar from the 4 to 6 gigahertz observation. And again, you see, and again, you see the main pulse, the interpulses, and all of the other emission components, including the total intensity, linear polarization and circular polarization. And when you look at this profile, you pretty much have the impression, okay, this is how it should look like, at least to people who do pulsar work, because the amount of circular polarization is usually a little bit lower than the one of linear polarization. But the story is way different when you actually look at single pulses and their polarimetry. So what do you see in these two plots here? To the left, you have single pulses originating at the phase range of the high frequency interpulse from 4 to 6 gigahertz. And each dot here is one single pulse. So what you see when you plot the degree of polarization against Stokes' I and the polarization angle is that the single pulses from the high frequency interpulse seem to have like a very distinct polarization angle value, basically somewhere here, and also be highly polarized. So they go from 0.2 and degree of polarization, but most of them are actually up here. And when you look to the right hand plot, where I plotted the polarization angle against Stokes' I and the degree of polarization, you see that most of the single pulses are actually located in this specific area here. So they have very specific polarization angles. But we do not see this S-shaped sweep that was suggested by some of the first papers about polarimetry studies. Radhakrishnan and Koch is the paper that I'm now talking about. So the CRAB pulsar doesn't follow this rule. And just very quickly.
Natalia.
Yep, thank you. And just very quickly, so this is the high frequency interpulse from 4 to 6 gigahertz. When you look at the corresponding results from the low frequency interpulse, you see that you do not see much. So no structure, nothing, just like random single pulses spread all over the place. And when you look at the main pulse, you have more single pulses in this frequency range than in the case of the low frequency interpulse, but still no structure. So this is an indicator that the high frequency interpulse works very much different than the other two. And of course, as most people know, the CRAB pulsar is a very prominent source of so-called radio giant pulses. So single pulses that are much brighter, that are apparently not regular, that follow a power law distribution when you plot their intensities. So what I'm currently doing, I'm running this whole analysis on radio giant pulses only. And I define a radio giant pulse by basically saying These are single pulses that are very, very bright, at least 5 sigma bright. This is what you see in this plot. And they follow power law distribution. So what you see here are the single pulses higher than 5 sigma, depending upon the off-pulse emission. And I plot basically, I fit basically like this part of the distribution against this part of the distribution. And I'm of course interested more in these single pulses that are here in the power law tail. So this is the definition that I apply. I know there are different opinions about a definition of a radio giant pulse. But anyway, since I'm running out of time, this is what I wanted to show you. So we carried out phased array mode observations of the Crab pulsar. We have S and C band data. We are focusing in this study on the main pulse and both interpulses. We carried out a DM search and we discovered an excess DM value so dispersion measure value for the high frequency interpulse. This is a very good confirmation of earlier observations with the upgrade made with the pre-upgrade VLA. And we have an indication now that this high frequency interpulse is coming from a different part of a magnetosphere as it seems. And the single pulse polarimetry show us that while main pulse and low frequency interpulse are very similar to each other in the polarimetric characteristics, the high frequency interpulse is not. So stay tuned for the corresponding results about their radio giant pulses. Thank you.
Thanks, Natalia. We have a question from Mark McKinnon. On XSDM, any evidence that the time delays do not follow a cold plasma dispersion law, i.e. dependence other than wavelength squared?
Can you read this one more time?
Sure. For the excess dispersion measure, is there any evidence that the time delays do not follow a cold plasma dispersion law? In other words, dependence other than wavelength squared?
No, there's no proof of that at the moment. So we still assume a cold plasma and a corresponding dispersion law.
Okay, thank you. Time for one more question for Natalia.
Hello.
Go ahead.
Hello.
Yes, we hear you. Go ahead.
Gene Ehrlich here. I was trying to type it and I ran out of time. I've heard suggestions that the high frequency interpulse comes from a high altitude current sheet around the Crab. Have you thought about that or tried to do any modeling?
I have not tried to do any modeling yet, but I have definitely thought about it. Yeah. So I'm currently waiting until we get the corresponding results for the radio giant pulses to just see if they are different or not. But yeah, this is in the making. Thank you.
Okay, good. Keep thinking about it.
Will do. Thank you, Gene.
All right. Thank you, Natalia.
Thank you so much. Let me just stop sharing.
Certainly. All right. So shifting gears slightly from things that are definitely neutron stars onto things that are probably neutron stars, Shami Chatterjee is going to talk to us about the first localization of a fast radio burst.
Hi, everyone. Can you actually hear me and see my screen okay?
I can hear you. We're still waiting for your screen. There it is. Now it's up.
Very good. Okay, well, it is my very great pleasure to talk at this meeting celebrating 40 years of the VLA. I have spent a couple of years in Socorro, and I've spent many hours out at the VLA site taking photographs, actually photographs on film that are scanned in here. I spent a year as a pre-doc and 1 year as a Jansky fellow out at the Socorro site. And so it was really very special to me to be talking at this meeting. Here's my very rapid introduction to what a fast radio burst is. These are millisecond flashes of radio waves. And these are dispersed so that they arrive earlier at higher frequencies, later at lower frequencies. The proportion, it scales as 1 over frequency squared, and the proportionality constant of that scaling is the pulse dispersion measure. And that is just the line integral of the electron density between us and the source. So when this dispersion measure exceeds the maximum that is expected for our galaxy, we can infer that it is an extragalactic source and that the pulse dispersion measure, there's a contribution from the Milky Way, from the intergalactic medium, and then from the host galaxy. And in this plot, that's particularly clear where you see the blue dots, which represent all the pulsars in our galaxy as a function of galactic latitude. You can see the envelope of the galactic plane. You can see the little bumps for the SMC and the LMC pulsars. And then you see these red dots, which are single pulses, which are very clearly not part of this envelope of the galaxy. So there are 610 published sources of so far. The inferred all-sky rate is very large, over 5,000 events all over the sky per day. And the dispersion measures range from 100 to 3,000 plus. So truly enormous pulse dispersion measures. An important point to note here is that we are currently incomplete in every single FRB parameter. We're incomplete in our coverage of fluence, dispersion measure, widths, bandwidths, rates, repetitions, polarizations, you name it. So this is a field in its infancy, and it is really expanding rapidly. I want to talk to you, though, about one very special fast radio burst. And this one is FRB 121102, named after the date it was received at the Arecibo telescope, 2012, November 2nd. It was detected during the P alpha survey of the galactic plane. And so its galactic latitude is low, but it's located in the anti-center direction. And its pulse dispersion measure exceeds the maximum predicted for that line of the galaxy. So we realized that this was an extragalactic fast radio burst. We published that. It was moderately interesting. And just as a matter of due diligence, we kept coming back to that position and following it up over and over again until, in an email subject line that has become immortal in our collaboration, a minor point of interest, then graduate student Paul Scholz realized that we had redetected the burst. And so this was basically the first time that a fast radio burst source had been seen to repeat. We published this. Laura Spittler led the paper in Nature, a repeating fast radio burst. And at one stroke, this basically gave us two things. One, that cataclysmic or explosive models were out of the question, at least for this one source. And two, that this was a better than random location to go fishing to see if we could find out more about the source. Because the key problem with all of these fast radio bursts with single dish telescope identifications is that in the field of view, there are thousands of galaxies that it could be potentially associated with. So what I'm showing here in the white circle is the original detection at Arecibo. The other two white circles are the later detections. And so in fact, the initial detection, we were lucky because it was actually in a side lobe. And this yellow circle is our best guess from Arecibo observations about where the source might have been located. You can see, again, hundreds of compact radio sources, thousands of galaxies within that. And so we basically undertook a DDT request to say we would like to do fast sampled visibility data in order to be able to detect this source. We tried two different complementary approaches: millisecond imaging, where we would de-disperse the visibilities and make images for each sample time, so that we could search for a transient source in the time domain, and the complementary approach, which is basically to beamform and tile those beams all over the sky and look for a pulse in the time domain. And our first DDT request came up empty, our second DDT request came up empty, and these became increasingly fraught until finally, in work that was done with Casey Law, Robert Wharton, and a large number of collaborators that I won't mention here, we finally were successful. And so you can see back, I showed you the two Arecibo localizations beforehand, and this point source is the burst that was detected. And in the complementary approach, when we phase up the array at that position, we get a nice dispersed pulse with the 1/nu² sweep. And we published this as the direct localization of a fast radio burst and its host. This was the first time that the VLA appeared on the cover of Nature. And right there, that little compact source is what the fast radio burst was associated with. So this led us down two very interesting rabbit holes. First of all, the radio counterpart, it's a persistent source, about 180 microjanskis, compact, variable, non-thermal, and it just kind of bounces up and down. Even now, we're not entirely sure what it is. And in this plot, you can also see the sporadicity of our FRB detection. We didn't detect the FRBs in all of these early observations. And then once we started detecting it, we detected one or more bursts in every subsequent observation. And that's actually deeply significant, as we found out later. But also, once we had this very precise position, we could do deep optical imaging. And in the Gemini imaging, we basically identified a dwarf galaxy host. We measured a spectrum for it. We found out that it was at a redshift of 0.193. So this was a host galaxy a gigaparsec away. And so the VLA really played a key role in establishing fast radio bursts as an extragalactic population. Excuse me. Now, I won't be able to tell you much else about this source. Unfortunately, I'll only briefly mention that it's 100% linearly polarized in Arecibo observations. And so it has this spectacularly high rotation measure in excess of 10 to the 5th radians per square meter. We published this as well, work led by Daniela Micheli that got Arecibo on the cover of Nature. The rotation measure changes over month time scales, although the dispersion measure change is much, much slower. And that led us to understand that the source was embedded in an extreme magnetoionic environment. The pace of discoveries has continued, even just for this one source, it has continued unabated. Here's a picture of the 500-meter aperture spherical telescope, FAST, in China. And with FAST observations, we have now detected recently 1,652 bursts from this one source in 60 hours of observation. And we find that the energy distribution is bimodal. There's a clump of lower energy bursts and there's a clump of higher energy bursts. And whatever the mechanism is, it must be highly efficient because we're detecting over hundreds of bursts per hour of observation on some occasions. So this is a paper led by Dee Lee et al., and it is now in press. What this source could be is something I won't get into, although many different models still remain viable. The most well-developed model is that it's a magnetar embedded in an extreme supernova remnant or pulsar wind nebula, maybe. And there are many references to these models that I won't get into. The one thing I do want to mention, though, is using these fast radio bursts as probes, because these fast radio bursts are probing the host galaxy intercluster medium, intergalactic medium, and then coming through our interstellar medium to us. And this is all laid out in a white paper led by Vikram Ravi and all, fast radio burst tomography of the unseen universe. We could actually use these fast radio bursts to probe the intergalactic medium quite successfully. Here's one of the first attempts to do so, work led by J.P. McQuart et al., where they used a handful of these fast radio bursts, and after estimating some fixed host galaxy contributions, they actually could use that to make a direct estimate of the cosmic baryon density in the intergalactic medium, finding that it was consistent with what's expected from Planck cosmology. So this is a very exciting indicator that very good things might be possible in the near future. There is a word of caution that I want to interject here. We have recently used the VLA to localize another new repeating fast radio burst source, 190520. Again, this was discovered at FAST. Here's again a dwarf host galaxy, an infrared counterpart, and a persistent radio source associated with it in the VLA image. This is work that has just been submitted very recently, and we're talking about it at the FRB 2021 conference, which is actually running in parallel with this meeting. But I'll just point to this one slide, which is, here you see fast radio bursts. This orange band is the cosmic variance expected for the intergalactic medium. And for FRB 190520, there is this enormous excess contribution that appears to come from the host galaxy. So this is just a caution that you can't just use the extragalactic DM component as a proxy for distance. You do in fact need to localize the sources, identify the host galaxies, and obtain a redshift. And so there's going to be an ongoing role for the VLA and other radio interferometers in following up each of these fast radio bursts. What's next for fast radio bursts? Are there multiple source classes? Is it all one central engine? Can we use them as probes to study the intergalactic medium using their dispersion, their polarization, their scattering? For all of these things, again, it requires not just the detection, but the localization of these fast radio bursts. I'll end with just one, with a pair of advertisements. If you'd like to find out more about this field, Jim Cordes and I wrote an annual reviews article recently on fast radio bursts. And Emily Petrov and I run the FRB community newsletter, which picked up right after the annual reviews article. And we put out a newsletter once a month that you can use to stay up to date on fast radio bursts. So realizing the potential of fast radio transients, I'll just emphasize that the key requirements as we look towards the NGVLA and future instruments are instrumental flexibility and breadth of coverage of phase space, because it is very likely that the most important future discoveries are going to be surprises. And most of you will recognize the three things that I've highlighted here: the discovery of pulsars, the WOW signal, and FRB 121102. And with that, I'll stop. Thank you very much.
Thank you, Shami. We have about 2 minutes for questions. So feel free to unmute or raise your hand or type in the chat. Not seeing any yet. Okay, so kind of leaving the repeaters aside, is there any consensus on the Lorimer burst yet? I mean, it's kind of been determined to be an outlier.
No, the Lorimer burst no longer is an outlier. It's fairly consistent with the range and diversity of bursts that are now being detected. I mean, there are some things that are marginally iffy still with it, just because it was taken with a very early digital system. But other than that, no, it fits within the parameter space of these fast radio bursts. And now that we have localizations, like I showed here, we do have a whole bunch of these localizations, and the localized FRBs are telling us a fairly consistent story, other than this new one I just pointed out with this enormous excess.
Okay. Ron, you have your hand up.
Yeah, hi, Shami. Good to hear from you. You say 190520 has this huge DM, but isn't it also possible that you've got the wrong redshift and this is a foreground galaxy?
Yeah, so unfortunately, like I said, FRB 2021 is running right now, and Stella just presented a talk there. We can actually use the scattering or the limits on the scattering of this radio burst to say, could this be a foreground galaxy? And the conclusion is, if this was a foreground galaxy, then the pulses, the bursts that we do detect should have been highly scattered by several orders of magnitude more than the scattering that we do measure. So we measure burst widths of the order of milliseconds. And if in fact this was just a foreground galaxy, then we should have seen almost seconds of scattering. So we're pretty confident about our localization.
Hey,
there is also the association. Oh, sorry. There's also this association with this persistent radio source, which we think is also additional evidence that this association is correct.
But you don't know that the persistent source is in the same galaxy. But hey, the scattering is highly variable, even right through our galaxy. You can have changes of factors of 10.
Yes, and so, like I said, again, we do explain this. We have a very, very conservative lower limit on the scattering that we could expect if this was a foreground galaxy. And this is orders of magnitude off.
All right, thank you, Shami. Yep. There's a question in the chat. Feel free to address that offline, and of course, continue discussions on Slack. But now we need to move on to our next talk. So Arvind Balasubramanian is going to talk to us about everybody's favorite double neutron star merger.
Thank you. Can you can you see my slides?
Yep, everything looks good.
Okay. Yeah, hi. So I'm a third year graduate student at Texas Tech. And today I'll be talking to you about the role that VLA has played in the discovery and follow-up of the radio afterglow of GW170817 on behalf of the Jaguar collaboration. So this will be the outline of this talk. So I'll first give a brief summary of the multi-messenger discovery of GW170817. Then I'll talk to you about the efforts that went into modeling GW170817. Later, I'll talk about how the VLA has helped us in understanding many aspects of this source. And finally, I'll finish with what we can expect from late time radio follow-up of this source. So the story began with the discovery of GW170817 on 17th August 2017 by the LIGO and Virgo detectors. About 2 seconds after the gravitational wave itself was discovered, the Fermi telescope discovered a short gamma ray burst. With both these discoveries, the rays began to try and localize the source and find where it's located in the sky. So here is a picture of how the localization bands looked for just the LIGO, Virgo, or with the Fermi. A few hours after the GW, I'm sorry about that. A few hours after the GW wave was itself discovered, the SWOPE supernova team found a bright optical source. And with continued follow-up in UV, IR, and optical, the emission from this source was categorized to be quasi-thermal emission, which also included R-process nucleosynthesis, which is one of the reasons why we have heavier elements in the universe. The X-ray and the radio observations were actually a little late in all this chronology. So the X-ray observations came in 9 days after the GW event, and the radio observation, which was made with the VLA, came in 12 days after the GW event. With all the observations that we have had till now, the next thing to look at was to model the source. The GRB that was actually seen was very low luminosity GRB, even for normal short GRBs that have been observed till now. It was 4 orders of magnitude less. So the top 2 models that I show here are actually not feasible in this case. This model where we are observing along the jet of the short GRB itself is not feasible as this requires very unphysically low interstellar medium densities and mass ejected to agree with the observations that we have. Also, both these scenarios do not explain why we have a delay in the X-ray and the radio emission. So the bottom 2 scenarios seem to be a better explanation of the observations that were there at that time. So here we have the isotropic ejecta that is circular here, and the jet coming in these 2 directions. The brown region here is the area that is being termed the cocoon, which is material that is stopping the jet from escaping from this isotropic ejecta. So the 2 scenarios that we have here is either the cocoon does not allow the jet to completely break out of these ejecta, or it does allow them to. So for just a moment, we'll go into why we need VLA to study this object. So as we have already seen in so many talks till now, radio probes fast-moving particles. The VLA with the superior sensitivity, resolution, and frequency tunability helps us to study these kind of sources very nicely. So as I mentioned in the first slide, the radio counterpart was discovered about 12 days after the merger with the VLA. The radio observation with VLA and all the other radio telescopes in the world was crucial in showing that the afterglow rises very slowly, and therefore that there is a structure in the jet. The jet itself has different velocity particles as you go away from the jet axis. Also, the X-ray and optical observations between 10 to 100 days after the merger were not feasible because of the source being very close to the sun. So radio observations were key in trying to continue following up and observing this source. Then VLBI observations of the source helped to show that the jet was actually successful. Continuous monitoring of the source has given us constraints about the ejecta velocity distribution, properties of the interstellar medium, the angle at which we are viewing, and so on. So the final picture that we have right now of the source is itself like this. So we have a successful jet which is structured as you go away from the jet axis itself. We are observing at angles that are similar to this. The kilonova afterglow that was observed in the UV optical IR were actually from the isotropic ejecta here, and the jet emission that has been observed in has been non-thermal emission from the structured jet itself. Moving on to late time, what we expect from this source is that we expect these this kilonova ejecta to also interact with the interstellar medium and produce non-thermal emission, which is expected to happen at a timescales of a few years after merger. So deep observations with the VLA will help us understand this kind of late time emission. So in this slide, I'm actually showing you a panchromatic light curve, that is a light curve over different frequencies, which are all scaled to the 3 gigahertz frequency to this power law. So we see that the structured jet emission itself follows a very nice power law distribution. The morphology of the source itself implies what the shape of the light curve is. So the slow rise of the light curve shows that there were different components, velocity components along the jet itself. So we have a structured jet. The peak and fast decline show that the jet was successful in boring through the cocoon material. And the time at which the light curve peaks itself tells us where the at what angle we are observing the jet from. So in the same figure, at these late time scales, I'd like to bring your attention to this orange and this purple data point. So this orange data point is one of it's the deepest observation of the GW170817 field that we have made. It's about a 32-hour observation on source with a VLA. At similar time scales, X-ray observations have actually shown a discrepancy, and there is a possibility that the source is actually brightening in the X-rays. So the scenarios that come up in the near future are these. So one is where we expect that the radio will also rebrighten in the coming years, or that the radio will continue to fade. So in the rebrightening scenario, if what this excess in the X-rays itself is consistent with the kilonova afterglow, that is the afterglow from the isotropic ejecta itself interacting with the interstellar medium, then the spectrum changes from what we have seen here. That can give us clues as to whether we are in the relativistic or non-relativistic regimes. The other possibility is that there are outflows that are powered by the central engine itself, and that can cause rebrightening in the radio. Fading in the radio, so the excess that is less than 3 sigma excess here is still compatible with the structured jet. So we can expect, in that scenario, we can expect the radio to continue following this, this curve. The last possibility is that the X-ray rebrightening can be due to accretion onto the compact object at the center. In this, the expectation is that the X-ray will start to fall off, whereas the radio will still remain at less than 1 microjansky.
2 minutes.
Okay, yes, thank you. So here I just show just the 3 gigahertz radio observations, and these different plots here are the expected rising of the kilonova afterglow. This red one is our deepest observation that I showed in the previous slide. So continued observations with the VLA at similar sensitivities as our previous observation can help constrain different kilonova afterglows if the radio is rebrightening. And finally, we can also talk about the equation of state of the neutron stars. So here is a plot from Nedora et al. That actually shows how the light curve changes for different equation of state models. And our deep observations actually show that they are not compatible with any of these set of models. And so even similar observations in coming years will help us understand more about neutron stars and also this source. Thank you for the opportunity to speak here, and I'll take questions.
Thank you, Arvind. All right, any questions? Again, feel free to raise your hand or unmute or type in the chat. Okay, not seeing or hearing anything yet. All right, so quick question just about the logistics. Was the radio source not detected earlier, or was it not even looked at earlier than 12 days?
It was not detected actually. So if I just go back to this slide. So here, the date, I'm not sure if it's too small, but this is September 1. So that is about 15 days after the gravitational wave was detected, and we don't see the source, but on September 7th, we do see a source. So it was actually, yes, yeah.
Okay, thank you. All right, any other questions? All right, well, thank you very much, Armin, very good.
Thank you.
All right, so the next talk is Alexandra Teterenko, who will be talking about VLA subarray mode for fast radio timing with Blackwell X-ray binaries.
Great, cool. Thank you very much. So, hi everyone. Today I'm going to be talking about using fast timing observations of X-ray binary systems to study jet and accretion physics. In particular, I'm going to focus on the transformative role that the VLA has played in being able to do this type of science in the radio bands, highlighting some recent results on a few X-ray binary systems, as well as providing a bit of a future outlook on what's to come with next-gen instruments like NGVLA. And this work is done in collaboration with a bunch of awesome people, all listed on the slide there. All right, so before I get into the details of how we can do fast timing in the radio bands with the VLA, I want to first just kind of briefly outline the science motivation for obtaining these kind of data sets. In particular, why it's important to understand accretion-driven jet phenomenon and why X-ray binaries are the best way to do it. So determining how jets arise and quantifying the energy they carry, these are important multifaceted problems in astronomy. For instance, we know that jets can influence large-scale processes, such as the formation of stars and even the evolution of entire galaxies. Black holes and their jets also provide unique laboratories to probe fundamental physics beyond Earth-based experiments, where in creating the first ever image of a black hole, the Event Horizon Telescope has performed some of the most stringent tests to date on Einstein's theory of general relativity. Additionally, jets also come into play within the exciting new areas of multi-messenger astrophysics. For instance, one of the most promising ultra-high energy neutrino candidates are actually the jets launched from supermassive black holes. So these jets are everywhere, but despite their prevalence and importance in our universe, we still understand embarrassingly little about them and their fundamental properties. Now, our best chance to really kind of change this doesn't mean we necessarily need to be studying the big supermassive black holes, like all the examples I just showed you, because it turns out that the smaller stellar mass ones that exist in X-ray binaries in our galaxy are much more ideal test beds for jet phenomenon because they're numerous, they're close to Earth, and they evolve on human timescales, where the majority of these systems are actually transient, progressing from periods of minimal activity into a bright outbursting state on timescales of days to months. And this means we can essentially probe many more dynamical timescales and ejection cycles in X-ray binaries when compared to their supermassive counterparts, and really watch them change in real time. So I told you all about why it's important to understand jets and why X-ray binaries are really great laboratories for them. But what's the big deal about the time domain? Well, time domain observations now offer a promising new way to really address some key open questions in jet research. For example, we can probe physical size scales not accessible with current imaging capabilities. And to really put this into context for you guys, timing studies of X-ray binaries can uniquely accomplish science that VLBI simply cannot. We can go beyond even the scales that the Event Horizon Telescope could image if we pointed at an X-ray binary and zoom in close to the black hole where jets are first launched and accelerated. We can probe notoriously difficult to measure quantities like energy output and speed with the time domain, and by comparing variability across different wave bands, we can link changes in the inflowing material probed by the X-ray with changes in the jets probed by longer wavelengths, thereby mapping out the sequence of events leading to jet launching and particle acceleration like never before. So given their incredible diagnostic potential, time domain studies have used extensively to study accretion around stellar mass black holes at X-ray wavelengths. However, it's only recently that technological advancements have actually made it possible to do these kind of studies in the jet-dominated longer wavelength part of the electromagnetic spectrum. Now, this first began in the optical and infrared, due largely to the advent of new fast readout detectors that allowed us to start probing sub-second timescales, getting closer and closer to what we are capable of doing in the X-ray already. But what about the longer wavelengths? Well, we've known for a while that radio jet emission from X-ray binaries is highly variable. But while the longer timescale variations have been tracked and well characterized in a lot of systems, this is really not the case for short timescale variations. So like less than a day, less than an hour, for which there's still really only a handful of detections. Now, the reason for this is while time-resolved observations are such a staple for X-ray binary studies in the X-ray and now even in the optical and infrared, there are still a lot of challenges that accompany doing such studies at the longer radio and submillimeter wavelengths. In particular, it can be difficult to disentangle intrinsic source variations from atmospheric or telescope gain variations. Our observations are often involve routinely cycling between observing a target and a calibrator, and in most cases, only one frequency band can be sampled at once. So all of this complicates time domain analysis. However, luckily for us, with today's more sensitive interferometric arrays like the VLA, which offer more customizable observing modes, we can actually begin to lift some of these limitations and start accurately sampling X-ray binary jets at radio frequencies in the time domain. But unlike in the optical and infrared, where simply having a better instrument was enough to really be a catalyst to doing these studies, in the radio, because of all the extra limitations we face, we have to also get a bit more creative with how we're using our instrument. Now, in particular, one technique that's proved to be incredibly important in overcoming the limitations we face in the radio is the use of subarrays. So essentially, what we can do here is we can split the full VLA array into separate subarrays, each essentially operating independently of each other. So you can imagine, say, splitting all 27, the full 27 element array into like a 10, 9, 8, 3 subarray split, observing a different frequency band with each subarray. And you're essentially able to be sampling 3 different regions of the outflowing jet, solving your simultaneous multi-band problem, and basically getting 3 telescopes in one. You can even get more fancy and start syncing up your subarrays to manufacture longer bouts of continuous data. And this becomes really important when we want to be using Fourier domain techniques to analyze our variability, and I'll get to that in a minute. But when it comes down to it, subarraying allows us to get the data that we need to take advantage of timing techniques that have been perfected at other wavebands, like in the X-ray. But now we can do it in the radio. So this is great in theory, but how does it work in practice? Well, our first attempt at using subarrays came during the 2015 outburst of B44 Cygni, where we used 2 subarrays, and this allowed us to sample these incredible flaring episodes that you see here on the left that actually coincided with repeated jet ejection events that you see resolved with the VLBA on the right side of the slide in that movie. And we were also able to combine the subarray VLA with the SMA and JCMT here in Hawaii, and to get this really incredible view of these ejection events. Now, that was really rare bright phenomenon. So what about a more typical, quieter source? Well, recently we observed Cygnus X1, again, using 2 subarrays at the VLA and synced up with X-ray observations from NuSTAR to really try and connect what's happening in the jet to what's happening in the accretion flow. And in this case, we got a bit fancy with our subarrays and synced them up so that we get longer continuous bouts of data that you can see in the light curves. And again, we're able to resolve these nice, beautiful flaring episodes. Now, recently, we kind of stepped it up a notch again, where what we really wanted to do was be able to connect variability across the electromagnetic spectrum. So we want to combine what we've successfully done with a subarray VLA in the radio with all these other bands, sub-millimeter, infrared, optical, X-ray. And we did this with the system MAXI J1820, where we combined a subarray VLA with ALMA, VLT, NTT, NICER, and XMM, giving us this killer combination of 10 different electromagnetic bands all at once. And over half of these bands are coming from a subarray VLA. So that gives you an idea of how important this has been in this science. And again, we see incredibly beautiful variability in terms of these rapid flaring episodes. All right, so it's clear that subarrays can allow us to get these beautifully sampled time domain data sets. Now I want to show you an example of with this latest MAXI 1820 data set of what we can actually do with this and kind of deliver on my promise from earlier slides of probing jet physics with the time domain. So the first thing we need to do is we need to characterize the variability we're seeing in our light curves. And to do this, we can start in the Fourier domain. Now, by building power spectra of our light curves, we noticed that there was clear differences between the power spectral shape and amplitudes for the different bands. Notably, the break, after which the power becomes damped on shorter time scales, seems to move to lower Fourier frequencies as we shift to lower electromagnetic bands. That's what you see here on the left of the slide. And we also see a trend in variability amplitude where it increases with electromagnetic frequency. Now, that's what you see here on the right. And both of these plots are color coded with a little schematic on the bottom of the slide there to give you an idea of where the different emission regions are coming from. Now, this trend in amplitude is easily enough explained by the fact that we expect higher electromagnetic frequency emission to originate from a region with a smaller cross section closer to the black hole. And the power spectral break trend, we believe, at least to first order, is actually tracing the size scale of the emitting region downstream in the jet. So in this sense, we're essentially using the accretion signal propagating down the jet as like radar or sonar to map out the jet, which is quite cool. Now, beyond just looking at the amplitudes of the variability, we also want to examine how correlated the variability is between the bands. And this is, again, a key thing we can do because of our use of subarrays, because we have this multi-frequency data all at once. To look at these correlations, we can use cross-correlation functions to look for lags or delays between our bands. And here on the slide, I show you an example of lags we detected between the radio bands from our subarray data in 1820, where again, we see this clear trend with electromagnetic frequency, exactly as we would expect if these lags are tracing material propagating down the jet flow. So, thank you. We have all these timing characteristics. We have lags, we have power spectral properties, we get average fluxes for free. How do we actually make the connection to real jet physics? Well, we can actually predict all of these quantities with even a standard compact jet model. So by simultaneously modeling all these measurements, we can start deriving meaningful constraints on key jet parameters, where for MAXI 1820, we, for example, found we have a highly relativistic, highly confined, incredibly powerful jet. Now, if you're not an X-ray binary person, you may not be as excited as me about this, but the bottom line to really kind of take away here is that by using observational techniques like subarrays combined with the modeling formalism we've developed, we can actually derive fundamental jet properties from light curves alone. So this is an incredibly powerful technique, but there's still one problem. The majority of these studies are one-shot observations and thus unable to probe how jets evolve over time through different stages of their outbursts. So to tackle this problem, I developed a multi-year large observing program that we call Pitch Black. It connects a global network of telescopes anchored by the JCMT here in Hawaii and includes the VLA. And the program is designed to perform this same spectral timing experiment throughout outbursts in 6 different systems over the next several years. Now, in addition to this systematic study, we also have a couple of lovely VLA subarray data sets of a couple more peculiar systems, Cygnus X3 and GRS 1915, that are also under analysis right now. So stay tuned for some exciting results from that. All right, so hopefully I've shown you that time domain analysis is an incredibly powerful tool, and we're not just limited to the X-ray bands anymore. We can push to longer and longer wavelengths with today's instrumentation, most notably VLA and subarray mode. So with these kinds of data sets, we can derive fundamental jet parameters from the time domain alone and really get out physics that we can't with other methods like VLBI. And while there's been a lot of early successes in these types of studies, especially driven by the VLA, they're still very much in their infancy. So we need to continuously improve and adapt them. And I hope the Pitch Black program is in a way an example forward in the near future. But looking farther into the future, we can look to improve capabilities of next gen instruments, especially the NGVLA, to play a key role in this science in terms of sensitivity and wavelength coverage. So there's a lot of exciting prospects for continuing to develop these spectral timing experiments, and the VLA and NGVLA are going to be key in driving new discoveries with this science. Thank you very much.
Excellent. Thank you, Alexandra. All right, we have about 2 minutes for questions. So again, Joe Lazio.
Hi, you can hear me?
Yep, go ahead.
Okay, nice talk. Completely agree on the importance of time domain surveys or time domain monitoring. Since you mentioned ALMA 2030, have you given any thought as to whether, or it may be potentially stupid question, is subarraying at ALMA and getting closer to the base of the jet feasible?
So that is an excellent question. And while unfortunately subarrays aren't possible right now with ALMA, myself and a couple other people have kind of been putting feelers out with like ALMA and NRAO user committees and stuff like that to try and get this sort of idea in the pipeline so that maybe using subarrays with ALMA might be possible in the near future. But you're absolutely right. Being able to do this with ALMA would be incredible for this kind of science. And yeah, we could get closer and closer to the base of the jet and really do some awesome stuff with that. Yeah.
All right, 1 minute left. Anybody else have any questions? Anna points out that, Alex, you appear upside down.
Oh, I don't know how that's happening. I'm sorry.
All right, well, thank you very much, Alexandra. That was great. So due to normal meeting creep, we are running roughly 5 minutes behind. That's not too bad. Our final talk for the session is Ron Eakers, who's going to give us a historical talk about the first 7 years of the VLA.
Okay, for me, good morning. I hope you can hear okay.
Yep, very good.
And I'd like to thank the organizers very much for shifting me into this, for us, much more pleasant time zone than the original 5 a.m. slot. So thank you very much. So 40 years of history, or celebrating 40 years. I've started with a standard quote, which you can read, to point out that talking about the history is also important. And while celebrating fantastic VLA discoveries as you are doing in this celebration, you might leave the meeting thinking that the telescope was actually designed to make the kind of exciting discoveries that are being discussed, the specific discoveries. But as I will discuss, the key to the VLA was designing a telescope which could open a new window on the universe. And all the discoveries in this meeting are following from that. And I make this point because if you now look at funding proposals, there's this idea that you have a science case and that justifies spending the money, but it doesn't actually work that way. So I thought I would start introducing the VLA when the concept in 1962 first arose that an imaging array would be the way to advance radio astronomy. Joe Pawsey had just been appointed director of NRAO, and he came very much with the concept that the next step in radio astronomy was an imaging radio telescope. Other colleagues, especially Cam Wade, were playing with the same idea. And shortly after joining NRAO, Joe Pawsey set out this vision. The field of radio astronomy, only about less than 20 years old at that point, of what the future would be. And here from his memo is the list of topics: H2 regions in absorption, studying magnetic fields. Sandy Weinreb had just demonstrated you could build a digital correlator, so the idea of Zeeman splitting magnetic fields. And there was the great radio source controversy. Evolution had been discovered in radio source catalogs, but was highly controversial at the time. The little ticks there show that this was a pretty good summary of what was going to happen in the future. But just look at what was missed in the next 10 years. There was nothing known about quasars, cosmic microwave background, masers, and pulsars. So while indeed the following decades were perhaps the golden years of radio astronomy, the message here is that you could not possibly have foreseen what this imaging radio telescope would do. And the session that we've just been going through included, for example, fast radio bursts. And it's not much more than a decade ago that we knew nothing of their existence. So here's a little bit of background before I jump into the rest of this talk as to why I'm in this position. As you may know, Pawsey died shortly after being appointed as NRAO director, and Dave Hession took over as director. There's a picture of Dave Hession and myself down the bottom left corner there. And if you want to know what would have happened perhaps to the VLA if Pawsey hadn't died, then you need a talk from Miller Goss, who can tell you all about that. On the right is what was the final funding proposal in 1969 for the VLA telescope. An advisory committee was set up a few years after the funding was obtained. I was a member of that advisory committee, so I was familiar with the development of the VLA from a very early stage. Once construction was well underway, Dave Hession stepped down in 1978, construction essentially completed. Jack Lancaster was the construction manager, and if you want to know more about that period, look up the thing called the VLA Completion Report by Jack Lancaster, a very good summary. I joined the VLA in 1980 to take over as director of VLA operations, and shortly after I arrived, we had the VLA dedication and opening ceremony. So I'm going to talk about that period from 1980 to 1987, which was the beginning of operations at the VLA. Now, let's have a look at what was actually in the VLA proposal, because this concept written out here, and largely due to Hession, is very important, I believe, to the success of the VLA. The idea was to build a radio telescope which could make pictures of the sky with comparable resolution to an optical telescope. A very broad concept. And that was the basic performance goal for the VLA. And as Hisham pointed out, no such instrument exists at present. And when radio telescopes with these capabilities do exist, it will revolutionize radio astronomy. And it did. To be a bit more specific, if we dig into that proposal, the science case, which was about each page, they were called the key scientific drivers. It was radio galaxies, quasars, cosmology, and a few pages about other things, planets, galactic studies, and the 21 centimeter hydrogen line. But then have a look at, in the first decade, what was actually done with the VLA. Now, this is not current. This was in the years 1980 to 1991. Yes, radio galaxies, quasars, and cosmology were in fact all included in the first 10 years of observations, about a fifth of all the observing time. But all the rest there in black, which completely dominated the observing time, were in fact not part of the VLA proposal. So the story is a very standard one. If you look at the history, telescopes become famous, not for what they're proposed to do, but the things they discover after they are built. Now, the next thing that was fantastically successful about the VLA was the way the engineering specs were not just, the goals were not just achieved, but they were surpassed. And this again is not the upgraded VLA. This is the VLA as it went into operation in 1980 with significant increases in sensitivity. But in particular, have a look down towards the bottom. When the VLA was conceived, there was no concept of deconvolution. I'll mention that later. So the idea was an 8-hour synthesis, so one arm rotates onto the other, and you could get 3 images per day. That, of course, especially if you listen to the last talks, has changed incredibly dramatically, and we talk about millisecond imaging. Also, the idea was you would make a little image of the center of the VLA primary beam, about 100 by 100 pixels. Since there was no deconvolution, there was no point in knowing what else was in the beam. You didn't care about that. And already, because of experience with Westerbork, I had come from Westerbork myself, it was realized that 100 by 100 was completely inadequate. So did this telescope have any impact? Well, you bet it did. Here's a plot which is made by optical colleagues, and so there's no radio bias included in this. Jean-Paul Roy, Phil Puxley, and Dennis Crabtree, who I got this plot from, were comparing the optical telescope observations, the other 3 down the bottom here. But they did put on the same plot the VLA. And these are normalized to the time when observations first started, and it's how many papers were being published per year by each telescope. So the impact of the VLA is absolutely enormous, and I think it is fair to say it is one of the most successful and highest impact telescopes ever built. Space telescopes, of course, have an incredible burst of activity, but we're now talking about 40 years lifetime for the VLA, so the accumulated impact is indeed enormous. Now, my talk is based around a document I wrote myself. It was called The First 7 Years of Operations and covered the period 1980 to 87. And so I went back to prepare this talk and looked through that document, and here are the various headings. In the 15 minutes or the remnants of the 15 minutes I have left, I can't possibly expose you to all of these topics, but each of them are incredibly interesting. But I thought I would flash through just a few bits of statistics for each of those, and then I will concentrate a little bit on computing at the end. And let me, okay. the way the science changed, what was not well predicted, this is the plots here are by year, index on the bottom. You can see that the use of stellar radio astronomy was increasing dramatically, and the envisaged dominant use of extragalactic radio galaxies and so on is decreasing. This was partly because there were vastly more stellar astronomers, especially in the world and especially in the US, and the VLA could make great observations of stars, mass loss rates, and so on. The other thing that was highly successful was, and it was really Dave Hesham's very strongly held concept, that the VLA should be a national facility. So this shows the number of users versus time increasing dramatically. But notice the number of staff at the NRAO, which is the one on top, hasn't changed. That means the telescope was being used by outside users. And for radio interferometry, that was a first, because it used to be not possible to do this unless you were a black belt radio interferometrist. So it opened up radio to a world of users. But the news wasn't all good. I thought when I arrived, fantastic new telescope, the NSF will fund this thing to do all the great science. NSF incrementally reduced our budget during the first 7 years, and we had additional costs, the cost of power, and the fact that we had to buy computers out of operating budgets meant that we actually ran on a declining budget, which I thought was bizarre for the richest country in the world that had just built the greatest radio telescope in the world. So now I'm going to talk about early computing, because up till now I emphasized the huge successes, but the computing, and this is part of the story you won't easily find, was not such a fantastic success. First of all, most people don't realize that when the VLA was proposed, there was no deconvolution concept. That came during the construction of the VLA about 1974. It was realized that a big software effort would be needed. And in 1975, a group was set up under Bob Jalming to write what was called the Candid Software Package. It was written in Sail, as is pointed out above, which was going to be the computer language of the future, Stanford Artificial Intelligence Language. It was what was called top-down software, and it was a complete failure. So the decision to use a language which had disappeared by the time the VLA had finished, and the idea that you could write the software without understanding the hardware was not successful. It was also thought that no computer available at the time could possibly process VLA images. And so the idea was that there would be an analog optical image processor. Each telescope modulated a thin film, you shine a laser on it, you image that, and you take a photograph of the image of the sky. Well, in an amazing leap, Barry Clark realized that this new idea of deconvolution wouldn't possibly work with something which had the limited dynamic range of this analog image processor. And he showed that it was just possible to build a pipeline of multiple PDP-11 computers and array processors to compute the VLA images. That was the famous pipeline. And as the older among you will know, that was also, by and large, a colossal failure. However, read Bob Duquette's VLA computer memo 172, whatever happened to the pipeline. It became Bob Duquette's job to try and make it work. He failed to do so. But the lessons that should have been learned and are outlined in that memo are quite incredible. And of course, because people pay no attention to history, the same mistakes have been made in almost every synthesis telescope that's been built. The Candid software package was finally abandoned. Eric Greisen saved the day basically by taking his 3-element interferometer package, converting it for VLA use, called it Rancid. Mort Roberts didn't much like the name, and it got rebadged as APES. And of course, that was a huge success. But 1980, as we started observing, the VLA computer system was totally overloaded. It was completely inadequate. Observing time was reduced to 50%, primary just because of the computer load, and spectral line was greatly limited. This is what we had to do.
You're into overtime there, Ron.
All right, this is my second last slide. So that shows how we recovered building computer capacity from 1980 to 1987. And it would be kind of interesting. These are in Cray XMP equivalents, so some nerd can tell us how many orders of magnitude more it is even now. So that was the most dramatic change. And this is what it enabled us to do. On top is a picture of Cygnus A. It is the dirty image, and that meets the specifications that the VLA was funded to do. Deconvolution is added, and we get the image in the middle. And then finally, self-calibration was understood and really introduced to the world primarily through the VLA with incredible dynamic range. And I believe in the first talk tomorrow morning, Rick Perley will tell you a bit more about how this happened and how these dramatic changes in our ability to image has also changed the way we do astronomy. Thank you.
Thank you, Ron. That's a great talk. Anybody have questions for Ron? Oh, we have one in the chat. Is there any chance of anticipating serendipity?
By definition, no. And in fact, it is quite interesting. You can anticipate that there will be serendipity, but if you try to predict what is going to be discovered and look at history, you'll find out that very rarely succeeds.
Greg, you have your hand up.
Sure. You make the comment, which I strongly support, that the idea that we can predict what we're going to do with these instruments is often not achieved. So given that, what suggestions you have to us as a community, about the radio community, but also the larger astronomical community, in trying to decide between all the incredible ideas that we have out there?
Design a telescope with the maximum flexibility. And do not try to become very specialized to solve the current scientific problem. This is not the current funding scenario, but you can always tell the funding agencies and the review committees some science case. The science cases are useful because engineers need something very hard to design against. But don't imagine that that's the science that the telescope will become famous for.
We have a question from Shami in the chat. How do you feel about open skies as it started back then and as it moves into the SKA?
Sorry, I'm just trying to find the chat, and unfortunately I can't get rid of my display. Open skies. As you saw that increase in the number of outside users, these were not NRAO staff. Open skies, of course, has two meanings. One is that it's available not just to the staff of the national facility, but to anyone. And it was also a strongly held view by the US community, I would say broadly, that you make the most effective use of your resources by letting the best scientists use it. And in fact, if you want to take a purely economic view on this, you'll even get other countries to pay the salaries of the people that are making the discoveries with your telescope. So I am 100% supporter of open skies. And I would say that the VLA paved the way for other telescopes, certainly the Australian telescopes, to be open skies. And I do hope that we will eventually get SKA into the same mode. And I would exhort all of you out there to push them in this direction. And of course, eventually the US will become part of SKA and NGVLA is what was proposed as SKA3. So it's pretty much the same thing.
Question from Jose. In those days, was it considered to have another, I'm assuming he means VLA, another VLA as is two eyes are better than one?
Oh, sorry. Can you repeat the question again? I was trying to find the chat box and I can't turn this.
I think he's asking, was it ever considered to have
okay.
two VLAs?
You mean north and south?
I'm not sure. Jose, do you want to unmute yourself? And yes, I think he means north and south now.
Well, in a sense, the proposal to build the Australia Telescope Compact Array was really based on the idea of having a VLA type telescope in the Southern Hemisphere. There was never a proposal that I'm aware of the US to build a second VLA.
All right, thank you. Any other questions for Ron? Not seeing any. Here we are. Hari, what is your timeline for lunar radio telescopes?
In a meeting I was attending last week, I was quite surprised to see some earlier results from Chinese radio lunar orbiters. So in a sense, we now have some operating radio telescopes in the moon. So watch this space. The Chinese are proceeding quite rapidly to set up radio facilities on the moon. As we had the sort of global competition before, I have no problem with the US trying to recover its lead position and getting funding for the NASA proposed telescopes on the moon, one of which is a Arecibo type telescope, and put it on the moon far side. You've got the one place in the solar system with no RFI. It is a brilliant thing to do. And Joe Lazio might want to chip in.
Any further questions, comments, additions?
So Joe, what is your timeline for a lunar radio telescope on the moon? Is he still there? Oh, maybe Joe's not there.
Yeah, looks like Joe has left already.
All right, well then I will go ahead and close this session. Thank you very much to all the speakers. And of course, thank you to Anna, Amy, and Frank for organizing everything. It's been a fantastic day. And I'm looking forward to tomorrow as well.
Yep, thank you everyone. And if you have not yet heard about the surprise celebratory VLA gifts that we're going to send to all the participants, attendees, shoot me an email and I send you a link or instructions how to claim it. And thank you everyone. And I'll see you at, I'd like to say 9 a.m. Mountain Time tomorrow, but what is it? 14 hours from now? 16 hours from now.
Bye. Thank you, Anna.
Hey, thanks, Anna, for sorting all those things out for me.
Oh, no worries. Actually, that was Amy who did all the shuffling. So.
Oh, well, thank Amy, or thank you, Amy, if you're there.
was a great talk, Ram. Interesting. I guess this was all before I was even born. I should stop recording it.
Well, we could have stopped it a bit sooner. Thank you. Okay, bye.
Bye, Byron. Hopefully see you tomorrow and after tomorrow. Cool. Okay.
Thanks. I think that went pretty well. As far as I can tell, I don't know what you. I don't know what you guys had to do it.
Well, no, it's good to know how to travel outside because I was already inside the
Right.
space.
I bet.
Especially the first flower. So that's why I was like, I really want to. Yeah, actually, also like very happy actually. I was hoping for people interacting and sharing stuff, and I was hoping for it, but people do it. So I was super happy.
Yeah, that's right.
Yeah, so they seem to be all excited.
Yeah.
Yeah, it's an online job. You
Yeah.
go to English, you keep fading how much you need to be with the person.
Yeah. But also by that.
Oh, that is true actually. That is true. We actually really ended up with 290 registered recipients.
Right.
I know when I like 5 of them responded. Well, they didn't respond.
That was actually weird today.
Oh, really? I thought it was like 40.
Maybe probably 1 minute, right?
I tried it. Oh, okay. I think I saw one today. And then it, yeah, and then one got really late in your life.
Right.
Yeah. Really late in your life. You weren't gonna be like, oh, pretty scary. Yeah. No, I have actually all the videos for the video, so I can check precisely how many ants were there. So I'll give those numbers to you. Yeah, I am happy that people are doing sharing and stuff. Yeah, and for